Welcome to Learning Salt. My name is Seth House, and I'll be your guide as we talk about Salt, which is often billed as a remote execution or configuration management tool. But as we'll see by the end of this course, Salt is so much more than that. It is a fairly open-ended, real-time communication bus between all of the systems in your infrastructure. Salt is a huge and complex tool, but it's made up of many small and simple parts. This video series will cover and explain those various parts, starting from scratch, and building toward the high-level goal of installing, configuring, deploying, and managing a web application to a few VMs behind a load balancer. This course will provide a fairly fast-paced tour of the breadth of what Salt provides. Each section will be information-dense and contain links to relevant resources such as the official documentation, formulas, package repositories, and other packed resources. We're going to learn the history of Salt, how it works, why it was written. We'll talk about installation and configuration. We'll talk about remote execution, then configuration management. We'll talk about how to do complex multi-system management and application deployment. And finally, we're going to talk about how to react to real-time events. We'll talk about Salt's event bus, how to generate events, that sort of thing, and how to integrate Salt with third-party tooling. There's too much content in Salt to fit into this video course to be able to tackle other introductions as well, so viewers should have a basic familiarity with a Linux environment, navigating a system using the CLI, editing files, that sort of thing. Basic familiarity with the major differences between CentOS and Ubuntu will be helpful, but not required. We'll point them out as we go. Examples and demonstrations of how to install and use Salt will be given on a CentOS 7 and Ubuntu 16.04 system. By the completion of this video series, viewers should have an in-depth understanding of Salt's inner workings and the confidence of how to continue to dive into Salt, as well as where and how to find additional resources. So the next section is the installation and setup section, where we'll talk about an introduction to Salt and get it up and running. The philosophy of Salt. In this video, we're going to take a look at Salt's approach to system management. We'll talk about why Salt was written and why the tech stack was chosen. The very first commit to the Salt repository was just shy of 6 years ago at the time of this recording by a guy named Thomas Hatch. Now, Tom had had this ideal of system management software rolling around in the back of his head for a number of years, and he had written a few precursors to Salt, but they weren't quite what he wanted. The missing piece that he needed to make Salt was finally found in ZeroMQ, and we'll talk about that as we go, but ZeroMQ is a very high-speed, very lightweight networking library. It's just a library. It doesn't have a concept of servers and that sort of thing. It's just something that you use to build out something that requires a flexible network topology. And we'll talk about the various topologies that are possible with Salt as we go. As is evident in this commit message, the name Salt is intended to evoke salt as an essential nutrient. It's something that everything needs. It is essential for life. One of the core tenets of Salt is speed. Salt should be fast enough to not require cached data or a database. If there's something you want to know about your infrastructure, you just ask. Part of that is distributing work to the minions so that the master itself can have very lightweight system requirements. It is essentially just passing messages most of the time. In the default configuration, it requires a constant network connection. Now that allows you to do a lot of stuff and real-time stuff, but that's not the only network topology that's possible with Salt. So if you can't or shouldn't have a long-running network connection, we'll see alternatives to that as we go. And last, there should be fast encryption everywhere. You shouldn't wonder if this operation or that operation is encrypted. Everything is. So Salt is a generic communication bus, and this is something that is often overlooked about Salt. Salt is often lumped into categories with other similar tools, but it was written to be a very different kind of tool from the ground up. Salt was written to be a generic communication bus. That means that Salt is useful for remote execution. It is useful for configuration management, what we call state enforcement, but it is also useful for so much more than that, as we'll see throughout this course. One of the last kind of design requirements for Salt was deterministic execution order. This seems kind of obvious, but not all tools in this space do this. The idea is whenever you run something, it should run in the exact same order and produce the exact same result, no matter how many times you run it, no matter when you run it. It's a simple thing, but it's important to have. So in the next video, we're going to talk about how Salt communicates between the master, which is long-running, and the minions that connect to the master. Video 1.2. How Salt communicates. In the previous video, we learned the design goals for SALT. In this video, we'll learn how SALT utilizes a technology stack to meet those design goals, and we'll talk about what that stack is. The default network topology is a master and minion setup, where the minions connect to the master. And we'll talk about how SALT uses pub/sub and rep/rec to make that topology. And we'll talk about how SALT uses 0MQ and MessagePack on top of that. And then finally, we're going to talk about other topologies and other transports that SALT can make use of. So the default topology, the most common topology that you'll see in SALT, is a master and minion topology, where the minions connect to the master, and this is by far the most scalable topology. You can have many tens of thousands of minions connect to a single SALT master. The master has to be on a reasonably beefy system to handle that many connections, but in general, the master is not doing a whole lot. It's farming a lot of work off to the minions, as we'll talk about, and so it is a very scalable way to go. To do this, SALT uses a 0MQ connection between all of those systems. 0MQ, as we've talked about, is a very high-speed, very lightweight networking library that can make a variety of network topologies. For this, we're using what's called pub/sub and rep/rec. We'll talk about that in just a moment. Messages over this 0MQ connection are serialized and compressed using a library called MessagePack. You can think of MessagePack as being similar to JSON, except it is very, very fast. So the minions connect to the master, as we've talked about. The master requires two open ports, port 4505 and 4506. So since the minions connect to the master, then if you've got a lot of minions, the master is the only system that needs those ports opened. That becomes a very nice thing if you've got a lot of minions. And so the minions connect to port 4505 and they start listening for broadcasts. They subscribe to these messages from the master, and the master will send out these broadcasts. And the minions decide if they care about that broadcast or not. So that means that no ports need to be open on the minions at all. They connect to the master. The master broadcasts out the commands. And then there's a second channel on 4506. That's a dedicated two-way channel for other communication. So if a minion gets a broadcast, for example, then the minion can process that command and send the result of that back up to the master on 4506. If the master needs to call out to a specific minion, then it can do that on 4506 as well. 0MQ is the default transport, and it creates that network topology we were just talking about. We also use 0MQ to provide concurrency within SALT itself. But in the last year or so, we've been moving toward a Python library called Tornado to provide that concurrency layer. We'll talk a little bit more about that in just a moment. MessagePack, so we've talked about, does that message serialization. All of the messages that go into and out of SALT are JSON serializable. They're JSON compatible structures. And that becomes a nice thing to be able to rely on for reasons that we'll see. It's very easy to get data into and out of SALT because it's all JSON compatible. Now, there's other topologies that are possible with SALT. The most common is that master and minion setup. But you can also use SALT in what's called a masterless mode, where you don't have this high-speed connection between all of your servers. You're just using SALT as essentially a library. You can use SALT for the platform abstraction that we'll talk about, or the configuration management portion, without having that long-running connection. And it's also a very easy way to get set up with SALT. SALT has a system called multi-master, which is useful for highly available systems. What this looks like is if you've got multiple masters like this, and then you've got a variety of minions, those minions then connect to each one of these masters in either a hot or a failover setup, where if one of these masters goes down, the other one is already hot and it's just ready to go. Or if one of these masters goes down, all of these minions fail over and start talking to the other master. And so multi-master is useful for highly available needs. Then there's what's called Syndic. Now, Syndic is a way to either logically group your masters or your minions under a given master. What it does is it provides a master of masters. So if you've got a top-level master of masters, then you've got a Syndic master down here and a Syndic master down here. And then you've got a few minions that then connect to each Syndic master. And so what this allows you to do is this allows you to provide logical grouping. So each one of these minions connects just to the syntax master, and they are completely isolated from these minions over here. They have nothing to do with one another. And then the syntax masters connect to the master. So this provides a nice way to, say, isolate minions that have nothing to do with, say, other minions. It also provides a way to, say, scale. So if you've got 5,000 minions over here and 5,000 minions over here, these guys are just dealing with 5,000 apiece. And this guy can talk to these guys, and for all intents and purposes, this guy thinks he's talking to 10,000 minions. It's transparent to him that his messages are getting passed through these syntax masters. And then finally, there's SaltSSH. SSH is a lot slower than ZeroMQ, obviously, but it's a nice thing to rely on if, say, for security reasons, you can't have a long-running daemon, or you've already got SSH, and so you can't have another thing. It can be used in conjunction with ZeroMQ, and this is one of the nice things about SaltSSH is you can call out to some minions via ZeroMQ and some other minions via SSH. And if you want to, say, start with SSH and then switch over to ZeroMQ later, nothing in your Salt states or setup needs to change. You just change the configuration of installing that minion daemon, connecting it to the master versus telling the master which box to SSH to. So SaltSSH is a nice seamless way to, say, start with SSH and then upgrade to ZeroMQ as needs arise. So ZeroMQ is the default transport. There's also another transport that we've been working on, which is a raw TCP transport provided by the Tornado library. It's experimental, but it's pretty exciting because ZeroMQ has been really awesome for us, but Tornado and raw TCP allow us just a little bit more control over that connection. We can get into the internals a little bit more than ZeroMQ by design kind of abstracts those away and provides an easier interface. And then last, if you need it, there's an HTTPS transport via Salt API, and we'll talk about that in the last section. So in the next video, we're going to talk about how to install Salt. Video 1.3, Install Salt. In this video, we're going to install Salt from the official SaltStack repository. We're going to install the SaltMaster, SaltMinion, and Salt API packages, and we're going to discuss the dependencies that get pulled down with each of those. We're going to explain some of the differences in packages between some of the different distributions as well. The very best way to install Salt is from the official SaltStack repository, and you can get there by going to docs.saltstack.com. This is the official Salt documentation, and from there you can see instructions on how to install Salt. And from there you can see more specific instructions on how to install Salt for each of the various operating systems that are supported. I would invite you to read the instructions for any of the operating systems that you have to deal with. In this video series, we're going to deal with two. We're going to deal with CentOS. So we've got a master, which is running Cent 7. And then we've got two minions, Jerry and Stuart. So keep an eye on these tmux window names. Jerry is running Ubuntu 14.04, and Stuart is also running Cent 7. So let's start by installing the master. Whenever you install or upgrade Salt, always start with the master and then move on to the minions next. The reason for that is the master often has backward compatibility code in it. So a newer master is meant to deal with older minions, whereas the reverse is not always true. So let's start with CentOS, and you can see that the very first command is to install the repository RPM. This RPM contains the GPG key for the repository as well as the repository file itself. Once that's done, we can yum install salt-master. And let's also install Salt API while we're at it. Okay. That's going to pull in Salt and its dependencies. Let me scroll up and take a look at those real quick. So you can see that Salt API and SaltMaster both got pulled in. Salt API is quite small. The SaltMaster package is a little bit bigger. And there's one other package that is noteworthy, which is a Salt package. We'll talk about that in just a moment. This one is a little bit bigger than the other two, as you can see. So I'll let that go. And while that's going, I'm going to jump over to Jerry, and I'm going to install Salt on Jerry. Jerry is running Ubuntu, as we discussed, Ubuntu 14.04, trusty. And again, the very first step is to wget the GPG key for our repository and install that into the system via app. I'm going to paste that in. Now that we've got that in place, I'm going to manually create our repository file. This is a standard sort of approach with these Ubuntu and Debian systems. And I'm going to paste this as the contents of this file. That'll tell Ubuntu how and where to get those packages. So I'm going to save that out, and once that's done, I can run apt-get update as normal, and that'll update that files that live in that repository so that we can then install them from there. While we're waiting for that, I'm going to check back in with our master. Okay, that's now done. Because this is a CENT7 system, none of these services were created or were started by default. Back to Ubuntu, our update is done, so let's apt-get install salt-minion. There we go. That brings in Salt and its steps. And so we're going to let that run for just a minute. So as we just did, the best way to install Salt is usually via an OS level package, via that package manager, or via the official packages if you're on Windows or OS X. You can also install Salt via Python packages if, say, you're a Python shop, or if you want to develop on Salt, or if you've got a specific need like where you need to install Salt into a self-contained Python virtual environment, or virtual env. But for most people, just install straight out of the OS package manager of your distribution. Some of the dependencies that get pulled in with Salt, and we'll look at the list in just a moment, are networking and concurrency dependencies, cryptographic dependencies, templating and serialization, and then there's some optional dependencies. And we'll talk about those in the next section when we talk about execution modules. The Salt module ecosystem is quite large, and so we don't install a lot of those dependencies by default. For example, if you're not a MySQL shop, there's no reason to install the MySQL database drivers. So we'll talk about that in the next section in detail. And finally, there are some differences in the packages for each platform. Each package tries to adhere to whatever is most accepted or canonical on that platform. So, for example, this means putting config files in place or using split packages. So, okay, our Ubuntu minion is done. So if we take a look at etc salt, you can see that some of these files were put in place by the package, and some of them were put in place when Salt started up for the first time. And we'll talk a little bit more about that in a following video where we talk about Salt Key. But because this is an Ubuntu system, it starts the minion by default, and we're going to then configure the minion and restart it here shortly. Whereas on the CentOS system, all of these files and directories were put in place by the package. The service was not started by default. All right, so Salt is installed, but we've got to configure it and we've got to run it. So in the next video, we're going to talk about configuring Salt, and we're going to go through the various config options, and then we'll get it up and running. Video 1.4, Configure Salt. In the previous video, we learned how to install Salt, and in this video, we will configure that installation. We're going to talk about the master and minion configs. We'll talk about the configuration directories that are available. And finally, we're going to talk about SDB, which is a way to pull in dynamic configuration from an external source. So, starting with the master config, the default master config file is put down by most packages. Not all packages, but most packages. And the defaults in that file are usually good for most installations. The only time you're going to want to dive in there and start tweaking things is if you need to, say, change ports or paths or fine-tune security, or if you get into some very interesting scaling situations, you might want to change some of the values in there for scaling purposes. Chances are you're not going to have to do that until you get well into the thousands of minions, possibly even upwards of, 10,000 minions. So let's take a look at the default master config. Jump over to our master. We're going to pull up etc salt master. Okay. All of the values in this file are commented, as I mentioned, and the default values are right there next to the setting, and there's ample documentation. So I would invite you to spend a little bit of time looking through this file and the minion file when you have a little bit of time, just to see what knobs and dials are available to you. So things like, changing what interface the Saltmaster daemon listens on, or changing ports, or changing the user that the daemon runs as. In general, you can run the Saltmaster as a non-root user because the Saltmaster is just sending messages to minions. But if you need to use Salt, or if you want to use Salt to, say, configure, programmatically set up that Saltmaster machine, you're going to want to keep this as root. Another interesting setting is this root dir option. It defaults to the root directory on the other system. But this allows you to, say, specify where all of your configuration files and log files and that sort of thing live. So this is a nice setting to change if you want to prefix all of those directories all in one fell swoop. But for this video series, we're going to leave all of these settings as default. The minion config, again, has the same kind of thing. All of the defaults are usually good for most settings. Now, there's two caveats to that, which are common to the minion. which is, as we talked about in the very first video, the minion connects to the master, which means you have to tell the minion where the master is. In addition to that, the minion picks up a unique ID. We call that the minion ID, and that value is picked up by default from the fully qualified domain name of that minion. If you want to override that or fine-tune that, you can specify the minion ID in that file as well. So let's take a look at both of those. Jump over to Jerry, and let's edit our Etsy salt minion file. Once again, all of these settings are commented out by default, but as you can see, one of the settings is the master setting. So this tells the minion where that master is. Now, if you have a host name on your network, salt, which resolves to wherever your salt master is, then that's it. You can leave this commented and you don't have to do anything else. But oftentimes it is common to say uncomment this and specify that IP address or whatever else to the master. There's one other value in here, which is a common one, which is the ID setting, which allows you to specify, hard code the ID for that minion to use. Now, this must be a unique ID across all of your minions, and it picks it up from that fully qualified domain name by default. But it's here if you want to specify it. One other setting of note, which is the master authenticates the minion, as we'll see in the next video where we talk about salt key. But the minion can optionally authenticate the master as well. So this gives the minion an expectation of which master it will be talking to when it starts up for the first time. So that provides just a little additional security so that when that minion starts up, if there's, say, a rogue master on the network for whatever reason, you know that that's not the right master that you should be talking to. And that is the master_finger setting. And so that takes the fingerprint of the master's public key and it validates the identity based on that. We'll see how to grab that fingerprint in the next video when we talk about salt key. So it's there if you need it. Most of the packages, and certainly CentOS and Ubuntu packages, will create these master.d, minion.d directories for you automatically. If they're not there in whatever operating system you're on, feel free to create them create them manually. And what they do is they take .conf files, and it will read all of the files in that directory. Salt will read all of the files in that directory and load them all up. And so this is a nice way to say, store all of the defaults in the main salt configuration, and then just store your overrides in, say, a conf file. These are also nice directories to, say, version control. So let's use those directories on our minion here. So let's edit Etsy salt minion.d, and let's create a local.conf. Now the name of the file doesn't matter, only the file extension. Salt will read every file, every conf file in that directory. And so in here, what we're going to do is we're going to specify the two settings that we just talked about, which are the overrides. So we're going to specify master and we're going to specify ID. So the ID we want to hard code for this class to be Jerry, so that it matches my tmux window here. But if you like the fully qualified domain name, then you can keep that as is. And then instead of salt, I'm going to specify the IP address of my master. Anything that will resolve on the network can be input here. So an IP address, a host name, what have you. So let's jump over to my master and let's find the IP address. There it is. Okay. So I'm going to put that in here and I'm going to save that out. Now, this is an Ubuntu system, and as we talked about, Ubuntu will start services by default. So even though our minion was not configured, Ubuntu started that minion daemon, and so it picked up the fully qualified domain name as the default minion ID. Now, Salt will cache that minion ID in this file here, Etsy salt minion ID. The reason for that is say the fully qualified domain name changes for whatever reason, you don't want to de-authenticate your salt master, and so it caches that value. Since we've hard-coded that value in our local.conf, we don't need this file, and so I'm just going to delete it. Etsy salt minion_ID. Okay. So with that in place, let's go ahead and restart our service. Service salt minion restart. That reminds me. Since our master is on a CentOS system, it did not start the salt master service by default. So let's go ahead and do that now. System CTL salt master start. There we go. So now that master is running, our minion is running, and finally let's configure our last minion as well. Minion.d, local.conf, master. Grab that IP address once again, and the minion ID this time around is going to be Stewart. Okay. Since this minion is a CentOS minion, you can see that there is no minion_ID file in that etc salt directory for the reason that that minion daemon was not started by default. So let's go ahead and start it. Systemctl start salt minion. There we go. So finally, let's talk about SDB. SDB is a way to provide dynamic configuration settings from external sources. It is a pluggable interface in Salt, and we haven't talked about these yet, but we will. Salt is made of many pluggable interfaces. SDB is one of those. And one of the nice things about SDB is SDB values can be encrypted, and they can be pulled into the Salt configuration files, and those settings are referenced are decrypted or are looked up at the time that they are referenced, not when the daemon is loaded. And so the way this goes is, let's pull up the docs on SDB. They're here, right? And so you can see how to, say, configure SDB, and you can go through here and see all of that information. If you want to see all of the available SDB modules, jump to the All Module Index. And we'll talk about this in detail in the next section. But for now, let's just jump down to SDB. So you can see that you can pull values into the Salt configs out of all of these sources that ship with Salt, including, say, etcd or HashiCorp's Vault, that sort of thing. And so some of these sources are encrypted, some are not, but in all cases, these values are pulled into Salt when the value itself is referenced. So if you were to say use one of these values in a Salt config file, so etc salt minion, let's go with minion.d local. So the setting would look like, my secret setting, and then SDB : and then lookup path here, right? So that's what that looks like. And so whenever this is referenced, it then queries SDB for that value. And so I'm not going to demo it as part of this video series, but it's very, very valuable for pulling in configuration dynamically or pulling in secure configuration. So I thought I'd mention it. All right, so that brings us to a configured Salt installation. In the next video, we're going to talk about how to accept Salt keys and how Salt's encryption layer works. Video 1.5, Key Acceptance and Encryption. In the previous video, we learned how to configure Salt. In this video, we will learn how Salt's encryption layer works. We're going to cover authentication, encryption, managing keys with Salt Key, how the AES key rotation works, and how to generate keys using the Salt Key program. So let's start with authentication. Salt uses public and private RSA key pairs. And what this is this is the SSH handshake algorithm that has been implemented on top of 0MQ. So both the master and the minions generate keys on startup, and then they do the public key exchange, same as SSH does. Let's take a look at that real quick. So on our master, we can look in our etc salt directory, right? And one of the directories that we see that is specific to the master is PKI, okay? So if we look inside the PKI directory, there is a master and a minion directory. And in the master directory is the master PEM and master pub, and then a bunch of directories to collect minion keys when minions public keys when they come in. So if we were to take a look at our files, master, there we go. So you can see that the master PEM file is just a standard RSA private key, and the master pub file, standard public key, right? On the same token, the minions also generate one. So etc salt PKI, and then in this case, there's a minion directory, and there's a minion PEM and minion pub. Okay, so if we take a look at them, same thing, standard RSA private key and public key. So when the minion connects to the master for the first time, the minion sends its public key up to the master, and the master must then accept that public key. We'll see what that looks like in just a moment. But keep in mind that those daemons generate those keys when they first start up. So if you're ever troubleshooting something, or if you need to swap out the key for whatever reason, make sure that you delete that key on the minion as well as on the master. So Salt uses AES standard encryption, and there is a rotating AES key. By default, it rotates every 24 hours, And it also is rotated every time a minion key is deleted or rejected. Salt uses this to create an encrypted pub-sub connection. So when that publish goes out to all minions, that publish is encrypted using this key. And so in order to, say, deauthenticate a minion, if you say delete a minion's key, then after you delete that key, Salt will then rotate that AES key, so all of the other minions will re-authenticate and pick up that new key so that they can decrypt those publishes. And Salt key is the interface to accessing all of these key management facilities. However, Salt key is not magic. It is just a front end to moving files around in the file system here. So as you can see, these directories that we were alluding to on the master, these are the directories that collect minion keys when they first show up. So when we have a minion connect, it sends its public key to the master, as we talked about, and that key shows up in this minion's pre-directory. In order to accept that key, you simply move that key from this directory into this directory. But the best way to do that is to call out to the Salt key CLI utility, because it can do some helper things on top of that action of moving these keys around on the file system. One of the things that we need to do with a CentOS system, if you're following along, is by default it sets up a firewall, so we have to poke a hole in that firewall for the master ports. I'm just going to cheat, and I'm going to turn off the other firewall completely, just for brevity. But keep that in mind. If you're on a CentOS system, you're going to have to poke those holes in your firewall. If in doubt, if you ever run into any troubleshooting problems, that sort of thing, as you might expect, take a look at the minion log, var log salt minion, right? And it'll talk about why it couldn't connect, for example. So you can see back when, since we're on Ubuntu here, since it started the minion daemon with that default configuration, you can see that the minion was trying to call out to that host name of salt until we finally got around to configuring that here toward the end. So then after we did configure that, it could not connect to our master, and it's asking if our master is responding for the reason that that firewall was up. So consult the minion config and or the minion log to do that troubleshooting step. So Salt key, like most programs in Salt, has very, very great help output. So I would invite you to run salt key -- help. And it's a little long, so I'm going to go ahead and pipe that to less. Okay? And this will go over all of the options that are available to Salt key. So standard options for a lot of these CLI utilities, version information, that sort of thing. Logging options, another common one between all of the Salt utilities. External auth, which we'll get to in a later section. Output options, how to display those keys on output, and then finally actions. So here's where you can say list keys and accept keys and delete keys and reject keys, that sort of thing. And you can print out the key fingerprint, as we talked about in the last video. So if you want to see, say, the fingerprint of your master key, you run salt key --F, and there you go. There's the private, there's the public, and these are the fingerprints. This is what you would copy into that master finger setting that we talked about in the previous video. In addition to that, you can see that we've got a couple of unaccepted keys. Now that we've dropped that firewall, those keys have been pushed up. And if we take a look at etc salt pki master minions pre, you can see there are Jerry and Stuart's keys. So if we take a look at those, you can see that they pushed their public keys up to the Salt master. Okay? So now we must accept them. You can also generate keys using Salt key. And this is a nice thing if you need to, say, precede a minion. If you want to generate that key and put it on the minion so that when it starts up for the first time, it's already authenticated with the master. It's already been accepted, that sort of thing. So as I mentioned, the AES key will rotate by itself. So the minions authenticate to get the current AES key. And then they can decrypt the published messages on the wire. And whenever you delete a minion key using the Salt key CLI, it rotates that key, forcing all of the minions to re-authenticate and get the current key. And so that's one of the reasons that using Salt key, the CLI utility, is usually preferred for most operations. To generate a key, let's do that real quick. Look at the help output once again. Jump down to generate keys. So here we go, key generation options toward the end. Okay, so you can you can generate a key, and by default, it generates the key in the current directory that you run this in. So I'll keep that up, and over here, I'm going to run salt key, gen keys, and let's generate keys for, say, a minion called Frank. Okay, there's the return, and you can see now that we've got a frank.pem and frank.pub. So if, for example, we wanted to precede this key on our master here, if we run salt key without any arguments, you can see that we've got unaccepted keys for Jerry and Stuart. So we could just take Frank's key. Let's copy frank.pub to etc salt pki master. And then the accepted directory is minions. So minions pre is unaccepted and minions is accepted. So if we just copy that there, I'm going to do it without the extension, copy that to Frank. Now if we run salt key again, we can see that we do indeed have an accepted key for Frank. So let's go ahead and accept the keys for Jerry and Stuart. There's a variety of ways to do this. We can do salt key -a and specify Jerry and Stuart, or we can just do salt key -A, and a lot of these salt key arguments have this lowercase, uppercase variety, and that'll just say accept everybody. And so it'll prompt us before that happens. We're going to go ahead and say yes. And so now that key is accepted. Salt has moved those keys into that minions directory for us, and there we are. So in the next video, we're going to move on to volume 1, which is us getting started with how to use Salt. We're going to talk about execution modules and targeting and grains and all of the basics of using Salt day in and day out. See you there. Section 2, Execution Modules. So in this section, we're going to take a look at Salt's targeting system. And then we're going to dive into execution modules. We're going to talk about the basics, the anatomy of a Salt command, that sort of thing. We're going to call execution modules from the master and from minions, and we're going to demo some common execution modules. Video 2.1, Target Minions. So we're going to start things off by talking about why targeting is important. We're going to demonstrate common targeting types, and we're going to talk about grains as well. Now, we haven't run any Salt commands yet, and we're going to dive into the anatomy of a Salt command in the next video, but we're going to kick things off talking about targeting because it's such a central concept to Salt. Targeting is used in so many places, and it's the very first thing you do when you type in a Salt command, and so that's where we're going to start. So bear with me, and then in the next video we're going to dive into the details of what a Salt command is doing when you run it. So let's demonstrate targeting real quick. Let's do a salt star test.ping. Now in this command, the star is the target. As you recall in the last video, we accepted keys for Jerry and Stuart, and so both of them are replying, and both of them match star, so they're both replying with true here. It's hanging because it's waiting for a reply from Frank. As you recall, Frank does not exist. We just generated a key for him. We're going to keep him around for now because it'll be useful to talk about that in a little bit. But for now, let's stay focused on targeting. Now, one of the things to keep in mind with targeting is the target information is published to all minions. So when I do a salt star test.ping, all minions, Jerry and Stuart, both receive a star and test.ping in a payload, and they decide independently, does star match me? If so, then I'm going to run test.ping and return the result of that back to the master. If not, there's nothing else to do. It's a no-op. That minion is done. It's out of the picture. But the minion decides whether or not the minion matches that target and runs the function or not. This is one of the things that makes Salt scalable. If you've got 10,000 minions and you do a Salt star whatever, right, then 10,000 minions are doing that determination independently rather than the master trying to do that determination 10,000 times. And so that keeps things light on the Salt master and distributes that work. Now targeting is used on the CLI as we just saw, so you know which minions should run this command. It's also used in other places in Salt. So like which states should be applied to a given minion, that sort of thing. And that's one of the reasons we're talking about it first. Now, Salt's --help output, as we saw in the previous video, is pretty verbose for all of the Salt commands, Salt key included. So here we're going to run Salt-help. And again, we're going to dive into the details about this, but as you can see in the next video, but as you can see, the target is the very first argument that you pass to this. So For now, I'm going to scroll down to target options, and we're going to talk about the different targeting types that are available. So the star that you saw is a glob. It's a shell-style glob, and it matches on the minion's ID. So that star is matched against the minion IDs. But there's a variety of targeting options that we can apply here. So for example, if I wanted to match that minion ID using pro-compatible regular expressions, I could just pass the -e flag. Or if I wanted to match on a comma-separated list of minions, I could do -L. So, for example, that would look like Jerry, right? Test.ping. Or Jerry and Stuart, test.ping. And as you can see, this time around, we're not waiting for Frank, right? It's just that finite list. In addition to that, I can match on grains, which we're going to talk about in just a moment. Or I can match on pillar, which we'll talk about in the next section when we talk about the details of SALT's state system. I can match on IP sitter. So say, for example, I wanted to match all of the all of the minions that had a certain IP range. IP sitter would do that. Or if I wanted to match on a combination of any one of these things, right? I could specify this compound targeting type, and this lets me specify any one of these other targeting types, but combined with and or and not operators. So SALT becomes very, very granular. SALT's targeting system is very granular. It's very easy to say, I want to run a command on this group of minions, but not this group, and oh, I want to include this one guy over here, by design. And sometimes these SALT targets get a little lengthy, and so when that happens, then you save them under a human-friendly name, and that is a node group. And so that's how you would specify just a human-friendly name to pull in that larger target. So let's talk about grains. Grains are static information collected about each minion as the minion daemon starts up. They are Python functions that introspect the local system and return a little dictionary about whatever it is they query, and that is combined into a larger dictionary of information about that system. So they're generated when the minion starts, and they are kept in memory on the minion. They are also shipped up to the master, and the master keeps a cache of them so that the master can, perform some out-of-band checks, and we'll get into what those are a little bit later. It's also very easy to set custom grain values. So it's just a data structure, and so it's very, very easy to say, include this little bit of a data structure in the larger grains data structure. And custom grain modules are easy to write as well. Again, it's just a Python function that returns a dictionary. So for example, we've got a community contributed grain module that is for Amazon EC2 systems, and that module runs and queries Amazon's API to find out information about that VM, and so they're just very, very easy to assemble. So let's take a look at what some grain modules, some grain output looks like. And to do that, we're going to jump over to Jerry and run a command, and we're going to get into the details of this command in a later video. So again, just bear with me. For this, I'm going to run grains.items, and let's look at the output that this produces. So you can see there's a good bit of output. And let's just go through some of these data points. So we've got a lot of hardware information, BIOS information, CPU information, CPU model, architecture, attached disks, DNS information, fully qualified domain name, GPUs, the host name, hardware interfaces, the minion ID, the init system that this particular operating system uses, IP address information, interfaces, the kernel release, locale information, LSB information, the manufacturer and ID of the CPU chip, memory information, the number of CPUs, the OS family, the OS architecture, code name, fingerprint, a unique fingerprint of that particular OS and version, right? The major release, let's see what else. We've got Python and shell path information, SALT version information. We've got the UID and the user that the minion daemon is currently running as. We've got whether or not this is a physical box or a virtual machine. So a lot of information, and again, a lot of this is really easy to extend as you see fit. One of the quick ways to do that is to just call into this grains execution module, and we'll get into the details of this later, but you can just say set val foo is equal to foo, right? And if you do that, now we've got foo as part of this grains.items output, and so if I run this again, scroll up, foo will be in there somewhere. There we go. So it was that easy to add a hard-coded value, or if you've got dynamic values, again, just a Python module that returns a dictionary. So grains are very, very useful, especially if you're coming into, say, an infrastructure that you don't know a lot about. You install the Salt Minion daemon on all of your machines. They automatically generate grains. You collect those grains at some central data store, and poof, suddenly you do know a lot about your infrastructure. So that's grains. Maybe before we move on to the next video, we should demonstrate querying by grains. So let's jump over to the master here, and before we go, let's query by grains. And we're going to do this with the G flag. And let's say we wanted to query everybody that was running an OS in the Debian family. So there you can see that Jerry is going to respond with a true. And it's waiting to hear back from Frank because we don't know anything about Frank. So I'm going to go ahead and Control-C that. But say we wanted to do the same for Red Hat, right? Now Stuart will reply. So it's as easy as that. Now, what else can we do here? Let's do a combination. Let's do a compound command. Let's say everybody that's running OS family, Red Hat, and I'm going to qualify this with G at. So in a compound command, the G, the flag here, corresponds to the CLI flag. So instead of G here, it's going to be G here. So otherwise it's the same. OS family Red Hat, and we can say combine this with an ID query. So an ID that starts with Stu. Right. Oops. Forgot the test.ping. There we go. And so that uniquely identified Stuart. And again, we can get pretty granular here. We can do ands and ors and nots, and we can use any one of those values that we just went over to make this this target. So I hope that helps demonstrate how granular this can be. So in the next video, we're going to dive into the basics of execution modules. We're going to dissect that salt command, and we're going to talk about the details, the very first details of some execution modules. Video 2.2, Execution Module Basics. In this video, we're going to talk about a bedrock of Salt, which is execution modules. They are used in many places within Salt, and they provide a large library of common tasks that can be used at the CLI, or within states, or within Orchestrate, or the reactor. They can be scheduled to run, or they can aggregate arbitrary minion data that can be cached on the master for quick lookup. They're useful all over the place. So we're going to start by talking about the anatomy of a Salt command. Salt commands take many forms and syntaxes in different places in Salt, and so it's important to be able to identify and understand the various bits that make up a Salt command, even when you're looking at it on the CLI versus looking at it in YAML versus looking at it in something else. We're going to talk about the scope of execution modules, where and why to use them, where and why to use other module types. Salt's loader is a lesser known but a key part of Salt and execution modules. We're going to talk about how execution modules are loaded for OS-specific functions or dependency-specific functions, and how to tell when that happens. And we're going to talk about the aliases that execution modules are often loaded as. So let's start with the anatomy of a Salt command. So we've seen this before, right? But as I mentioned at the top, this structure that we're looking at, it is formed into a data structure that's shipped over the wire. And this data structure can take many formats in different places in Salt, but it's very, very consistent, where you've got the target, and then you've got a module, and then a dot, and then a function that lives inside of that module. And then everything after that is arguments that function takes. So again, very consistent, but there's some places in Salt where this gets a little confusing, and so it's important to be able to unpack this. So the target, as we discussed, module dot function, and then arguments to that function. Okay. So execution modules they're one-offs. You run them, and they run a function and they return the result, right? So Salt likes to differentiate between what we call flow versus state. Flow is something ephemeral. It's something you run and it changes the system right now, and that change isn't really tracked or enforced over time, right? It's just something that happened. Versus state, which is enforcing the state of a system over time. I want system X to always look like this. That is enforced over time. And so broadly, flow and state are represented in Salt as execution modules and state modules. Execution modules are Python functions that are inside Python modules. So let's take a look at the documentation module index. Okay, this is something that we're going to spend a lot of time visiting in this video series, because once you understand the basics of Salt, once you understand how Salt and minions communicate and when and why different functions are executed, really the thing you'll want to know about Salt is how to run a given function. What arguments does it take? What does it return? That sort of thing. And so this module index is the go-to place for when you understand Salt and you just need to know the details about a particular module. And there are many modules in Salt. And so it's more than any one person can keep in their head. Okay, so let's start with execution modules. Now, for historical purposes, execution modules, they were the very first module type. And so they are under this module index as M for modules, when in fact they are execution modules. Throughout this video series, I will call them execution modules. Whenever I say the word module, I will try to qualify it by saying what module type it is, because there's a lot of different modules. So let's start with the test.ping execution module. So really that's the test module and the ping function inside of that. So I'm going to scroll down until I get to test. There we go. The test execution module. And this module is comprised of a lot of functions. So you can see that there's an arg function, or you can see the full list here on the sidebar. So I'm going to jump down to test.ping. And you can see that test.ping is used to make sure the minion is up and responding. It is not an ICMP ping. So as you recall from the previous video, the minion performs the matching. So the minion decides whether or not it matches this target, and then based on that, it runs this function or not. And so it's not an ICMP ping, but it's useful to make sure that the minion is up and responding, because the minion will get this target, evaluate if it matches, and then run test.ping and return the result. If the minion's not up, then it can't run this, and so we won't get a response back from them. And so that's why test.ping is useful for that. If we jump to the Salt Git repository, which lives at github.com/saltstack/salt, we can jump down into the Salt subdirectory, and then from there, there's a subdirectory for each one of the module types, basically everything we were just looking at in that module index. So I'm going to jump into the module subdirectory. And then, as you might have guessed, there is a test.py, the test module. Not that one, but that one. There we go, test.py. And then within this Python module, there is a function called ping. So let's do a search for that. There we go. Now, as you can see, the documentation is extracted from the code, used to make sure the minion is up and running, or up and responding, not an ICMP ping. Returns true, right? Exactly as we just saw in the documentation. And we build the documentation from extracting these doc strings in the source. Now, there's a little bit going on here with proxy minions, but really the thing the takeaway here is, if we're not running a proxy minion, test.ping returns true. Okay, that's it. It's a function that returns true. If the minion is up and responding and can execute this function will return true, and we will see that at the CLI. It really is that simple. Execution modules are just Python functions that return JSON serializable data. That's a nice thing to be able to rely on, is all of the execution modules in Salt return JSON serializable data. That means it's very easy to get that data out of Salt and into other places, and we'll talk about that in detail in a future video. There's no interface. There's no subclassing, nothing like that. It's just a Python function that returns JSON serializable data. So if you've got an existing library of Python things, you can just drop them into Salt, and Salt will just run them. So Salt has what's called a loader. The Salt loader is responsible for loading all of these module types that we're talking about in this module index. So the Salt loader goes through and decides which one of these modules are applicable to the underlying operating system or have dependencies met or whatever else, right? And they are loaded into memory based on that. Salt is a heavily pluggable system. The core of Salt is really very simple. Oftentimes, the way I'll diagram this is the core of Salt is this tiny little thing that maintains a always-on encrypted high-speed communication channel. And then surrounding Salt is just a ton of these pluggable interfaces. And each one of these pluggable interfaces it has a corresponding module type that does something wildly different. Some of these are execution modules, some of these are state modules, some of these are auth modules, some of these are beacon modules, right? But Salt itself is quite simple, and the module ecosystem is very, very large. So as you can see in the module index here, there's a lot of execution modules that ship with Salt. And that's where the complexity lies, not in Salt core. It's also very easy to customize Salt by writing custom modules. Salt was written to be pluggable, and it was written to be extended by you, the user. And so the test.ping is a perfect example of how easy it is to write a custom Salt module, and then Salt has a system that we'll see in a future video where you can write your own Python module, automatically distribute it out to minions, and get a response back. So it was made to be pluggable, heavily pluggable. So Salt's loader will load all of these module types, and as there's many, as we've seen, there's many of them. Just to see a quick overview, there's auth modules that can call out to external authentication servers. There's beacon modules that can periodically collect information about the underlying system. There's cloud modules that can spin up VMs. There's engine modules that are long-running modules that listen to Salt's event bus. There are file server modules that pull files out of external systems. There's grain modules, which we've talked about. There's execution modules. Here we go with M. After that, there's NetAPI modules that we'll see with Salt API that start up some long-running API interface. There's outputters that take this information, this JSON serializable information from execution modules, and format it for display. There's pillar modules which pull data into Salt. There's proxy modules that allow us to integrate with systems that cannot run a long-running minion daemon. They're things that provide API interfaces or switches, specialized or simplistic hardware. There's queue modules to be able to maintain a persistent queue on the Saltmaster. There's renderer modules that govern how the Salt state system is programmed. There's returner modules which get data out of Salt into arbitrary data stores. There are roster modules that tell Salt SSH how to generate a list of minions, minions that it can SSH to. There's runner modules that are similar to execution modules, except they run on the master. There's SDB modules, which we've talked about briefly, that pull data into Salt configuration files. There are serializer modules that know how to either ingest or produce data structures from various file types. State modules, which we'll talk about in great detail, which enforce the state of a system over time. There are thorium modules. Thorium is kind of a decision engine that's baked into Salt. There are top modules that generate top files, which we'll talk about in the states section. And finally, there's wheel modules that govern programmatically managing the Saltmaster, setting files on the file system or managing keys, that sort of thing. So a lot of Salt modules. And all of these can be extended first class. So that module index is alphabetical by module type, and again, it's one of those go-to places once you understand how Salt works. So Salt's loader will optionally load modules based on OS requirements, right? It doesn't make any sense to load the Windows modules on a Linux system and vice versa. So these modules know how to perform various checks as the minion daemon is starting up to decide which modules to load and which ones not to. Similarly, some of these modules have library requirements. So the MySQL execution module will not load if the MySQL database adapters are not installed, or the Git module will not load if the Git CLI is not installed on the system. So it saves that memory and avoids having to do that work. In addition to that, some of these modules are loaded under a common alias. So for example, there's a package module, or a user module, or a command module. And in these cases, these are other modules with other names that are loaded up as these names, as these aliases. So for example, if I were to do a quick search for package here, let's see, let's jump down to execution modules. There we go. So there's an apt package module, and there's a D package module, and there's a FreeBSD package module, and there's a Mac package module, and an OpenBSD, and an O package, and then this is a virtual module that those other ones get loaded as, just kind of a placeholder. Package NG for BSDs, there's Solaris, there's Windows, right? And so each one of these OS-specific package modules knows how to query the package manager for that operating system in the most efficient way. So in the case of, say, the Windows package module, if you ask it which packages are installed, it will of course query the Windows registry. But if you do that on a Debian system, then it will call out to apt cache, or if you call out to a Yum system, it'll do an RPM-Q, right? Excuse me, a Red Hat system. And so they know how to query, or they know how to talk to that underlying system. And so those platform differences are abstracted away for you. So you just call package, you just call user, you just call command, and it knows the best way to call out to that underlying system, or whatever else has been abstracted away. And some of these modules have been renamed for a variety of reasons. So like the command module has been renamed so that it doesn't step on the Python command module, but in the Salt code it's the command mod. And so whenever you see that in the code, all Salt execution modules have this example, the CLI example. And so if there's ever any question about what name a module is loaded as, look at the example. So you can see that the command mod is loaded as CMD. Right? And that'll be true for all of the package modules as well. So in the next video, we're going to actually get our hands dirty, and we're going to demonstrate some common execution functions. We're going to run them and see what they produce, and we'll see some of those underlying OS differences. And that'll be a big deal when we get into states as well, abstracting away those platform differences. Video 2.4, Common Execution Modules. We're going to build on what we learned about execution modules in the previous video, and we're going to demonstrate some common execution functions. There's many execution functions, as we saw when we looked over that module index, and you're not likely to ever run most of those. But there's some execution modules that you're very likely to run regardless of what you're doing with Salt. So we're going to cover the common execution modules: package, user, service, status, test, command, grains. And then we're going to talk about some execution modules that expose some Salt internals, namely match and CP. So let's start. Let's go through them one by one. A good way to discover execution modules at the CLI is via an execution module, specifically the sys execution module. So I'm going to limit my query to Jerry, and I'm going to call sys.doc test.ping. And what this will do is this will extract the documentation from the function that I'm specifying there, same as the documentation was extracted to build the HTML version of the documentation. We're just doing it at the CLI now. And so this is calling out to Jerry and grabbing that documentation from Jerry. And as you can see, it's exactly the same as what we saw in the other docs, not an ICMP ping, right? In addition to that, you can just specify the name of the module. I'm going to pipe this to less. And now we can see the documentation for all of the functions in the test module. And then, of course, I can call it without any arguments at all, and that will show me all of the documentation for all of the loaded modules. So as you can guess, that's a tad long. In addition to that, we can do things like list modules, and so this will list all of the execution modules that have been loaded on Jerry. And we can also do list functions. That'll show all of the functions in each one of those execution modules. So let's start with the package module. Let's do a sys.doc package.list pkgs. So what this does is this lists the packages currently installed on the minion, and it has the package name and the version. Now, as we talked about in the previous video, each one of these package modules queries the underlying operating system and whatever is the most efficient, quickest way to get that data. So in the case of a Red Hat system, it'll call out to RPM-Q. In the case of a Windows system, it'll consult the Windows registry. So let's do a package.list pkgs on Jerry and see what we get back. So there we go. We got the information just that fast, and we can see all of the packages and their versions that are loaded on Jerry. So this is a taste of what I meant in the introductory video when I said that Salt was written to be fast enough that if there's something you want to know about your system, about your infrastructure, you just ask. So say you wanted to know whether or not wget was installed on your minions, you just run this command and you find out in an instant. So for example, if we wanted to, say, query both Jerry and Stuart, package.list pkgs, I could pipe this to, say, grep, and I could grep for wget. Now that's not going to be super helpful because, as you'll recall from that example, it was outputting a representation of a dictionary. So what I'm going to do is I'm going to use an outputter, which we haven't talked about yet, but I'm going to use the text outputter, which is useful for integrating Salt with shell tools to see which minions produce what. Now that produced a little too much data, so I'm going to cut, and I'll cut it, say, 20 characters. And so there, we've got a quick overview of which minions have wget installed. So you can see that Jerry does, Stuart does not, and it's just that fast. So package.list packages queries the system for what packages are installed. But we can also use it to change the system. So let's actually install wget on Stuart. So let's call out to Stuart. And for this, we're going to do package.install wget. So this is calling out to whatever is the best way to install packages on the underlying OS. So in the case of Stuart, that's calling out to yum, and it's just doing a yum install wget. There we go. Now wget is installed. So if we query them again, we'll see that both minions now have wget installed. So it's just that fast. If there's something you want to know about your infrastructure, just ask. There's a variety of functions in the package module for upgrading or doing more specific queries or holding packages or uninstalling, all of that stuff. So I would invite you to look through that list of functions to see what all is available. All right, now let's talk about the user module. Very similar to the package module in that you could say query minions to see user.list users. And that'll show you all of the users that are available on the system as a list. You can add users and all of that. So let's pull up sys.doc user. So add users, information about the user, full name, groups, all of that, changing groups, setting the home directory, all of that stuff. So again, it's a mix of functions that change the system or query the system, that sort of thing. Execution modules are totally open-ended in what they do, and that's one of the reasons that they're so useful from a variety of places. So say we wanted to pull up the information on a particular user. Let's do the getEnt, in fact, because that returns a bit more information. So let's do user.getEnt, and let's query let's do the root user. So there we go. We've got the full name, the group ID, groups, home directory, all of this stuff for the root user, just for the asking. Let's talk about the service module, meant to either query or start services, that sort of thing. It abstracts out whatever init system the underlying operating system uses. So one's using system D, one's using system 5, that sort of thing. So once again, sys.doc service. So you can see service.available, service.disable, service.enable, right? So you can set a service to start on boot, or you can see if it is currently enabled to start on boot. You can start, stop, reload, all of that normal stuff. So let's get service.running. Okay. Service.running. I think that was list running, wasn't it? Oh, get running. So there you go. Now this is an example of how there are just too many execution modules in Salt to keep in your head at any one time. I use Salt day in and day out, and I forget which execution modules take which parameters or what they're called, that sort of thing. And so I reference that module index all the time. So don't be shy or don't be embarrassed about doing that. There's just too many execution modules to keep in your head at any one time. And so once you know how to use Salt, you're going to want to pull up the documentation on how to use a particular module to do whatever it is you need to do. All right, next up, the status module. This one's a lot of fun. So let's do a quick search for our modules.status. And so this one can query the underlying operating system for various status information, disk stats, memory stats, load average, uptime, that sort of thing. And so this is a nice way to query an infrastructure for performance information. So say we were to do status.uptime, and we can get uptime information from Stuart, or Stuart and Jerry. just that fast. Right. Let's do status dot, how about disk stats, disk usage. There we go. And just that fast. And again, all of this data is JSON serializable, so it's really easy to take this output that we're getting from these minions and feed it into some data store that we can use for, say, querying, or we can generate graphs or any of that, just that fast. The test module we've seen a bit of with test.ping. There's a few other functions in the test module which are useful, one of which is test.version. And that'll show you the Salt version that's installed. Or you can see test.versions report. Let's see, versions report. And that'll show you not only the version of Salt, but the version of all of Salt's interesting dependencies. And so this is a nice thing for, say, a bug report, if you ever have to file one of those. The command module is very, very useful for shelling out. So we could do command.run. And from here on out, it's just a shell command. So we could run the whoami shell command. Salt is running as root on both of those. Or we could say run the date command. Or we could do a directory listing of etc salt. One of the things that we did with when we set a custom grain is custom grains are stored in a little YAML file. So we could cat that file. We could say cat etc salt grains. I don't think Stuart has one, but I believe Jerry does. So there we go. So Jerry's got that little foo-foo that we set in a previous video. Stuart does not. So they were just shelling out. Command.run is one way to go. We could also do command.run all, and that'll show us not only the output, but also the PID, the ret code, standard out, standard error, that sort of thing. We can do command.script. This one's an interesting one. This one takes a path to a salt file, and we'll talk more about that in detail later, but my script, .sh. And what this does is this transfers my script.sh from the salt master to each one of the salt minions, and then executes it locally and returns the result. So it's a nice shortcut around that workflow, and you get to store that script centrally on the salt master and version control it, for example, in just one place. There's a variety of arguments that the command modules take. And so this is one of those things where you're definitely going to want to pull up the documentation in the all module index. So M for execution module. Let's jump down to the command execution module. And let's take a look at command.run. So one of the interesting arguments that this takes is the user to run it as, or the current directory to run it as, or the shell that you want to run it under, or any environment variables you want to set for the duration of that. In addition, you can specify this template argument, which is a lesser known argument. And what this allows you to do is this allows you to run the command that you're executing through a templating engine that allows you to, say, reference grains or other data from within Salt right there in the other command. Pillar data is a big one. So definitely look at the documentation for each one of these. And last but not least is grains, which we've seen a bit of already. So with grains, you can do grains.items, and that'll output all the grains, and we've seen that before. We could do grains.setVal, and we've seen that. We could do grains.get. So say we wanted to get a specific grain. Show me what OS family each one of you are under. And we can also do we can do lookups within data structures. So for example, say we wanted to find out if SE Linux was enabled. Well, we can see that SE Linux is that information that we want is under a data structure here. So we can say query SE Linux enforced. And the way we would go about doing that is we would say SE Linux : enforced. And that would drill down into that data structure so that we could pluck out just that one data point that we're interested in. So that's a whirlwind tour of the common ones, and we're glossing over a ton of nuance and detail in every single one of these. And so when you have a particular need, pull up the docs and see what's available. Last, let's cover two more execution modules. Salt internals are often exposed via execution modules. It's just something that we do in Salt semi-frequently. So CP and match are two examples of that. The CP module is interesting. CP dot, let's go with list master. So this will list all of the files that are currently available on the master. So we're calling out to both Stuart and Jerry and saying, query the master and tell me what files you see. So right now we don't have any files, but we will when we get to states, and cp.listmaster is a nice way to go about that. In addition, we can use the CP module to say push files from the master down to the minion. So when I mentioned that command.script before, it uses the CP module to actually transfer and checksum to make sure that that myscript.sh is in the correct format and with the correct, it's up to date, the latest version is available on the minion, that sort of thing. And so it uses the CP module to transfer that file from the Salt master down to the Salt minion. And the CP module can push files back up from the minion to the master if it's been whitelisted. So the CP module is quite useful for listing files or transferring files. And then finally, there's the match module. The match module is interesting in that we've talked about in Salt's targeting system, where if you run a test.ping or any other command, each minion says, do I match either Stuart or Jerry? Yes? And so it executes that conditionally. Well, the way it does that is it calls out to the match module. It says, do I match Stuart or Jerry? And then we want to specify that we're passing a list target, right? Try that again. There we go. List target. And so this is exactly how each minion will decide if it matches the target when it gets sent down. So it'll call out to this match module. If we've specified a list target, it'll call the list function in the match module, and that'll return a Boolean or not. If it returns true, it executes the function. If it doesn't, then it doesn't, right? And this is also one of those things where it starts to get a little fuzzy when you're looking at a Salt target as to what's a Salt target and what's an argument. Now, this Salt is very consistent on this. It just takes a little while to kind of get an appreciation of what's what. So this is the target here, and this is the target type. This is the function, module.function, that we're asking the minion to run, and this is any arguments to the function. The arguments to the function just happen to be the target, right? But those are just arguments. It's just a string of the arguments, and so that's an example of where it gets a little confusing. So I hope that's clear, and we'll cover this in a few other places in Salt as we go. All right, so we've gone over the common execution modules. So in the next video, we're going to call execution modules from both the master, as we've been doing, and from the minion, because Salt is both push and pull. Video 2.4, call from master or minions. In this video, we're going to take a look at either master-centric invocation or minion-centric invocation. We're going to use Salt call to invoke Salt. We're going to use Salt call to debug Salt modules. And we're going to talk about how Salt maps arguments to Python functions. And then we're going to talk about the difference between positional and keyword argument and how those are parsed at the CLI. So Salt is both push and pull. And what that means is you can initiate a Salt job or you can run an execution function from either the master or from the minion, and the result is the same. It doesn't matter where you invoke it from. You can invoke it from a scheduled job, or from orchestrate, or the reactor, or really anywhere else, and the result is the same. You're just calling a Python function with a set of arguments. And so what that looks like at the CLI is Salt call allows you to invoke from, say, a minion. That's the common use case. And it takes the same structure as Salt from the master, except it's just missing the target parameter because you don't need it. So there's nothing different about calling Salt call from a minion and calling Salt from a master. It still communicates with the Salt master as necessary to, say, transfer files or return job results, but you can also run it standalone. So you don't have to run with a master daemon running, and salt call allows you to tap into that salt library of functionality without having a master. Now, noteworthy is salt call does not reuse the running salt minion daemon if there is one. So if you've got a running minion daemon and you call salt call, it's its own thing. It doesn't reuse any of those existing memory spaces or processes or anything like that. And salt call is also quite useful for debugging because it produces a lot of output. And it's a window into viewing what system calls salt is making under the hood. So let's take a look. So we've seen already that we can say call, how about list target to avoid triggering Frank, waiting for Frank. Let's do Jerry and Stuart. And here's our test.ping, right? So there is, right. So there is our result from test.ping, and we've got this targeting semantic. But if we were to jump to, say, Jerry directly, we could use salt call to do test.ping. And we just need to omit the target here because we already know the target. We're on the target. Since this is just running on Jerry, as opposed to, say, being broadcast out to both Jerry and Stuart, we just don't need that targeting semantic. But everything else is the same, so we can still do, command.run and ls etc salt. And we get the exact same output. So you can tune up the debug logging with salt call. And what that looks like, it's the same for all salt commands, and it's -L for the logging level, and then you specify that level. So let's go with debug level logging. And if we run that, then we can see that salt produces a great deal more output. So let's scroll up and take a look at it. So first of all, you can see salt is reading in a bunch of minion config files. It's setting up some Zerum queue sockets for probably concurrency. It's still decrypting the master's AES key, so we're still talking to the master. We're still authenticated. We can still request things from the master. And here we go. So executing command ls/etc/salt from this directory. And here's the output from that. So we can see that salt is actually shelling out, and we can see what it's shelling out with right there in the debug output. Okay. So one place where this becomes really helpful is visualizing what salt is calling out to for some of these other modules. So let's take a look at, say, network.netstat. So this is a very useful function that produces a data structure of netstat information, all of the connections that this particular minion is made and to who. So if we scroll up, and if we look at the debug output for that, actually let's run that again with debug output, try again. So -L, debug. All right. So now if we look at the debug output, one of the things we can see is we can actually see that salt just did, it just called out to command.run for us transparently, executing command netstat with these flags from this directory, right? And so this is the actual output from netstat, which you should be familiar with if you've run netstat on the CLI before. And so what salt has done is it's shelled out, run this command, same as you could at the CLI, but then it's parsed the output into a data structure that it ships back up to the salt master. So we can clearly see that we're looking at a data structure here, and that data structure was parsed out of this string that netstat produces. And so a lot of the times what salt is doing is it's wrapping normal system calls and just making that either a consistent interface or parsing the output like here. And we can see exactly what salt is doing if we call with that debug logging. CLI programs take arguments, and they use those arguments to call Python functions in the way that we've seen. So we can use both positional and keyword arguments. And the keyword arguments can be parsed as YAML, and this becomes an interesting way to pass in complex data structures from the CLI. So let's see what I mean by that. So in the case of, say, let's go with command.run, okay? So command.run takes an argument, and we're passing this in as a positional argument, as a string. And we're going to do an ls in the etc salt directory. So it is calling command.run with this argument. And let's pull up the docs for command.run to see exactly what this argument is. So M for execution modules, and it is the command mod execution module, if you'll remember. Let's jump down to the docs for command.run. So you can see that command.run takes an awful lot of arguments. And the very first argument that it takes is the command to run. And we're passing this in as a string, and we're quoting it to protect it from the shell. We don't want this to get parsed by bash. We want to send it to salt. So command.run is getting called with this string. And that string is being used as the positional argument to command. Right? If we wanted to change anything else here, we would then pass it in as an additional argument. Now, to avoid having to pass in everything as a positional argument, Salt also takes these keyword arguments. So, for example, let's go with CWD. So, say we wanted to execute this from, say we wanted to execute ls, and we wanted to execute it from that directory. We could pass in a keyword argument, CWD equals /salt. Right. So now, if I run that, the output should be the same. But this time around, what we're doing is we're passing in two arguments. One string and one positional argument and one keyword argument. Both are strings. And we can pass in a mix and match of positional arguments or keyword arguments. In fact, we don't need to use positional arguments at all. We can see here that the first argument is called CMD, and so we could certainly pass this in as CMD equals ls. And again, we get that same output. So everything to the right-hand side of these equal signs is also parsed through the YAML parser, and this lets us pass in complex data structures here at the CLI. So I'll show you what I mean by that by using a function in the test module. I'm going to do test.arg, and this will just echo out everything that I pass in. So first I'm going to pass in a positional argument, foo, and then I'm going to pass in a keyword argument, bar, and I'm going to give that an argument of bar. And now I'm going to pass in a third keyword argument, baz, but baz is going to be a complex data structure. So I'm going to quote this to protect it from the shell. And everything to the right-hand side of this equal sign is going to be run through the YAML parser, meaning it has to be valid YAML. So if here I do quux and quux, oops, like that. Now if I run this, let's take a look at the data structure that Salt actually parses. So here we've got a positional argument of foo, as expected. Now in keyword arguments, ignore everything that starts with pub, that's a little bookkeeping that Salt uses internally. We can see that bar was indeed passed in as a key value pair. And baz was indeed passed in as a dictionary, a complex dictionary. Let's do one more. Let's do quux is equal to true. And now we can see that quux came through, and it is not a string. You can see that this is expressed in yellow. It is an actual Boolean value. And so that allows us, again, to pass in a complex data structure. We're not limited to just strings. We can pass in numbers or Booleans. This will come back when we're invoking the Salt state system and trying to pass in pillar data from the CLI. So I'll return to this example when we get there. All right, so in the next section, we're going to dive into Salt states. We've talked about execution modules now, and now we're going to move on to Salt state modules. We're going to start with kind of a high-level overview of state modules, a user-centric overview. And then from there, we're going to dive into the details of what the state system is doing behind the covers, which is quite a bit of stuff. So thanks for joining me. See you in the next. Section 3, the state of an infrastructure. In the previous section, we got up close with Salt's execution modules and targeting. In this section, we're going to build on that knowledge to learn about Salt's state modules that make use of execution modules for much of the work that they perform. So we're going to talk about the philosophy of Salt's state system, why it was written, how it works from a high level, how state modules relate to execution modules. We'll write our first state to actually change a system. We'll take a look at common state functions. We'll dissect state functions, how Salt actually calls them. We'll talk about the layers of the state system, renderers, declarative versus imperative execution. And then we'll talk about the execution flow of a state run, ordering, and then we'll do a step-by-step walkthrough of an entire state run. And then finally, we'll end the section by talking about debugging Salt states. Video 3.1, the philosophy of Salt's state system. The state system was written to be a terse and powerful configuration management solution, and it was a natural next step after execution modules because it could reuse that existing library of functionality that they provide. In this video, we're going to take a look at flow versus state once again. We'll talk about how states are idempotent and execute in a deterministic order. We'll talk about how they are run on the minion and compiled on the minion. And then we'll talk about how the entire system is comprised of simple individual function calls. So once again, flow versus state. Flow is one-off, it's ephemeral. It is a function that queries a system or changes a system as a one-time operation. You run it once and it's done. Versus state, which is defining the state of a system or the configuration of a system and enforcing that state over a period of time. It's writing a configuration file that says, I want system X to look like this, what is described in this configuration file, and then having that enforced over time. If the system needs to change to match that, it will be changed to match that. And if it doesn't need to be, then nothing will happen, right? In addition, states are idempotent. If we run a state that's going to install the Apache web server, we don't need to care if it was installed already or not. Salt will figure that out. We can run the state over and over and over, and the end result will always be the same. Salt will figure out all of the steps necessary to make the current state of the system match what is defined in an SLS file. Each SLS file is comprised of many state functions, state function calls, and those state functions will be called in a deterministic order. Every time you kick off a state run, it will run in the exact same order as the last time you did it. It sounds like a simple thing, but not all tools do this, and so it's a nice thing to be able to rely on. We'll see throughout the course as we dive deeper into the state system how you can, say, specify ordering either explicitly or implicitly and have that order enforced between runs. Now, the minions are the ones that actually run the states. The work is distributed across all of the minions, which means the Salt master is only responsible for sending out that initial command and then transferring any files that any of the minions request to those minions. The minions themselves compile the state tree, as we'll talk about. So, for example, say this is our master, and we've got a bunch of minions that are connected to our master. Then the Salt master sends out the publish, as we've seen already with execution modules, and all of these minions get that publish, and they kick off the state run. If they need any files, they'll request those from the Salt master via that two-way channel that we talked about in the previous section, and they will compile the state run. And so what that means is they can use local data. If this guy's a CentOS machine and this guy's a Windows machine, right, they can use grains data that we talked about to generate the details of a state run. So distro-specific file paths or package names. They can shell out, right? Each minion can run execution modules or shell commands to collect information from that local system that can inform the state run. So, for example, a state run can fail early if the system load is too high, or if there's a maintenance flag on the machine, or Salt can change the behavior of a state run based on some condition. For example, it could check if SE Linux is enabled, and it could switch SE Linux to permissive mode during the state run, and then switch it back at the end of the run. And it's going to be different for each minion. So if this is CentOS and this is Windows, right, we're going to have each one of these minions is going to have a state run that differs from the other minion. It's going to have different file paths, different package names. It's going to call different commands. It's going to do different things, and Salt helps abstract away all of those, as we'll see. So the execution is managed locally. Each minion will manage its own state run and request any files from the master that it needs. And finally, when each state run is done on the minion, regardless of how long that takes for each minion, the result is then returned back to the Salt master and saved in the job cache. So the state system is just comprised of simple function calls. This is one of my favorite things about the state system. There's no magic, right? Salt doesn't know anything about CentOS or Apache or what a service is or what it means for a service to be running. Instead, Salt runs a series of very simple functions in the order that you tell it to, and each function performs an individual action. And if any other functions care about the result of that action, they can declare how they care about that result, and we'll see what that looks like when we talk about requisites in the next section. But it really is that simple. It's just running functions, and once you can kind of wrap your head around what each one of those functions is doing, the state system as a whole becomes very, very simple to reason about. And so I'll spend the remainder of this section and the section after this kind of going over that. So in this video, we learned from a high level how the state system operates and what problem it solves. And in the next video, we're going to watch the state system operate, and we're going to use it to start to configure a system. Video 3.2, our first state. In the previous video, we talked about salt states from a high level and what function they perform in the salt ecosystem. In this video, we'll write one, explain the parts as we go, and then look at a few other common state functions. We'll start by talking about YAML, then we'll write the state, and we'll take a look at the package, service, and file state modules. So YAML stands for YAML Ain't Markup Language. It's a serialization format. It was made to be easy to read and easy to write for humans. There's a few gotchas, some edge cases, and we'll go over those throughout this video series. Noteworthy is SALT is only using a tiny subset of YAML's features, really pretty much just the JSON subset of those features. Now YAML is a superset of JSON, which means valid JSON is valid YAML. If you're not familiar with the YAML syntax, it's a good idea to compare the YAML version to, say, a JSON version as you go. The one that I use to do that is this one here. The reason for that is YAML is a really easy to read format. It doesn't look like a data structure sometimes, but it is. It is a data structure. And so sometimes it's useful to look at it as something that's a bit more common of a format to view a data structure in. So I use this YAML-online-parser.appspot.com, but there's many others available. So let's create our first state. To do that, we're going to create the serve salt directory. This directory does not exist by default. The reason is you might be using salt without using the state system. That's a common thing. Salt, as we've talked about, is many modular interfaces, and it's not uncommon to use this module or that module and not all of the modules together. So we're going to create this directory, and what we're going to do is we're going to initialize it as a Git repository. So serve salt. I'm going to change directories into that directory. Now, it is a good idea to version control your salt states, especially if you're working in a team environment. And then we're going to create our first state. And we're going to install the Apache package. Okay? To do that, we're going to create an apache.sls file. In here, I'm going to start with a human-friendly identifier. Install Apache. This should describe the states that come under it. Next, I'm going to do package.installed, past tense, with name Apache2. Okay? So this is a complete state to install Apache. It is calling package.install. This is similar to execution module, the syntax for execution modules, in that it is the module.function. And then everything that's after that is arguments to that function. Let's take a look at that function now. So if we jump back to the salt module index, we've seen execution modules under M, but this time we're going to be doing state modules. So let's jump to S. Now some state modules will have similar or even identical names to execution modules, but keep in mind that state modules and execution modules are completely separate. Sometimes state modules call execution modules under the covers, behind the scenes, but they are different module types, so don't get them confused. So let's jump down to the package state module. So you can see, as with execution modules, there's a bunch of functions in this module, one of which is installed. And installed takes as the very first argument. Now all state modules take a first argument, which is name. And that's why we've got name here. If we were to say also pass version, right, then we would do that in the exact same way. Version colon, and then, some version. 1, 2, 3. So keep in mind that this is a data structure that we're looking at. If we paste this in here, see it's nice and readable here, and this is what it looks like as a data structure. You can see it as a dictionary of dictionaries, and then within there is a list of single key value dictionaries. So name Apache, version, right? If we did version here. So it is a list of single key value dictionaries, and those dictionaries are then mapped to the arguments in that function call. So let's take a look at a few common state modules as we're building out this state. So let's save this, apache.sls. And in order to run this, we're going to do a salt. I'm just going to target Jerry for now because we've hard-coded Apache 2 as the package name. And that is a valid package name on Debian machines or Debian family machines, but not CentOS machines. So it's not going to run on Stewart right now. We'll get to that in a moment. So then I'm going to do state.sls Apache. Now, noteworthy is state.sls is an execution function, right? It's a function in the state module, and it's an execution function that takes an argument, which is Apache. So an execution function is what kicks off the state system. So if I run that, it'll take just a moment as apt-get is updating and then installing the Apache 2 package. And so the workflow that's happening here is when I hit enter, this execution function, gets broadcast out to all minions, same as before. So Jerry and Stewart all get Jerry state.sls Apache. Jerry and Stewart both say, do I match Jerry? In this case, only Jerry does. So then Jerry executes state.sls. The very first thing that state.sls does is it asks the saltmaster, do I have a copy of apache.sls? In this case, no. So it asks the saltmaster via that two-way communication channel for a copy of apache.sls, this file here. This file is sent down to the minion using a function that we've already seen, which is cp, or it's on a module that we've already seen, which is cp cache file apache.sls, right? And this cache file, this does a conditional, it checksums the file and it does a conditional download of that file from the salt master, and it stores it on the salt minion in a cache directory. So it always makes sure that it has the most up-to-date version of that file. If it doesn't have the file, it'll download it. If it does have the file, it will compare the checksum on the minion to the checksum on the master and only transfer it if the checksums don't match. And then it will run this file through the YAML parser, producing a data structure, which is handed off to Salt's state system. And I'll go through that in a little bit more detail later, but keep that in mind. So there we go. We've just installed Apache. Let me scroll back up there. You can see that this is the response that we get from Jerry, saying package.installed. The result was true. Comment, just a human-friendly description of what happened, some timing information, and then a changes key in that dictionary. So there's a couple of fields here in this return format which are noteworthy. The main two are result and changes. Okay, changes is a dictionary that is either populated or not, and in this case you can see it was indeed populated. And so we've got Apache 2 and the version that got pulled in, as well as any other dependencies that came with Apache. So there we go. Apache is now installed on Jerry. Since Jerry is running as running in the Ubuntu family, he has automatically started up the Apache service by default. But it's not a bad idea to make that explicit using the service module. So let's take a look at the service module. So let's do start Apache service.running name Apache 2. In this case, the init script has the same name as the package name. Okay. Let's pull up service.running real quick. Back to our module index. We're still in states. So let's jump down to the service. Not that one, not that one, but that one. And again, when you're jumping through the module index, make sure that that you're looking at the right module type. So like there's several modules with service in the name. In this case, we need states.service. Okay. So don't get tripped up there. So service.enabled, service.running takes name as the first argument again, right? The name of the init or RC script used to manage the service. It also takes a flag called enable, which sets the service to be enabled at boot time. Now this doesn't matter on Ubuntu systems, but it will on CentOS, so let's go ahead and add it. Enabled true. Okay. Enable. There we go. All right, so now we've got two states and two IDs. This is the ID of the state, and this is the state. Now we can group multiple states under a single ID. If we did that, we'd probably want to rename this install and start Apache kind of a thing. And that's perfectly valid. In this case, I'm going to keep them separately, and we'll get into some best practices in the next section. So I'm just going to keep them separate for now. So we're going to install and start Apache. Okay. Let's do one other thing. Let's put a configuration file in place. Let's do let's do a welcome page. So on Jerry, let's take a look real quick. Switching over to Jerry. Apache lives in, or Apache's welcome page is in var www html index.html. Okay, so let's go ahead and put that in place. Now, I'm going to add welcome page. Let's just go with welcome page. And for that, I'm going to call a state function called file.managed. File.managed is a workhorse of Salt state system. You're likely to use it day in and day out. So the name parameter is the file path that we want to write to. In this case, we're going to override this existing file with a new file. So I'm going to specify that. And file.managed, let's pull up the docs on that. So we're still in the states here. Let's jump down to file, states.file, file.managed. File.managed takes many arguments, as you can see. The name parameter is the location of the file to manage, and then we can get the contents of that file in a variety of ways. If we leave out any other arguments, it'll just touch the file. It'll make an empty file for us. We can specify source to transfer a file from the Salt master to the Salt minion. We'll do that in a bit. But for now, let's just go with contents. Contents takes a string to put down. And this brings us to a very useful feature of YAML, which is multi-line strings. This is something that comes up very frequently in usage in Salt. So if we end the line with that pipe character and then indent 2 past the C, everything we put here with consistent indentation will be put into that file. So we could do doctype HTML body, leaving out a few tags here, paragraph, let's do head 1, I guess. Hello world. Okay, I'm going to save that out, and so now if I run this, it'll put that the contents of this file in place. Now, one thing to keep in mind, we're going to talk about the ordering that this is going to happen in detail as we go. But suffice it to say, this will execute in top-down order. So the order that appears in the source, it will execute in that order by default. So this file.managed will be put in place after the package is installed and after the service is started. Okay. Let's go ahead and run that again. State.sls Apache. It'll do that cache file business again, check some of the files, see that it's changed, update it, and there we go. All right, here we go. Install Apache, that ran first. Start Apache ran second. It was already running, nothing to do there. And then welcome page ran, and you can see that that file was indeed updated. And here is the diff, the unified diff of the changes to that file. So you can see that we lost an awful lot of content, and we gained a few lines here at the end. So there we go. There's the summary of our run on Jerry, and that file is now in place. Let's take a look at the result of that. Let's grab Jerry's IP. So I'm going to do network.ip adders. Grab Jerry's IP. Jump over here, and there we go. So in this video, we got our feet wet with a few common Salt states. In the next video, we're going to pull these 3 states apart and look at what each one is doing and what each one is returning. Video 3.3, Dissect State Functions. In the previous video, we saw how to write a few kinds of common states. In this video, we're going to dive into what each one of those states is doing. So we're going to take a look at how Salt maps a data structure to a function call. We're going to talk about the anatomy of the return from each state function. We're going to talk about the anatomy of the state function themselves. And finally, we'll talk about dry run mode. So we covered this briefly, but what SALT does is it maps data structures to Python function calls. And it does this in the state system, and it does this at the CLI, and it does this in the reactor and orchestrate, and really everywhere in SALT is mapping data structures to Python function calls. So for example, let's pull up the docs on install Apache. That's a state module. So S for states, and we'll jump down to package. Not apt package, but package. States.package. There we go. Package.installed. So package.installed, as we've talked about, takes name as a parameter and a few other things. And as you recall, when we look at this, in the YAML format, it looks human readable. It doesn't look quite like a data structure if you're not familiar with YAML. But if you view that in, say, JSON, then it does, right? Package.installed, and then a list of dictionaries. And so those are used to call that function. It says, find this module, find this function, call this function with these parameters. But one of the interesting things is if, say, we were to do salt jerry state.sls Apache, right? This is doing the exact same thing, and we can actually see the data structure that salt makes when we look at the event bus in the last section in this video series. But basically, there's a dictionary that's sent over the wire that's published out to all minions saying, here's the target, here's the function, here's the arguments, right? Just a dictionary with target, arg, and then fun. And so salt, so each minion, right, Jerry and Stuart both get that, and they say, well, I see that that there's a target in there, so do I match that target, yes or no? If I do, then I'm going to look up this function that's been loaded into memory, and I'm going to call this function with any positional or keyword arguments that have been specified here. So it's just mapping a data structure that was generated on the master to a function call that happens on the minion. And the state system is exactly the same way. So here's the anatomy of a state. So we've got the ID of a state, and that is something that identifies, it should be human-friendly, human-readable, something to identify to humans that all of the states that live under this ID do a particular thing. And as you recall, you can have multiple states that live under a single ID. And really, there's no pros and cons to doing that. It's just really whatever is best to organize your state tree. And we'll talk about some best practices for doing that in the volume after this one. So again, module.function, and then any arguments to that function as list items. It's a list of dictionary key value pairs, single key value dictionaries. And that is a state call, right? The return structure for state functions is structured, unlike execution functions, right? Execution functions are very free-form. Test.ping returns a Boolean. State.sls, as we've seen, returns a dictionary. So sky's the limit there. But for state functions, they return a dictionary, and that dictionary has these three set keys plus a few other things. Result, whether it succeeded or failed or is running in dry run mode. Changes, which is a dictionary saying any changes that were made to the system. That dictionary is empty if no changes were made. And then comment, which is a human-friendly description of what changed on that system. So, for example, if we run our state.sls Apache here, we will get back one of those for each state that ran. So nothing needed to change with install Apache, but we got the result is true back. We got an empty changes dictionary back. Same here, right? If this state had failed, this would be false, of course. If we were running in dry run mode, it would be none. Let's go ahead and edit something so that happens. Let's do a serve salt Apache, and let's change our hello world here to an exclamation point. Now, if we run that, we can see that nothing needed to change with the first two states, right? They're already set up correctly, but the welcome page was indeed changed, and here's our diff, right? Changing that dot to a exclamation point. And so the result there is true because it succeeded, and changes this time around is non-empty, okay? So that's useful for one state to programmatically inform another state that either there was a success or failure or the system was changed. And we'll get into this when we get into SALT's ordering and the requisite system where you can build up a dependency tree. So, usually you'll want to start the Apache service after you install the package, but you probably don't want to try to install or to start the service if the package install fails. And so we'll set that dependency up explicitly in a later section. But the way that that this service state finds out about that is through this result and changes fields in that return. As I mentioned in the previous video, each function in Salt State System just does its own thing. It doesn't know anything about what comes before or after it. So it just is, we would set this up to say, don't do this if this other state that I'm requiring fails. And it doesn't know anything about that state. It just looks to see if it failed. And so that makes Salt State System very simple and very kind of easy to grasp. Let's switch this back. So I'm going to switch that back to let's go with a question mark this time around, and I'm going to save that out. And let's kick this off in dry run mode just so you can see how that differs. Test equals true. So very similar to what we've seen before. These two didn't need to change, so nothing to do there. They're basically no ops. But in this case, something did need to change, except we were running in dry run mode. So the result this time around is none instead of true or false. This indicates to Salt that that something will change if we run this in an actual run, and you can see that changes dictionary is then populated with the changes to be. So very broadly, each state function goes through the following checklist. Does anything on the system need to change? Am I running in dry run mode? Make the change, check the result. So let's walk through that. So does anything on the system need to change? So say we've got our package.installed here at the top, right? It needs to know, it runs first, and it needs to know, does anything on the system need to change? In other words, is Apache already installed on the system? Well, it doesn't know. And so it's going to farm that work out to an execution module. Generally speaking, state modules they just perform this workflow that we just went through, and they're very simple things, and they farm all of the actual work out to execution modules. So it needs to know if Apache is already installed. And the way it does that is package.list pkgs, same as we've seen in a previous video, to list all of the packages that are installed on the system. And as you recall, this is done in the most efficient way for the platform. So on CentOS systems, it calls out to rpm-q. On Windows systems, it consults to registry. So it can generate this list very, very quickly. And then it looks in that list to see if Apache 2 is already in that list. So it's not grepping, it's done in Python, but the result is the same. So it runs that and it looks to see if Apache 2 is in the output. And in this case it is, so this is now satisfied and it no ops, right? So, okay, so nothing needed to change, and then it moves on to service.running, and again it calls out to an execution module to consult the list of running services to see if Apache 2 is there, and then it moves on, and so on and so forth, right? So the execution modules do the actual work. If, for example, Apache 2 had not been installed, then it would then call out to an execution module to install the package, same as we've already seen. It would call out to package.install, present tense, Apache 2, to actually install Apache, right? So the state modules farm the work out to the execution modules. So say we needed to, we found out that Apache 2 was not in that list, so we need to install Apache 2. It then checks to see if it's running in dry run mode. And it just checks a global variable to see if that's happening. If it is running in dry run mode, then it bails out early. It doesn't change the system. It just bails out early and produces that dictionary that we were just looking at, saying this is what will change when you run it for real. If it's not running in dry run mode, then it makes the change by calling out to that execution module, and then it usually checks the result of that operation and produces that final dictionary saying, here's a report of what did change on the system. So the execution modules provide that actual functionality. Finally, let's talk about dry run. So the dry run keyword argument is just a regular keyword argument that's accepted by several of the functions inside the state execution module. So as you recall, there is an execution module that kicks off the state system. So if we jump to the module index, this is M for execution modules, and there is a state execution module. So state.apply, state.highstate, state.sls, these are all functions that take a keyword argument called test, right? So keep that in mind. This is specific to the state system, so you can't run any execution module and expect dry run mode to work. It's only within the context of a state run, and this execution module just passes that along. In fact, it passes it along as a global variable. If, for example, we were to jump over to the minion, let's jump over to Jerry and edit the minion config, etc salt minion. We could, for example, put a configuration option in here, which is test equals true, right, in YAML syntax. So if I were to save this out, now every state run that I run defaults to being dry run, right? And then if I wanted to override that on the CLI, I could pass test equals false. So really that's the only thing that's going on. It just sets that variable for the context of the state run. I'm going to leave that out for the video series though. And that's that. So in this video, we went a level deeper into the state system when we talked about how Salt performs many of those actions. Now, in the next video, we're going to return to the state tree and we're going to perform a step-by-step explanation of a full state run, including file transfers and that sort of thing. Video 3.4, Execution Flow of a State Run. In the previous video, we investigated the layers that make up a state run. In this video, we're going to return to the states that we've already written. We're going to walk through each of the steps, the data flow and execution flow of each step of that state run, from fetching files to rendering to executing and to returning the results. So broadly speaking, the execution flow of a state run goes a little something like this. The execution module, the state.sls execution module, is invoked. That gets broadcast out to the minions. The minions request any files from the master, so any files are transferred and cached as necessary. The renderer system kicks off. That is handed to the state compiler. The state module invocation happens one by one, and then the running dictionary is returned, and that is what is displayed. So we're going to cover some of this stuff in more detail in some future sections. So keep an eye out for those, and I've put little numbers for when we'll talk about each one. But let's go through it. So say we do a salt Jerry state.sls Apache. So if we hit enter here, what happens is on our master, when we hit enter, that broadcast goes out. Jerry gets it and Stuart gets it. Jerry says, do I match Jerry? Stuart says, do I match Jerry? Stuart, of course, does not, and so he no-ops, right? He doesn't return anything. He's just done. He's out of the picture. Jerry does match, and so Jerry will then execute the state.sls function. And the state.sls function is executed with this as an argument. And so the very first thing it does is says, do I have a local copy of apache.sls? And the way it does that is it runs the CP module that we've already seen. It runs CP cache file, and then the path to that file, right? And so this cache file goes through the process of looking to see if it exists locally. If it doesn't, it'll request it of the master. If it does, it'll compare the checksum of the local file to the checksum of the file on the master, and if they don't match, it will grab a new copy from the master and overwrite that cache. So then, after all of that, we've got a local copy of that file on the minion, right? And it's just the SLS file. It hasn't been processed or anything like that. It's just the SLS file directly as we've seen it. To demonstrate that, let's jump over to Jerry and just take a look at that file. There you go. No surprise. All right. So that file is then run through Salt's renderer system. Now, we've only talked about part of that renderer system so far, which is the YAML part. We'll get to the Jinja part. But suffice it to say, it goes through Salt's renderer system producing a data structure, the high-state data structure that we've been talking about. If you wanted to see that high-state data structure, you can, instead of running state.sls, you can run state.showSLS. And so if I do that, what will be output is the high-state data structure. So you can see this is pretty much what we've typed into the SLS file, except there's a few extra keys. It grabs a copy of the Salt environment, it grabs a copy of the SLS name, that sort of thing, and it's put an explicit order key in there. It's also separated out package.installed for us, And that's just a little internal bookkeeping. We don't need to go into a lot of detail on that here, but pretty close. This high state data structure matches pretty close what we typed into that SLS file. And so the renderer system produces this, and this is handed off to Salt's state compiler. Salt's state compiler then takes that and produces what's called a low state, and you can see that by running show low SLS. And this is what that data structure looks like. It is a list of dictionaries, an ordered list of dictionaries. And so you can see that that list has been ordered by this order key. We don't need to go into a lot of detail about the low state data structure. Suffice it to say, the high state data structure is human friendly, basically what you type in. The low state data structure has been optimized a little bit for being more machine friendly. It's a little bit easier to execute on. So that data structure is given to Salt's state compiler. The state compiler then goes through that data structure one by one and starts executing each individual state. So it will start with install Apache, right? So it gets to this ID, it executes each one of the states inside of that ID. So it goes to package.install, installed, and it goes through that workflow that we talked about in the previous video, you know, the pre-check, the post-check, all of that. And then it takes the result of this and it puts it into what's called the running dictionary. That is an in-memory dictionary where it keeps track of that result in that changes dictionary that we talked about in the previous video. So it puts that, it takes the result of this function and puts that into a dictionary with a key that allows it to look up the result of that dictionary. So if we ever have a state that depends on another state, it knows how to look that up. And we'll get to that when we talk about requisites. So then it moves on to service.running, takes the result of that, puts it in the running dictionary, and then finally file.managed and puts that into the running dictionary. And the running dictionary is easy to see because the running dictionary is what we're looking at here. This is the running dictionary. It doesn't look like a dictionary. It has been formatted for the CLI here through Salt's outputter system, but this is the running dictionary, and this is actually the order that things ran in. So that's a nice way to debug ordering issues, is you look at this running dictionary. This ran first, this ran second, this ran third. Okay? So you can see it put our index file back into place. And that's it. So yeah, so that running dictionary is the final result that is returned. It's a JSON serializable dictionary that's returned to the Salt master, and the Salt master takes that dictionary and runs it through Salt's outputter system to print the results to the state run. We can, of course, save that to a database or whatever else we want to do with it, and to really dive into that data, especially over time or across a large infrastructure. But that's the full execution flow of a state run. And so in this video, we learned all the steps that Salt performs during a state run. This by itself is very helpful in debugging a complex state run, and we'll return to it a few times throughout the course of this video series as we do a deeper dive, continue to do a deep dive on states. In the next section, we're going to take a look at how to debug a state run and gain visibility into the steps that it's going to perform and the commands that it runs on the minion. Video 3.5, Debug States. In the previous video, we walked through the full execution flow for a state run. In this video, we're going to close this section and volume out with some debugging tips. We're going to talk about how to develop directly on a minion. This isn't strictly necessary, but it can reduce the save, refresh, compile time necessary to save a file and then check the result. We're going to use salt call for debug logging, the same as we saw with execution modules. That'll show us a little bit extra information about what that state run is doing behind the scenes. So let's start by talking about developing directly on a minion. Now, unlike with execution modules, we've got files that we need to deal with. We need to transfer those files from the Salt master to the minion in order to execute them. If we wanted to avoid that step and have those files directly on a minion, we could use this setting here, File Client. So if we jump over to our minion, I'm going to jump over to Jerry, and I'm going to edit etc salt minion. And if I were to do a search for File Client, there's a default setting, there we go, and it defaults to remote. If I were to switch this to local, then this would cause the minion to reference the local file system for all SLS files. And this works for custom modules and pillar and that sort of thing as well. But but specifically for the SLS files, it will reference a local serve salt directory. Now, I'm not going to use this in this video series, so I'm going to leave this commented, but it's there if you need it. Salt is pretty fast, and so usually it's not a huge win, but it's there if you want to develop that way. If you ever want to do that as a one-off, you can also just do -- local to your salt call invocation, and the result is the same. It references that local file system instead of calling out to the master. So if I were to do a state.sls Apache, you'll see that it did not find the Apache SLS file because we do not have a serve salt directory on this machine. All right, now let's talk about debug logging. So just like we saw with execution modules, it is useful to tune up the logging level using that salt call in exactly the same way as we saw with execution modules. And that shows us a little bit more about what's going on behind the scenes. So I'm going to do this again without the -- local, and I'm going to bump up that that logging level to debug. Okay. So now when I run this, it's going to produce a bit more output. And then here's our familiar state run output. As you can see, nothing changed. So let's look through this debug output for some interesting things that we can pluck out of here. So one of the things that we can see is the file is transferred from the master. If I can find it, there we go. So it's referencing that path. It's changing that Apache argument to an Apache SLS and changing that to a Salt Apache SLS, so it can look it up on the Salt master. It's considering this path, this cache path, to resolve that file. And then you can see here that it is skipping transferring that file, right? The latest version of that file is already in the cache, like we would expect. And then it goes ahead and it compiles that template. It outputs some profiling information, which is quite interesting. So you can see that the Jinja renderer took a certain amount of time, and we'll talk about Jinja in detail in the next volume. We can see the result of the Jinja rendering. Again, we'll circle back to that. We can see more profiling information to see how long it took the YAML renderer to parse that YAML result and produce that data structure that we've been talking about. And we can see the result of that YAML rendering. So this is the actual data structure that it produced. And then we can go through and if we look closely, we can see the individual state runs as well. So running state Apache 2 at this time, right? Executing state package.installed for Apache 2, executing command, right? Deep package query, right? So it's checking, it's calling out to that execution module to find out if Apache 2 is installed, exactly as we talked about. It's already installed, so nothing needs to do. Completed state Apache 2 at time, duration, right? So useful information. And we can see the order that it's running all of these states in as it goes. And so we can see that information repeated for each one of the other states. And that's all there is to say about debugging. It's a little noisy to parse through, but a lot of useful information there if you run into a snag, or if you're wondering how long something took, or if you've got a long state run and you're wondering where the hang-up is. That's a great way to find out. So in this video, we learned some simple tricks for debugging states locally on a minion. The next video will begin volume 2, and we're going to dive into many advanced techniques for writing salt states, including a lot more debugging tips. So stay tuned for that. See you in the next volume. So we'll start with section 4, expand states with Jinja and Pillar. We're going to dive deeper into YAML and Jinja, and we're going to talk about how they should be used and how they should not be used. We're going to discuss best practices for writing reusable and maintainable states and how those relate to salt formulas. In this section, we're going to do an introduction to YAML, Jinja, and the other renderers that are possible. We're going to write reusable states and maintainable states. We're going to talk about YAML and Jinja best practices and gotchas. We're going to configure states using Pillar data, and we're going to learn salt formulas, and finally we're going to learn about debugging Jinja. Video 4.1, Introduction to YAML, Jinja, and other renderers. In this video, we'll explore salt states as data structure generators. Again, but this time we're going to be using the renderer modules to generate the data structure using a variety of syntaxes and methods. We're going to take a look at renderer pipes. State files are essentially data structure generators, and we're going to talk about why Salt generates states. Salt is syntax agnostic, Salt doesn't care what it is that generates those data structures. And we're going to talk about how salt can be either declarative or imperative depending on the preference of the author. So to start with, salt uses what are called renderer pipes to decide how to produce that data structure. The default is Jinja to YAML. And one of the things that I like about this syntax is it very clearly evokes, if you're familiar with Unix pipes, that these are separate steps. Jinja does its thing, and the result of that is handed off to YAML, who does its thing, and the result of that is handed off to Salt's state compiler. There's many other renderer modules available. So if we jump to the module index and we jump down to R for renderers, you can see the list of renderers that ship with Salt. And there are many. The default is Jinja to YAML. But if you don't like Jinja, if you don't like YAML, you can just mix and match any one of these. You know, if you want to write in straight Python, if you want to write in a Python-like DSL, PyDSL, or PyObjects, both look an awful lot like Python, right? Package.installed, service.running. Same end result, but a different syntax. If you want to, say, encrypt your SLS files at rest, you can run that through GPG and then through Jinja and then through YAML, right? Same as normal. And one of the nice things about this shebang syntax is you can set the default render pipe globally in your master and minion config, but if you just want to do a one-off, you can put this shebang syntax at the top of your SLS file. So for example, here is our serve-salt apache.sls file that we've been working with. If, for example, we wanted to swap that out with, say, Python, what we could do is we could take a copy of this, jump over to our YAML parser here, and let's take a look at what that looks like in Python format, right? So here we go. Produces a dictionary. Let me just copy that. And then if I jump over it here, instead of using the default Jinja to YAML, I can override that with a shebang syntax. And let's say we want to use the Python renderer. The Python renderer takes a Python function called run, and that function returns a dictionary, basically the exact same dictionary that YAML would give us. So if I save that and run that, then the result is the same as what we've seen before. No changes are necessary, otherwise it's the exact same state run, just represented in a different syntax. So state files are data structure generators. They produce a data structure of salt commands that are run one after the other. And they are specific to the underlying minion, as we've talked about, right? Oftentimes these SLS files contain OS-specific data or role or machine-specific data. The minion downloads the text files that are relevant to its state run from the master, and it parses and runs them right there locally on the minion, so it can use any data that lives on that minion. So those files usually generate data that is tailor-made for that minion that is running those files, like package names and paths, or even which state files are meant for this minion based on its location or its role or its operating system or whatever else, right? And it is syntax agnostic, right? Jinja and YAML are the defaults. But if you don't like Jinja, if you don't like YAML, you just mix and match any one of the other renderer modules, and poof, right? You've got something else. Jinja was chosen because it's very popular. YAML was chosen because it reads well. But use whatever you're comfortable with. In addition to that, salt states can be written either declarative or imperative. And it's entirely up to the author, right? If you want a declarative state syntax, stick with the default YAML. If you want something that's more imperative, go with something like the PyDSL or PyObjects. Right? And these look and read like Python, top down, with statements, all of that. So in this video, we learned about Salt's renderer system and that we should think of salt states as generated data structures. In the next video, we're going to apply that knowledge by generating states with an eye toward reusability. Video 4.2, How to Write Reusable States. In the previous video, we learned that states are data structure generators. In this video, we're going to generate states that are specific to a given platform. We're going to talk about what reusable states are. We're going to learn ways of introspecting the local system to fetch data about that system. We're going to parameterize states, and we're going to do some light conditionals and looping to generate states differently for various platforms. So a state is reusable if you can take the same SLS file and you can run it across a variety of operating systems or distributions or across different environments like production or development or staging. And the way you go about doing that is you parameterize states using external data, meaning you call those state functions with different arguments, with different parameters, right? And the external data that you pull in is data that you get from grains or from execution modules or from shelling out. So the obvious go-to for introspecting the local system is grains. Grains are loaded when Salt starts up. It provides a wealth of information. A lot of that information is stuff that we're probably going to want when we parameterize states anyway, things like OS information or architecture information, that sort of thing. Or we can call out to execution modules. We've got the full library of Salt's execution modules available to us, including command.run, which means sky's the limit. We can do anything we want to the underlying system from Jinja. But there's good reasons not to, right? There's good reasons to limit the scope of those activities to just fetching data, because when you shell out, when you call these functions directly, it bypasses all of the normal mechanisms that we've talked about already in the state system, like dry run mode or the idempotency, where these state modules do pre and post checks. Does anything need to change, yes or no? Instead, if we change the system with one of these calls, we're just calling it directly, and so the system changes, and so it bypasses those. So the best use of Jinja is to fetch data. So let's take a look at what that looks like. Let's parameterize one of our states with some OS-specific values. As you recall, the place that we left our apache.sls file is our package name and our service name had been hard-coded for Ubuntu systems, and so it will not run on Stuart, who is running CentOS. So let's fix that. And we're going to do that with Jinja. So this is our first taste of Jinja, and it looks like this. If salt.grains.get OS family is equal to Debian, then do something. Otherwise, do something else. So the package name on CentOS is httpd. And then we're going to close out that if statement, right? So now what we've got is we've got a little Jinja here on our state. Now what we've got is the exact equivalent of doing a salt star, well, not the star because it's running locally on the minion, so it's the equivalent of salt call. But otherwise it's grains.get OS family. So the end result is the same, it's just the syntax is slightly different because we're calling this function from Jinja instead of from the CLI. But there we go, we've got Debian and Red Hat, and then we can, there we go. And so now we can change the state depending on which minion it happens to be running on. So let's take a look at what that looks like. Let's do a state.show SLS Apache. I'm going to pipe that to less. Let's see what each one of our minions gives us back. Go to Jinja syntax error. Okay. We don't need the closing parenthesis. Let's try that again. There we go. So you can see that the function call that we're making is the same as the function call we're making at the CLI, and the result of that is going to be a string, same as we saw in the CLI, and so then we're comparing the result of that to these strings. All right, so we can see that Jerry gave us Apache 2 back. But if we scroll down a bit, we can see that Stuart gave us HTTPD. So there we go, that worked. So now this state, this one package.installed state, can run on either Ubuntu or CentOS. So that will work. But there's a couple of problems with this. One is intermixing Jinja with the state is a little hard to read, right? Jinja is it's fast, it's a good choice for a lot of reasons, but it's visually noisy. So it's kind of hard to unpack where one ends and where one begins, especially when you've got, some subtle typo like that. It's just really hard to parse that out visually. So it's a good idea to separate the Jinja from the state, and we'll see good ways of doing that in the video after this video. But for now, we'll keep this in here. The other problem is this isn't reusable, right? We've got to do the same thing down here, and that's even more visual noise. And so there's got to be a better way to organize that. So I'll keep this for now, and we'll return to this in the next video and do it the right way. Let's go ahead and copy this to make sure that our state will run. So let's run this on state.sls Apache, and let's run this on both minions. So Stuart should finally pick this up and have Apache installed. You can see that Jerry returned quickly because nothing needed to change. Apache was already on there. No surprise there. Stuart will take just a minute more to run. While he's running, let's talk about light conditionals and looping. So again, when you do light conditionals and looping, it's a good idea to separate the Jinja from the states as much as possible. And I'll show what that looks like. All right, there we go. Stuart is now done. Let's see what we got. Install Apache. The following packages were installed. HTTPD at this version. And it was indeed started and set to start on boot as well. And our index.html page was put in place. Let's double check that that's the right place to put that on CentOS systems. I'm going to jump over to Stuart and let's take a look at our var www html directory. Okay, so it's in there. Let's take a look and see. Let's see, IP header. Stuart is. There we go. Let's jump over to our browser. So as you recall, here is Jerry. There we go. So now Stuart is also running our file, same as Jerry. Okay. Now let's talk about looping. So I've gone to the trouble of creating a mods.sls file so that you don't have to wait for me to type this out. So what this does is this enables mod status and mod info on the Apache server, and it does so in a way that's specific to Ubuntu. So we need to fix that. But you can see what it does is it puts down a file modstatus.conf in the conf available directory, and these are the contents of that file. And then it also does a command.run, and it runs a2nmod status and a2nconf, both of which are Debian things. And then we've got one other flag to command.run, which is creates. So when this runs, this a2nconf, then it creates a conf enabled modstatus.conf. And so this tells command.run that you don't need to run again if this file already exists. Okay? So it copies the conf available to conf enabled. So that's what's going on there if you're not familiar with Debian or Ubuntu isms. Okay, so there's a couple of things, right? One, these two states are nearly identical. Really, the only thing that's different between them is mod status versus mod info. The other one is we've got this command.run, which is only applicable for Ubuntu machines. This does not need to be done on CentOS at all. So let's start to make this state applicable to both operating systems, and let's cut out some of the duplication. This might not be the best use of cutting out that duplication. You might not care about this level of duplication, but we're going to use it as an example either way. So let's do a for loop. So for conf in, and then let's do an array of strings. So status and info. So those are our two modules. Okay, there's our for loop. Let's scroll down here, loop and for. And so what we're going to do is we're going to generate these states based on the values in this for loop. So instead of mod status, we're going to do mod conf. So in Jinja, these braces, these double braces, are how you do a variable lookup. So in this case, the conf variable is this. So this will get expanded out to mod status in the first iteration through the loop, and then mod info in the second. So then we've got this here, mod status, so we'll do the same here, mod conf, and then the location, once again, conf, and then finally the handler, so server status, server info, same thing, conf. Okay, and then we've got this, a2n mod status, conf, a2n conf mod status, conf. And then finally, it's going to create this file mod status. So conf. All right. So with that done, we can now get rid of all of this. Okay. What else to say about that? One thing to keep in mind is when you do this kind of thing in a for loop, the ID, as you'll recall, must be unique across the states, across the entire state tree. And so this ID has to be unique if you put it in a for loop. In our case, it will be. It'll expand to mod status and then mod info, but keep that in mind. That's a common gotcha. And Salt will complain at you if you miss that. Okay, so let's save that out. Actually, let's do one other thing while we're in here. This command.run doesn't need to run on CentOS systems. So let's go ahead and put that inside of a conditional. So if salt .grains.get os family is equal to Debian. Then go ahead and run that. And if it's not, don't run it at all. And we can put in a little vertical white space if we want to make that a little bit more readable. Okay, so now this will not show up on CentOS systems at all. Okay, let's double check our work. Let's see where we're at. So once again, I'm going to do a state.showSLS, and then this one is called mods.sls. So it'll be showSLS mods. Now, we've still got some Ubuntu specific paths in here. We're going to fix that in the follow-up video to this. So let's just run the showSLS to make sure that the data structure that is generated is what we're hoping it is. All right, so Jerry produces mod info with a2n mod, right? And it's got the command, it's got the command run, and it's got the file managed, and it's got mod status, and it's got the command run and the file managed. And Stuart produces, again, mod info with the file.managed and the mod status with the file.managed, and you can see that the command.run is in fact not in that output. So that is exactly what we want. We won't run this one because it's not going to do quite what we want on Stuart, but we'll fix that in the follow-up video. So there is an example of generating salt states using for loops, conditionals, and parameterization. All right, so in this video we expanded on generating states to produce a single SLS file that can generate a state for a variety of platforms. In the next video, we're going to discuss best practices for writing states in a clean, readable, and maintainable way. This is helpful for teams of people that are working on the same state tree and for everyone who needs to keep a state tree up to date for months or years, right? That maintenance cost is a good thing to keep as low as possible. Video 4.3, How to Write Maintainable States. In the previous video, we wrote SLS files that can produce a state tree that'll work across a variety of platforms. In this video, we'll discuss best practices for writing states in a clean, readable, maintainable way. This is helpful for teams of people that have to work on the same state tree, and for anybody who needs to keep a state tree up to date for any length of time. So we'll talk about brief style suggestions. We'll talk about how to separate logic from states. We'll talk about what map files are and how they can help us do that. And then we're going to talk about how to pull the result of a map file into an SLS file that we can use. Then we'll talk about why SLS files should be single purpose and how that helps us kind of mix and match them so they can be used from a variety of contexts. So let's start by talking about style suggestions. We've mentioned before that it's a good idea to use a descriptive state ID that just kind of helps the reader skim a state tree and say, well, this does this and this does this. It's also a good idea to always specify the name parameter. So the state ID in Sol Apache, that just kind of explains what that state is doing or what the states under that ID are doing. And same for Start Apache. Now, the name parameter is a good thing to specify. Now, technically, we could do something like this. We could do package.installed. The problem with this is the ID here, the thing that needs to be unique across the state tree. This is the thing that's going to change between various platforms. And so it's a good idea to get into the habit of specifying name because that's usually the value that's going to change between platforms. And so this will help you kind of future-proof your states. It's also a good idea to comment your states. So like a top-level comment here, manage Apache is a nice thing to add. YAML's very forgiving about vertical white space and new lines. We could do something like explicitly enable to start on boot because we need to manage CentOS as well, right? If you're a Debian shop where this behavior is just implicit in the normal behavior, you might forget to do this if you happen to have a CentOS system or two that you need to mention, and so this might be a nice way to remind future you or other people on your team why this is needed, that sort of thing. So it's a good idea to just put comments in explaining what you're doing and why. Just be careful not to try and comment out Jinja using YAML comments. If you'll recall from the render pipes section, Jinja happens before YAML, and they're completely separate steps. So if you put a YAML comment here, this Jinja will still run. It completely ignores the YAML comment. If you want to comment out YAML, you have to use a Jinja comment, which looks like this. But if you're just using comments for documentation, the YAML style comment is usually good. So let's talk about separating logic from states. It's a nice thing to be able to only reference a Jinja variable in a state rather than intermixing this logic that we've talked about before. So a quick way to go about doing that is maybe we just move this conditional up a bit, right? So let's do something like this. Now, instead of putting YAML inline within the conditional, let's set a variable instead. Let's do set Apache package equal to Apache2 and HTTPD. So now that we've got this Apache package variable, we can get rid of this conditional altogether, and we can just reference our variable here. So suddenly this state becomes a lot more readable, and we can glance at the state tree with that in place and just kind of get a quick sense of what it's doing. We can also reuse that variable in multiple places. Package doesn't quite make sense here, but you get the idea, right? We can reuse that variable in multiple places, and so instantly it becomes more readable. Map files will help us get a little bit farther in this direction, which we'll see in a moment. It's a good idea to avoid more than 2 levels of loops or conditionals for the reason that we've talked about over and over now, which is Jinja is just a little syntax heavy, and so it's hard to unpack that syntax from the Salt syntax. And so if you can separate them out or use as few of them as possible, the more reusable your states will be. As a rule of thumb, the more readable it is, the more maintainable it will be. Oftentimes people will try to use Jinja to calculate values or build up lists, in a for loop or something like that. Jinja is a logic-light templating language by design. It just doesn't have a lot of constructs to do calculations or data structure, munging, that sort of thing. And so avoid doing that in Jinja because you'll just be going against the grain. It's a good idea to put custom logic inside of a custom execution module. This is a really easy thing to do. So for example, if you've got something that, you need to do to a data structure, you need a unique list of things, or, you need to prepare some data for use within an SLS file, it's an easy thing to be able to just make a directory, serve salt underscore modules, and then from there you can do you can put a Python file in there, so myutil.py, and that file is just a regular Python module that contains regular Python functions. So you could do, for example, something, right? And really the only constraint is whatever this function returns has to be JSON serializable. So something happened, right? So it's just that easy. And then you can sync it down to your minions, salt star, salt util, sync modules. And now all of our minions have this myutil, and so we can call it salt star myutil something. It's just that easy. If you want to cross-call salt modules, you could do something like salt command.run date, right? Exactly as the same that we did in Jinja or on the CLI, just again a slightly different syntax because we're calling it from Python this time, but the return is the same. So this is us calling out to the date command, right? So now if we sync that down and run it, just that easy. And since we can call it from the CLI, we can call it from Jinja as well. And so that's a nice way to keep logic out of Jinja. Or, as we talked about in the renderer section, you can just write your SLS file in Jinja using, say, the PyRenderer. All right, so let's talk about map files. What a map file is it's a convention. It's a single location to put a bunch of reusable values. It's a good way to avoid conditionals while allowing sane defaults and overrides of those defaults. It's a good place to put platform-specific details, application defaults, environment-specific values. And map files are useful in both states and in pillar, which we'll talk about. So what that looks like is we've got this apache.sls file, and we're building up this this construct here to produce this Apache package variable. Well, what a map file is it's just a dictionary that allows you to look up a subset of that dictionary. So let's make a dictionary. We'll call it lookup. And we're going to key this dictionary based on what we are pulling out of this conditional, what we're looking up in this conditional. So in this case, it's the OS family grain. And then I'm going to do subdictionaries. And then from here on out, we can put arbitrary data within this subdictionary. So we can do package Apache 2. And service. Right. We can put whatever we want in this lookup dictionary. And now we just need to pull a value out of it so that we can use it like we are down here. So to do that, we're just going to look a value up in this dictionary. We're going to set a new variable. We'll call it Apache. And we're going to set that to lookup. And it's just a dictionary, so we're going to pull a value out of it. And the value that we're going to pull out of it is the OS family grain that we were using in our conditional. And we've already seen how to pull that out. It is salt.grains.get OS family. Right? And so now the result of this Apache variable is set to either this inner dictionary or this inner dictionary, depending on where this SLS file is rendered. And then we can say switch this out. So instead of Apache underscore package, it'll be Apache dot. That dot is just a Jinja shorthand for looking values up in a dictionary. We could certainly go the longhand format if we wanted to like that. But in this case, we don't need to. So there we go. That's a lookup file. It's really that simple. And the nice thing about lookup files is it gives you one place to put these values. So if we wanted to add, support for FreeBSD, for example, all we have to do is add a new dictionary entry with the right values, and poof, our state is already written to work with FreeBSD. So adding support for various operating systems is a lot easier that way as well. So since this is a common pattern, we've got a few constructs in Salt that allow us to do that a little bit more succinctly. Basically, what a map file is doing is it's a dictionary, and then you're filtering data out of that. And it's also a nice thing to be able to specify defaults or overrides, right? So this is a dictionary, so we can say override values in that dictionary however we want just by modifying that dictionary. Say we want to say these are all our defaults, but we've got a Snowflake server, for example, that we need to override. We could just override that value in here somehow. But Salt has a function in the grains execution module that'll help us do this. It's called filter by. And what that looks like is instead of manually pulling this value out of the lookup dictionary, we're going to do this instead. We're going to do Apache is equal to salt.grains.filter by, and then we're going to pass in our dictionary here. So that does the exact same thing as this. It defaults to using the OS family grain, but we can use a different grain if we want to. Okay, so it's just that easy. And oftentimes what people will do is they'll just avoid the extra variable here. And instead of lookup, they'll just put the dictionary in line. Okay, and there we go. So let's test this to make sure that our lookup dictionary is indeed working. Salt star state.show SLS Apache. Okay, there we go. So we can see that Stuart is still getting HTTPD and Jerry is still getting Apache 2. So our lookup dictionary is indeed working. Another thing that's nice about map files like this is we don't care where this dictionary comes from. Right now we've got it embedded within the SLS file, but there's no reason that we can't pull this out of, say, some arbitrary place like a YAML file or a JSON file or a database call. It doesn't matter, right? We can pull this out of wherever we want because it's just a dictionary. We're filtering on it after the fact. So let's go ahead and pull up the documentation for the filter by module. So it's an execution module, so M for execution modules, and it's the grains execution module. And in here there is a function called filter by. So you can see there's a variety of arguments here that might be of use. You can change the grain that's used to look up the other values. You can specify another dictionary to merge on top of this dictionary. So the map file becomes just the defaults, and then this dictionary becomes any of the overrides that you might want. Default lets you specify, if a key in this dictionary doesn't match, go ahead and use this one as the default. There's also a corresponding filter by function in the match module, which we talked about, which allows you to, say, make a lookup table based on compound command or that sort of thing using Salt's matching semantics. If you're on a fairly new version of Salt, there's also an SLS util execution module that contains an update and merge function for updating or merging dictionaries together. And there's an SLS util render function that allows you to write map files in any syntax that you want. So you can write them in Python and pull them into Jinja, or you can write them in Jinja and pull them into Python. It doesn't matter. So it's a good idea to write single-purpose SLS files. Each SLS file should do one thing and do it well. It should be self-contained, and the reason for this is this allows mixing and matching in how this SLS file is used. So if you've got an Apache SLS file that's doing as little as possible, in this case we're installing Apache and starting the service, right? But we're also putting the welcome page in place. And we might not want to do those two things together, right? We might want to be able to call out to a file that just does the basics of setting up Apache and getting it running. We might want to put the welcome page in place as a separate action, right? That allows us to run this separately from these. And as we start to glue SLS files together, as you'll see in the next section, that becomes a nice thing to be able to do. It also allows us to use this SLS file from a variety of places, and we'll talk about that in just a moment. So since we've got a bit of a few Apache files, I think it's a good time to finally group these into a subdirectory. Generally speaking, you should group related SLS files together. So I'm going to move mods.sls into the Apache subdirectory, and I'm going to move the apache.sls file into the Apache subdirectory, except I'm going to rename it to init.sls. So this will allow me to still run state.sls Apache. This is sort of a Python idea where an init file takes the kind of place of a module, right? So it takes the place of the default file within this directory. So I can just specify the directory. And now that that's in, now that both of those are in a subdirectory, I can reference them with state.sls Apache to get the init and state.sls apache.mods to get the mods file. Okay. So now that those are in there, let's break these out. So let's make a serve salt apache welcome.sls, right? And for that, we're going to go ahead and move our welcome page in here. So now we can deploy that separately. And we should probably also move our map file out into its own file so that we can use it from multiple places. So let's go ahead and create a serve salt apache map.sls. Okay. And so now we can move this Jinja variable in here. So now that we've got that in its own file, we can then import it from here. And that looks like from apache map.sls import, and what do we call that variable? Apache import Apache with context. Now the with context is interesting. This is a Jinja thing, and it's basically saying render this map.sls file with the same context variables that I'm being rendered with. So that allows us to get access to this salt variable. So keep in mind that's required. All right, let's make sure that I didn't fat finger anything, and let's run the show SLS again. And there we go, still working. Apache 2 and HTTPD. So now our map file is broken out into its own thing, and our SLS file is small and single purpose so that we can call it individually. Now the places that we might want to call that from are, we can call it with state.sls as a standalone thing like we've been doing, or we can pull it into a top file, which we'll talk about, or we can call it from orchestrate, which we'll talk about, or we can call it from the reactor, which we'll talk about, and you can call it in masterless mode as well. So it's a nice thing to be able to call this one SLS file from all of these locations and not have to worry about it pulling in other behavior. You know, we might want to manage the Apache server without pulling in that welcome page as we discussed. And I'll talk about this a little bit more in the next section. All right, so in this video we learned how to keep our states readable and thus maintainable. In the next video we'll learn some tips for working with Jinja and YAML, as well as a few things to watch out for. Video 4.4, YAML and Jinja best practices and gotchas. In the previous video we learned about how to write maintainable states. In this video we're going to shift gears a bit and talk about some of the pitfalls of both Jinja and YAML, plus a couple tips. We'll talk about YAML idiosyncrasies and multi-line strings. We'll talk about how to write Jinja in a readable and maintainable way, and how to use Jinja to create variables, fetch data from external files, and fetch external data using function calls. So one of the things that's interesting about YAML is the specification is really quite large. Unlike JSON, which is pretty small and narrowly scoped, YAML can do quite a lot of stuff. In Salt, we're using just a small subset of it. And one of the things that's kind of a common gotcha in YAML is typecasting. YAML will cast things that look like certain types to other types. So for example, if you have something like the word on, that gets cast to a Boolean, right? Off. Or if you have something like true, on, and yes, right? All of those get cast to Booleans. So if you're templating something like an Nginx config and you need to write the word on, you have to quote that to prevent YAML from casting that to a Boolean for you. YAML will also cast things that look like date times, and it does some interesting things with numbers from time to time. So when in doubt, quote, right? When in doubt, wrap the thing that you're typing in quotes and just be explicit about it. Another common tripping point with YAML is indentation. This comes up somewhat frequently in Salt when you've got a nested dictionary, and that dictionary needs an additional level of indentation, and that's not quite obvious. So for example, say you're templating file.manage, so you've got, my file, and it's going through the file.manage state, right? You've got, temp some file.txt kind of a thing. And you're running that through the Jinja templating language. And so you're passing in context, additional context variables. This is going to be a dictionary of things. And so if I don't indent this correctly, so, say I want to do foo equals foo and bar equals bar, right? So I want this context dictionary to be a dictionary of additional values that get passed to my template, right? I've got to indent this inner dictionary to past the C in context. If I don't do that, it is valid YAML. And so it's a common tripping point because it won't throw any syntax errors. But as you can see, that is not the result that we want. Context should be a dictionary, but rather context and foo and bar are siblings instead of children of context. So keep an eye out for that, and subdictionaries need that additional level of indentation. There's a whole list of YAML idiosyncrasies in the Salt documentation in a document called YAML idiosyncrasies. And this is well worth reading because YAML is used so heavily, especially in Salt states, it's likely that you're going to run into something that doesn't do quite what you were expecting at some point. And so just give it a quick look whenever you have a few minutes and see what tripping points there are for YAML. Now let's talk about YAML multi-line strings. We've mentioned them and demoed them before, but it's worth pointing out that they're really, really useful in a variety of places, especially in states. So for example, command run, right? Command run is one of those things that should almost always be used with a YAML multi-line string because it avoids so many quoting problems. So the way this goes is you end the line with a pipe character, and then you indent to past the N in name, and then for as long as you've got consistent indentation, YAML will treat everything in there as a multi-line string. So as you can see in this example, we've got two different kinds of quotes. We've got single quotes and we've got double quotes. And we can just write out the shell command without worrying about nested quoting or that sort of thing like we would normally worry about in, say, JSON or typing in at the CLI, because all of this is encapsulated in a multi-line string in YAML, so we can just type out the shell command. We've talked about this before in the previous video, but the key to readable Jinja is to not use too much Jinja. Set variables, separate those variables from the Salt states, pull data out of external files like we did with map files. You can do that with JSON files or YAML files. Sky's the limit. And move complex logic, like we talked about, into custom execution modules. They're really easy to write, they're really easy to sync down, and they can do a lot of stuff, and then you can just benefit from those by pulling the result of that into a variable in Jinja and using it right there. Use Jinja to call out to external sources. Set variables, read external files, call external functions, fetch external data. Don't try to do too much in Jinja. As a rule of thumb, if you're having a hard time reading the Jinja, then you're going to have a hard time maintaining it. So in this video, we learned what to do and what not to do with Jinja, plus some YAML tips and tricks. In the next video, we're going to continue writing Jinja in YAML in the context of Pillar. Video 4.5, Configure States using Pillar. In the previous video, we learned the do's and don'ts for Jinja and YAML. In this video, we're going to use more Jinja and YAML to create minion-specific data. So we're going to talk about what Pillar is, how it's used, what it's useful for. We're going to talk about the pros and cons of storing data on the master versus storing data on the minion. We're going to talk about passing in Pillar data at the CLI to override values. We're going to talk about using Pillar for secure data and security pitfalls to watch out for. We're going to talk about how to create map files inside of Pillar. And finally, we're going to talk about how to set up certain preconditions so that Pillar values are present at the top of a state run, otherwise the state run will fail. So Pillar is arbitrary minion-specific data. That's really it. It's data that gets sent to this minion or this minion or this minion. Now those minions could get the same Pillar data, but it is delivered to them individually and it is generated for them individually. So that means that Pillar can be useful for secure data. If you want minion A to have an SSH private key, for example, you would send that private key to that one minion and that one minion only. If you wanted all of your web servers to have access to the database password so that they could connect to the database machines when they first started up, then you would send that to just those machines and no others. So that's why Pillar is useful for secure data. In addition to that, Pillar is a good way to get data into Salt from external places. And that is done by yet another pluggable module interface in Salt called external Pillar modules. So if we jump to the module index and go down to P for Pillar, you can see that these are the modules that Salt ships with, and Salt can pull data out of these data stores and into Pillar and then distribute that to minions from there. So sky's the limit, right? MySQL, Mongo, Hiera, if you're coming from Puppet. You can query web services that can return JSON, that sort of thing. So really open-ended, and it pulls data out of these data stores and then distributes that to the various minions. Plus, these are also easy to write if there's something that's not covered by Salt already. So each minion will request its Pillar from the master. Let's see what that looks like, and then we'll talk about the pros and cons of storing data on the master versus storing data on the minion. So the way we're going to do this is we're going to create a new directory that will not exist by default, which is /serve/Pillar. And then in here, we're going to put SLS files. Now these SLS files go through Jinja and YAML as normal, same as SLS files in states. The difference is these SLS files don't have a predefined structure. They can contain arbitrary data structures. And if you want to use any of the other renderer modules, like we talked about in the renderer section, you can do that as well. So you can write these in, say, Python instead of Jinja and YAML. So what I'm going to do is I'm going to create a Pillar file called name.sls. And in name, I'm going to make a value called name, and I'm going to put world is the value. We can do anything we want in here. I'm going to set up one key for name. Now, one of the things we haven't seen yet is a top file. Pillar must have a top file. And what a top file is it's something that says the following minions get the following SLS files. States can use them as well. We haven't talked about them yet, and we will in the next section. So let's just briefly cover top files now so that we can use it with Pillar. So I'm going to create a new file, and it's going to be servepillar-top.sls. This is just a special file name that Salt looks for. And in here, the top file starts with an environment, and you can configure other possible environments in the master config under the Pillar root setting, but we're just going to stick with the default of base. And then what comes after that is a Salt target. Now this is the exact same that you're familiar with from other places in Salt, except this time it's expressed in YAML. And then after that is a list of SLS files that should apply to that target. So let's put our name file in there. So now what this is saying is it's saying all minions that match this target get the name.sls. Okay? So what we're going to do is we're going to run a salt util refresh Pillar. This will cause each minion to request its Pillar of the master. There we go. So the way this works is each minion, when this function is run, each minion will send a request on the private channel to the master saying, hey, can I have my latest pillar? The master then compiles pillar for that one requesting minion. And it does so with the local cache that lives on the master of that minion's grains, as well as the minion's ID, and also a copy of the minion's configuration file. And then it generates pillar, and it consults any of those values from those data sources if it needs to. And then it returns over that wire, over that private channel, a dictionary of those pillar values, of those rendered pillar values. So the minion never gets access to these SLS files, it just gets access to the resulting dictionary. All of those SLS files are merged together into one big dictionary, and then anything that comes in from external pillar, again, merged into that big dictionary, not dissimilar from grains. So the master compiles this once for each minion, and then each minion keeps its own copy of pillar in memory. So pillar is not appropriate for, say, large binary files because it's kept in memory. So keep that in mind. But pillar never touches disk on the minions. Okay. So we've sent down this pillar value to our minions, and if we wanted to, say, send different values to different minions, one of the things we could do is we could, say, set up targets here to send different SLS files to different minions. So we could do, Stuart gets, name 1 and Jerry gets name 2 kind of a thing. But that's not really very scalable. Plus, like SLS files in states, we can use Jinja to generate these SLS files, these pillar SLS files, and we can do that per minion. So, for example, we could do something like if grains.id is equal to Jerry, right? Then it should be Jerry's world. Otherwise, Stuart's world. Close out our if tag, refresh pillar, and there we go. So Stuart's world. Okay. So keep that in mind, that pillar files have all of the same generation kind of semantics as SLS files. All right. With all of that in place, you might be wondering whether or not it's best to store data on the master in pillar or to store data on a minion, say in grains or something like that. Another common pattern is to store data in an SLS file that gets distributed down to a minion, like, for example, the map file that we made in a previous video. So really the determination is where is the best place to store and organize and manage that data over time. If it's secure data, you probably just want it in one place, maybe on the master, right? If it's not secure data, if it's verbose, or if it's just defaults, then something like the map file in an SLS file or in the file roots directory that gets transferred down to the minion might be a better choice because that keeps it out of memory on the minion, but still gives the minion access to it. Or grains is another common place to go. With grains, the difference is, do you want to, say, send commands down to your minions to set values or update values or query values, or do you just want to store that centrally in one place on the master? There's no right or wrong answer. It's just what is best for your app, your organization, and how you want to manage that data over time. So you can pass in pillar data at the CLI, and that can override data that you, say, put into an SLS file here. So for example, we've got this name parameter. We could do something like this. Now the state, there's a few functions in the state module, take a keyword argument called pillar. Now this is similar to test equals true, right? It is specific to these state functions and it's not just any execution module. But so we can pass in data or pillar data here at the CLI. And one of the things that Salt does, if you recall from the very first section, is we can put in YAML in this string here, and Salt will parse that as YAML. So we can pass in complex data structures like name colon override, right? And then as long as the thing in between these single quotes is valid YAML, then that should work just fine. Okay, so there we go. That was something that we could use to override. So this is useful for, say, putting arguments into a state run. Say you've got an SLS file that deploys your application, your web application, and it defaults to, say deploying from the master branch or something like that, you could pass in pillar data here at the CLI to say, no, I want to deploy this version or that version, right? And so that's useful for that pattern. And a variety of other things. Just keep in mind that when this happens, this pillar keyword argument is part of the publish that goes out to all minions. So the salt master sends out the publish, and so even though it's using the pillar keyword argument, that publish is received by all minions. So you don't want to put sensitive data in this keyword argument. Just overrides for non-sensitive data. Anything sensitive has to be kept in an SLS file, and you have to do that refresh pillar dance to get it down onto the minion. Let's see. Yeah, not private. Keep that in mind. So secure data means, as we talked about, any data that's specific to a minion that other minions should not have, or other groups of minions should not have. Avoid tying any data that lives on the minion to data that should be secure on the master. Let me show you what I mean by that. So in our top file here, we're matching with a compound command. So like one of the things we could do is we could match on a grain. We could do a grain at, if they've got the web role, right? Go ahead and give them the database password pillar, right? So you could do that. The problem is if somebody ever compromises a minion, they'll have root access on that minion, and they can change the grains on that minion. So then when they go to refresh their pillar, the salt master will happily give them the pillar for, a web role. If it's, some low impact customer service machine or something that changes its role to the web role, poof, he's got the database password. So avoid tying master side security pillar, namely the top file, to minion side data, just in case you have a minion that gets compromised. The best way to do this pattern that we're kind of typing out here on the left is to key that off of the minion ID. And we'll see a good way to do that in a scalable way when we talk about map files here in just a moment. Map files, as we talked about in states, are just as useful in pillar. And there's a few execution modules that can help us do that. One is in the match module. So if we jump up here to the module index, this is, of course, an execution module, the match execution module. And like the grains execution module, the match module has the same filter by function in it, the same concept, where you're taking a dictionary and you're filtering on it. So this is where you can, say, very easily dole out roles via pillar instead of grains. Or to keep a list of minion IDs that you want to say whitelist, and then give out the database password to those. So this filter by filters this dictionary based on the minion's ID. So if the minion's ID happens to start with web star, and the minion ID cannot be changed by the master, as you recall, that's used for Salt's keys and Salt's authentication. So if a compromised minion changes its minion ID, then poof, the attacker has just de-authenticated himself with the Salt master. So you can rely on the minion ID. And that's what we're doing here to set roles, but we could just as well set the database password. We could send the database password down to the web machines, that sort of thing. You can also keep, say, a comma-separated list or an array of minion IDs if they don't have this common name, for example. And you could do a lookup based on that using Jinja. So you could say, if the minion ID is in this whitelist of approved minions, then go ahead and send them the database password, that sort of thing. So that's a way to do it if you don't have minion IDs that all have a common prefix. So let's fix up the state that we had been writing with a map file to make that a little bit more clean. So instead of this nested conditional, we could do something like this. Set lookup is equal to our dictionary once again, right? Jerry, kids, Jerry's world. I need double quotes there, don't I? Stuart's world. Okay, so there's our lookup table, and then we're going to pull a value out of that. So we could do something like set name is equal to lookup, and then again it's just a dictionary lookup. And for this we're going to use grains.id to grab the minion ID. Okay, so now we've got a Jinja variable with the right name, the value for whatever minion we happen to be on. And so now we need to make this Jinja variable available to YAML, and we do that in the normal way, like this. Okay. One of the things to keep in mind is when you're doing this, you're doing templating within templating, right? So on the master here, we're doing templating where we're taking Jinja, we're parsing it through YAML to produce a data structure. And then we're sending those values down to the minion to again be used in a different template on the minion via the states. So keep that kind of dual templating in mind. You know, first it's templated on the master, the values are sent down to the minion, and then it's templated there. There's you know, occasionally some interesting kinds of surprises where you send down a Boolean value or something like that, and then you forget to quote it in the state on the minion, and then that Boolean value gets cast to YAML or something like that. One of the ways I like to avoid doing that is, since JSON is a subset of YAML, I like to just cast values to JSON here. So the result of this is going to be a JSON string, so it's going to have double quotes around it. So we're going to avoid any escaping problems that, you know, I don't think we'd run into any here, but we might with other values, you know, since we've got multiple words or that sort of thing, especially when you've got data structures. If name happens to be a data structure instead of just a string, casting that to JSON to ensure that there's no kind of quoting surprises and that sort of thing is always just kind of a nice safeguard. So with that in place, let's refresh Pillar once again. Run our Apache welcome. Okay. And there we are. We're back to the values we had before, but this time using a lookup table. Okay. Finally, let's talk about preconditions. So there's an interesting function an interesting state function in the test module that allows us to put a requirement that certain pillar values are available, which is nice since we're using a pillar value here in our state. So let's pull that up. It's a state module, so S for states, and it is the test state module. There we go. So the test state module is useful for testing, obviously. So there's a lot of functions in here that say display, they can output state runs with successes or failures or changes or no changes, that sort of thing. But one of the functions in here is called check pillar. And what check pillar allows us to do is it looks for the presence of certain pillar values, and it fails if they're not there, right? So you can say, I want to make sure the foo value is present, and I want to make sure that the bar value is an integer, that sort of thing. So let's use that in our state to make sure that that a value is present. So that'll look like this: salt Apache welcome. Okay. So we could use a default value here, but we pulled that out. So say we want to ensure that the user always passes this in. We're going to check pillar values, and for this we're going to run this. We're going to specify our test module and then the check pillar function. Okay, and we're going to say I want the name argument is again accepted since this is a state module, and as you recall, all state modules take a name value, but in this case the name value is ignored. So again, read the docs for each one of these state functions to see what it does. So we're going to look for present. We're going to say present, and we want name to be present. Okay, just like that. So with that in place, if for whatever reason we don't send name down, let's change this real quick to something we know is going to fail. So if we run that, now our state failed, right? Name X is missing, but this state still ran, and that's not what we want. We want the whole run to fail if that value is not present. And so we're going to use a new flag that we haven't seen before on states called fail hard, and we're going to set that to true. Sorry, no underscore. Fail hard, true. So what this does is this instructs Salt's state system to say, if this state fails, fail the entire run. And if you wanted to set this value globally, you could do that. You could put this in the minion config and then it would fail globally. So now, if we run this again, you can see that failed, and it didn't run the other state. It bailed out at that point. And so that's a nice thing to say, ensure that certain pillar values are present. So now if we switch that to an actual pillar value that we know is there we go. And it does exactly what we want with that checking in place. So that's a nice thing to be able to rely on. All right, in this video, we learned about pillar and how to use pillar to parameterize states and to send private data down to minions. In the next video, we're going to talk about salt formulas, which make use of everything we've talked about in this section thus far. Video 4.6, Learn Salt Formulas. In the previous video, we learned about pillar data. In this video, we'll see one way that pillar data can be applied to a state tree by exploring public salt formulas. We'll talk about what formulas are. We'll see that they are essentially best practices in action. We'll talk about the salt formulas GitHub organization, and then finally we'll talk about how to install the formula. So formulas are reusable, maintainable salt states, exactly as we've talked about in the previous two videos. Quick point of terminology. A state is a function call. So many states live inside of an SLS file. And you glue SLS files together to form a state tree. Now, if you've got a bunch of SLS files that all center around a single theme, like they live in a common subdirectory, for example, then you can call those a salt formula. So you could have, say, a bunch of SLS files that all manage Apache, and that would be the Apache formula. Oftentimes, formulas are publicly available, and oftentimes they're configured using pillar data in the way that we saw in the previous video with map files. Salt formulas live in an organization on GitHub called SaltStack Formulas. And there's a link to the SALT documentation from that organization page, as well as each one of the formula organizations that talk about the best practices that we talked about in the previous two videos. So if you come to the SaltStack Formulas organization, you can see that there's a link to the docs here. If you pull that up, then you can see that there's documentation here about how to install formulas and use them. But if you scroll down to the middle, there's recommendations on writing formulas, style guides, use comments, what you should and should not do with Jinja, how you should use map files, that sort of thing. And so if you want a refresher, or if you want a little bit more detail than we talked about in the previous two videos on map files, along with a bunch of more real-world examples, then come to these docs and definitely give them a look. So each formula lives in its own repository, and this organization is maintained by the community. So there's a contributors team that anybody can be on, and so if you're interested in contributing and working on formula repositories, just reach out to somebody on the SaltStack core team, and we'll get you invited. Each formula is a separate repository, and the reason for that is the directory structure is intended for direct use as either the file roots configuration entry or with getfs, which we'll talk about next. In both cases, you just clone the repository or automatically clone the repository using getfs, and the directory structure just puts everything where it needs to go by default. There's two good ways to install a salt formula. One is to clone the repository locally onto the master, and the other one is to set up a file server backend. We haven't talked about file server backends yet, so let's do that real quick. If you jump to the module index and you jump down to F, you can see that there is a module type called file server. These are the modules that ship with Salt. What a file server module is it's a module who takes files from some place and makes them available on the Salt master so that they can be used with the CP module that we've talked about before to transfer files from the master to the minions over that existing encrypted connection that Salt provides. So you can see that we can pull files out of Azure or S3, or we can pull files out of version control using Git, Mercurial, or Subversion. One other note, which is if you have the workflow of wanting to transfer a file from one minion up to the master so that it can be redistributed to other minions, the minionfs backend makes that workflow a little bit more smooth. This is, for example, useful for a minion who is a build server. And when a build is finished, that build gets pushed up to the master, so the master then can deploy that out to the application servers. The roots backend is the default file server backend that pulls files out of the file system there on the master, the file roots file system. getfs is by far the most common file server backend, especially for formulas because all of the SaltStack formulas live in Git repositories. It's a good idea to avoid pulling from the upstream repository directly. The reason for that is getfs automatically pulls down the latest copy of whatever branch you've told it to look at on a regular interval. And so you're going to want to make sure that it's pulling from a source that doesn't change until you expect it to change. So the way you install a salt formula is you edit the master config, and then of course when you edit the master config, you must restart the other salt master daemon. And you edit the master config for either file roots or for getfs. Let's take a look at both real quick. So if we edit the master config, one of the settings is called file roots. Now this is one of the default settings in Salt, and as you can see, we've been using file roots because it defaults to the serve salt directory. That's where that default comes from. But this is a list of directories. So say like you were to create a directory to hold a bunch of formulas, you could create that here. And then the structure of each formula repository is such that you can say clone the Apache and memcached and whatever else formula into this directory directly, and then just include them in this list. So you can say Apache formula or memcached formula, that sort of thing. And then Salt will just do the right thing. The other way is for to use getfs, and for that we're going to use a file server backend. So if we do a quick search for the file server backend, you can see that that is a default setting, and the setting defaults to just roots. So it only pulls files out of the directory on the master. But if we wanted to use multiple file server backends, we could then say uncomment this, and then we could say use both git and file roots. Now, if we wanted to use git, then we need to install a module on the master that allows us to work with Git repositories from Python. That library on CentOS machines lives inside of the EPEL repository. I've gone ahead and installed that repository already so that we don't have to wait for it in this video. So install EPEL if you haven't already, and then you can yum install Git Python. If you're on an Ubuntu system, that package name is python-git. I would invite you to read the documentation on getfs, because GitPython is one possible library of multiple libraries. Each of them have different pros and cons with authentication or other things like that. And so definitely give this a look to make sure that GitPython is the best one for you. But that's what we'll be using in this video. Now that GetFS is installed, we can then make use of it in our file server backend setting here. So then we need to configure GetFS. To do that, we're going to search for a setting called GetFS remotes. Okay, and GetFS remotes is again a list of things, and those things in this case are Git repositories. So then we can uncomment this, for example, and then everything that we list in here will get pulled in. So let's pull in the memcached formula. To do that, I'm going to grab the URL to that repository, and then I'm just going to go ahead and paste it in here. Okay, and I'm going to save my salt master config, and once that's saved, then I'm going to restart my salt master. Anytime you edit the master config, you have to restart the salt master. Systemctl salt, let's see, restart salt master. Okay, there we go. So now the salt master should see that configuration and should pull our memcached formula into a local cache directory, so that if GitHub ever goes down, for example, not that GitHub ever goes down, of course, but should such a thing happen, we've got a local copy of it here on the master, so the master can still deploy out to minions. Let's see if it worked. And we're going to see if it worked by asking one of our salt minions which files it can get from the master. So let's do a salt. Let's limit this to Jerry. And we're going to run a module that we've seen before, the CP module. And we're going to call list master. So this is asking Jerry to ask the master for all of the files in its file roots. Okay, there we go. So you can see we've got our Apache files that we put in before, but now we've got a bunch of memcached files as well. Another file, or another function inside of the CP module, which is quite useful, is list states. That just shows you the SLS files that live inside of file roots. There you go. And bonus, they're in the format that you would need to supply to, say, running state.sls. All right. In this video, we learned what formulas are and how to use them. In the next video, we're going to wrap up this section with some debugging tips, specifically for Jinja. Video 4.7, Debug Jinja. In the previous video, we learned about salt formulas. In this video, we'll end this section with some tips on how to debug Jinja. We're going to talk about how to use debug logging to see the post-render output. We're going to talk about how to see what context variables are available to Jinja. And then finally, we're going to talk about a form of print lining that uses file.managed or command.run. So we've seen this before, but it's worth revisiting that you can see the rendered output that Jinja produces by running show SLS or state.sls with the -l debug flag. So for example, if we were to jump to one of our minions, so I'm going to jump over to Jerry, and from here I'm going to run salt call state.show SLS Apache. Now this is going to show me the data structure that that SLS file produces. It's going to do all of the normal file transfers and that sort of thing that we've talked about. But if I run it with debug logging instead, then we get a bunch more output. And so if we go through some of this output, we can see some stuff that's useful for debugging Jinja. Namely, we can see where the file comes from. We can see that it tried to look for apache.sls in the base environment, and then it fell back to looking for it in apache init.sls. We can see that it already had the latest version of it in the cache on the master, so it didn't need to transfer the file, so it did the checksumming from the master. We can see that it then compiled the template, starting with Jinja. Now, this is interesting because it allows us to see how long it takes the file to be rendered. So time in seconds to render using the Jinja render, and there's going to be another one of these for YAML because it's run through both, as you recall. And then this is the most important part for debugging. Rendered data from file, right? So there's the file that we're interested in, and here's the actual rendered data that we're interested in. Meaning this has already resolved all of the variables in our map.jinja. And so we can see the result of this after processing all of that Jinja. And so if we want to see what the Jinja produces before we hand it off to the YAML parser, then this is the best way to do that. So whatever this produces, as you recall, has to be valid YAML because that's the next step. And so that's a nice way to make sure that Jinja is doing what you think it is. And then, of course, continue that for the result of the YAML parsing as well. You can also see what context variables are available to Jinja using this function. Now let's pull up the Jinja docs. What a context variable is Jinja is a templating language. And so you've got a template that's stored on disk or something like that, and then you render that template using variables that are then made available to that rendering process. So if we start from the module index and we jump down to renderers, we can jump to the Jinja renderer, and that has quite a few docs on things that are available to Jinja, customizations, additional imports, that sort of thing. And so it's a good document to read through. So if we create an SLS file, serve salt show context.sls, we can call that function in here. Now, this is not going to produce a valid salt state, show full context, but it's going to be good enough. Now, it's going to be good enough to see the context. Now, the context dictionary is a dictionary, and it's a large dictionary, so we're just going to want to output the keys to keep that nice and readable here at the terminal. So I'm going to save that out. And then now what I'm going to do is I'm going to call this on Jerry, state.show SLS, and then I named this show context. And there we go. So again, it failed, but what we got was what we were hoping to, the variables that are available in context. So we can see that pillar and grains, there we go, grains, are available, as is the salt dictionary with all of the execution module functions, the environment that it was running as, the salt minion opts, which is the minion configuration file after it's been pulled into an in-memory dictionary, that sort of thing. So if ever you're, say, debugging templating and you're making new context variables available, maybe via file.managed or something like this, this is a nice way to output the available context to make sure that what you're looking for is actually in there. And last is print lining. So print lining is putting a bunch of print statements into your code. So the equivalent of that in Salt is using something like command.run with echo or file.managed to actually output the result of some kind of Jinja variable or something like that. And this is a nice, just kind of lightweight, easy way to go. It's a little verbose, and print lining should be avoided when possible, but sometimes it's just a nice fallback to output something. And so for that, you just use file.managed. You can use the contents argument that we've seen before with a multi-line string, and you can output Jinja variables directly there. Or you can, say, use the template Jinja flag to file.managed to actually run a file through the Jinja parser and see what the result of that compilation is, since that's kind of templating within templating. And then if you're going to, say, output a string content like this, it's a good idea to cast any Jinja variables to a string using JSON or YAML and serialize them thusly. Simple, but it can be a nice way to debug certain things. Okay, in this video we learned some tips for working with Jinja. In the next section, we're going to continue our dive into Salt's state system, and we're going to build up a complex state tree. Section 5. Complex State Trees. In the previous section, we did a deep dive on most of Salt's state system. This section will complete our understanding of states by building a complex state tree that spans many files. In this section, we're going to take a look at how to build a state tree by gluing SLS files together using top files or includes and other techniques that we'll see. As we will recall, Salt states always executed in deterministic order, so we're going to talk about how to define, enforce, and debug that execution order. We're going to talk about how to do conditional and branching logic during a state run using onFail and onChanges. We're going to talk about how to debug a state run from top to bottom. We're going to talk about how to share data between systems using SaltMine, because that data is very useful to reference from Salt states. And then finally, we're going to talk about Salt Orchestrate, which can manage complex multi-system state runs. Video 5.1. Glue SLS files together. In the previous section, we talked about the basics of Salt's state system and about renderer modules, and we talked about the peculiarities of YAML and Jinja. But we didn't run any state trees that spanned multiple SLS files. So in this video, we're going to start to explore complex multi-file state trees. We're going to start by talking about how to glue SLS files together using include statements, and then we're going to do that using top files. And then we're going to talk about the differences between running state.highstate versus state.SLS and why you might want to do one versus the other. And then we're going to talk about the differences between running state.highstate versus state.SLS and why you might want to do one versus the other. So let's start by reviewing our state tree. As you recall, the way we left things is we had a serve salt Apache directory. And in there, we had an SLS file that installed Apache and started the service. We had one that put some configuration files in place. And then we had one that put an index.html file in place. So we might want to say we might want to run our welcome.sls file that puts that index.html file in place, along with the one that starts the service and installs the package, right? And so one way we could do that is we could do a salt jerry state.sls, and we could glue SLS files together manually by saying run Apache and Apache welcome, right? So we comma separate those two things, no space in between them. This is a single argument, and so that needs to be a single string. So Apache comma Apache welcome.sls. And so if we run that, that will run those two SLS files together, and will not produce any changes because we haven't changed anything since then. And as you can see, it ran in the order that we wanted it to mostly. It installed Apache, started the service, and then put the index.html file in place right there. So that works for the simple use case, right? But it would be nice if the welcome.sls file was self-contained, right? If we didn't have to worry about anything that it depended on, and we could just say run it all by itself. And so one way to do that is with an include statement. So if we edit that file, welcome.sls, here at the top we can say include. Now this is YAML, and this is a directive that Salt's state compiler will notice and then process. And this directive includes all of the SLS files that we specify in this list. So this is a list of SLS files. So in this case, we want to just include Apache, right? So now, if we run this again, but instead of specifying the Apache file, we just run apache.welcome all by itself, the result will be the same. So it was installed, the service was started, and then the index file was put in place. Now, again, this is nice because now our welcome.sls is self-contained. We can run it in isolation from anywhere and have it just work. But one thing that's important to note about include statements is you shouldn't rely on them for the source order execution that we've talked about in the past. Now, it worked in this instance because it was kind of a simple example and we didn't have any requisites, which we'll talk about in the next video, that they could say, put that ordering out of whack. But in general, when you start to rely on multi-file state trees, you don't want to rely on source order execution anymore, and you want to rely on requisites. And again, we'll talk about those in the next video. Now, top files do something very, very similar. They glue SLS files together under a target. Now, we've talked about SLS files before when we talked about pillar. Let's make one in our state tree so that we can see what that looks like. So again, this looks like serve salt top.sls. This is just a convention, right? State.highstate looks for this file called top.sls. And in here, just like with pillar top files, we start with the environment and then a target, okay? So if we wanted this to apply to everybody, in this case, Jerry and Stuart, now we can do apache.welcome, that sort of thing. And so if we were to say make a top file and we were to do our ordering in the top file, we wouldn't have to put an include statement inside of apache.welcome. Now there's some good reasons for doing that, and we'll talk about those, but this is yet another way of gluing SLS files together. So if I run this, or if I write that file out, now instead of running state.sls and having to specify all of the SLS files here on the command line, now I can just run what's called state.highstate. State.highstate is saying, make this system look like what is described in the result of my top file, right? And so that's a nice thing because you can just run this one command. You can hard code all of the targets and SLS files here. So, if you wanted all of your web servers to run one thing and all of your database servers to run another thing, right? So say all of your database servers started with DB, right? And then, in here you'd run Postgres, that kind of thing. Right? So now you don't have to specify each host on the CLI. You just run state.highstate against all of your minions and all of them do the right thing. And so a high state run is a very nice thing to be able to rely on just for that, because you've got this hard-coded configuration of what your infrastructure looks like here. And in this top file, as we discussed in Pillar, you can do all of the other normal salt matching semantics. So, if we wanted to do the database role instead, we could do a compound command. So roles database, that sort of thing, right? Or roles database and not Frank, right? That sort of thing. So all of that's available to us from this top file. Now, top files are processed on the minion. Unlike with Pillar, where Pillar everything is processed on the master, as you recall, and just the resulting data structure is sent to the minion, top files in states are processed on the minion, which means this top.sls file is run on each one of the individual minions. So if you ever want to see what is the result of processing a top file, so top files are processed on the minion. Unlike, say, in Pillar, which is processed on the master. As you recall, everything in Pillar is processed on the master and just the resulting data structure is sent to the minion. But with states, the SLS file itself is transferred to the individual minions, just like all of the state SLS files, which means that we can put Jinja and conditionals and that sort of thing in our top file. So, we can do if, something, and that'll just get processed on the minion exactly as it does in a state. We can also use non-standard renderers. So if we wanted to use the Python renderer, for example, then we could do this kind of thing as well, right? And really the only constraint is the data structure that this produces has to be the exact same data structure that would be produced in YAML, right? So just do that trick where you take a look at what the YAML looks like as a Python data structure, and you're all set. So you can do some complex things in top files with those techniques. We'll stick with YAML for this video, though. You can use the different renderers. All of the different renderers are available to you as normal. There's nothing special about a top.sls file. State.highstate just defaults to looking for a top.sls file. But there's another function in the state module called state.top, which allows you to specify the top file that you care about. So that means you can have multiple top files, and you just do state.top and then the name of your top file, and poof, you can have multiple top files. So that might be useful for, say, organizing your infrastructure into, say, a bootstrapping series of states that get a system up to a known kind of baseline, and then another top file that configures them from there. So, configures the web servers to look like web servers and the database servers to look like database servers, but you already know that they've been brought up to that known baseline of, this is the minimum that we need for all servers, kind of a thing. So whatever is appropriate for your organization, just keep in mind there's nothing special about top files. So why you might want to run state.highstate versus state.sls, both perform a regular state run as we've seen, but state.highstate adds that additional targeting semantic. And so it's a nice thing to be able to just hard code in that one file. However, it's still a good thing to be able to hard code the dependencies in each one of your SLS files so that each SLS file is a standalone entity like we did for the welcome.sls. So that way, if you want to run it in isolation, you can. And we're going to see some good uses of running SLS files in isolation as we go through this particular section. So if you code things up with creating a top file, but also making your SLS files self-contained, you get the best of both worlds. In this video, we talked about methods of combining multiple SLS files into a single state tree. In the next video, we're going to do a deep dive on ordering state executions. Video 5.2, Define, Enforce, and Debug Execution Order. In the previous video, we talked about combining SLS files into a single state tree. In this video, we're going to build on that and talk about ordering strategies to get that state tree to execute in the desired order. So we're going to talk about implicit versus explicit ordering. We're going to talk about requisites and requisite types. We're going to talk about the extend directive and what requisite ins are. We're going to talk about ordering strategies for complex state trees. And finally, we're going to talk about how to view the final order. So we've seen already that Salt uses implicit ordering with source order parsing. The way Salt does this is Salt has a custom YAML parser that keeps an internal counter as it's parsing an SLS file to see which order it encounters a given state in. So if we take a look at our serve salt apache init.sls file, install apache comes before start apache, right? And we can see this if we run salt, I'm going to pick Jerry here, state.show SLS apache. Each state picks up a order key, and this order key is generated from this custom YAML parser. So it sees the install apache state first and starts counting at 10,000. Then it moves on to the next one and it counts up to 10,001 for the next state. And so this is the order that these states are run in. Now, you can override that by putting in your own order, right? You can say order 4, right? And that's fine for some things. In general, that is really hard to reason about and very, very brittle. So you can do order first and order last, which do have their uses, so keep that in mind. But generally speaking, order is not a useful directive in states, and so we won't be talking more about it in this course. This implicit ordering is nice because it is simple, right? It's best for a single SLS file, or when you have an order-centric top file, as we saw in the previous video. The bad part with this implicit ordering is it can be problematic for state trees that have include statements or require statements, where those start to run at unexpected times, because as we saw with that counter, it is dependent on when the file is parsed. That counter happens when that file is parsed. So if that file is parsed differently from one state run to another, say that you've got an include statement in one SLS file and an include statement in another SLS file, and then you glue those two SLS files together, you can start getting some conflicts in when the ultimate, that third SLS file is actually included. And so it becomes hard to reason about and just kind of brittle. So the way you get around that is with something called requisites, which provide explicit ordering. This allows you to define dependencies using require statements or some of the other requisites that we'll see. This allows you to use include for any dependencies, and then use a requisite to follow up and enforce the order after that. So the pros of requisites and this explicit ordering are they are very robust. They are the final word in ordering in Salt. They trump all other ordering configuration directives. They're also very flexible, as we'll see. They can provide this ordering expression in a variety of ways. It allows you to write an SLS file that can be safely run from anywhere because it has all of its ordering semantics already baked in. And of course, it's best for complex multi-file state trees where this really starts to matter. The downside of requisites are they're a tad verbose. So let's take a look at what they look like. So here in our Apache state, we could say define a requisite that says the service should definitely start after the package is installed, not before. We don't have to do that in this particular example, but let's look at what a requisite looks like. In this case, we're going to use the require requisite, and all requisites take a list of states that they should reference as part of their lookup semantics. And the syntax for this looks like, so what this means is that we're looking for the install Apache state, or the install Apache ID, I should say, and then the call to something in the package module, a state call to something in the package module under that state. This allows us to uniquely identify this one state under this ID, right? So for example, if we had this under a single ID, this requisite statement would still be valid, right? It'd be looking for the package module call instead of the service module call under the install Apache ID there. And you can't call the same module more than one time under an ID, so this is invalid, and Salt will complain at you if it's a thing. So that's why the syntax exists. It's a way to look up a state unambiguously. And so now we've explicitly said that Apache should start after it is installed. So we can take a look at this, right? If we run our state again, nothing will change, nothing to see there. But say we were to move this state under that state. Let's see what happens. Okay, we can see that the service state picked up the 10,000 count. So that one was encountered first, and so it is ordered first. So let's see what happens if we run it now with that ordering out of place. And as you recall, the output from the state.sls function is the order that it actually ran in. So you can see that it installed Apache first and then started Apache after that. So it ran in the order that we wanted with this requisite in place, even though the source order is out of whack. Requisites build up a dependency tree, and they are evaluated at runtime. And so that's how this works, right? As Salt is executing on this, it hits the service.running state first, and it says, okay, I see I've got a requisite for install Apache. Do I already have a response from that function call? Well, no. So I'm going to pause execution. I'm going to find this state. I'm going to execute this state, right? And then I'm going to hang on to that return. And then I'm going to resume execution, right? I don't have any other requisites. This one requisite has now been satisfied. And so I'm going to resume execution here, right? So then it's going to execute the service.running state. And then it's going to encounter this install Apache state again, but it's already been run, so Salt doesn't run it a second time. And that's it. That's the state run. We'll get to why it's important that this happens at runtime a little bit later, especially when we talk about prereq. Now, since this is a dependency tree, you might be tempted to want to view it as a dependency tree, and there's a great community project for doing so called Salt State Graph. This uses the GraphViz library to actually generate a dependency tree of your requisites. In this graph, the blue is a require statement, and the red is a watch statement, which we'll talk about in just a moment. There are other requisite types in Salt. We've seen require, which requires that the other state run first and run successfully before continuing on. There's a similar one called watch. Watch is the exact same as a require statement in all respects, but it also performs an additional action after that. So, for example, the service module is a good example. Let's jump down to S for state modules, search for service, not that one, not that one, but that one. Any state module that supports the watch requisite will have a function inside of it called modWatch. This function is the additional functionality. In the case of the service module, the additional functionality is restarting the service. So it will have all of the semantics as a normal require statement, but then once all of that's resolved, it then will restart the service. Let's talk about why this is useful. So back to our Apache state. Let's move this back so that install Apache comes first, just so that it reads a little bit nicer. So say we've got a configuration file that we want to put in place, and we want to restart the Apache service if ever that configuration file changes. I'm just going to stub out one as an example here. So some config file.managed. And if you'll pardon the demo, I'm just going to toss a file in temp. So this is going to say, this is going to put this file in place. And what we want to do is, whenever this file changes, let's say it's an Apache configuration file, then we want to bump that service. So instead of requiring install Apache, which we don't need to do here because they live in the same file, let's switch this over to watch. And in this case, it's going to be file, some config. Okay. So now this will cause the service to be restarted if ever this changes. Let's take a look at what that looks like. So I'm going to run state.sls Apache. It's going to put that some config file in place. There we go. And you can see that the service was indeed restarted. So let's go through the execution flow. Salt gets to install Apache, right? It installs Apache, then it gets to start Apache, right? And it sees that there is a watch statement. There's a require statement in there. So it pauses execution. It says, do I have a return from some config already? In this case, no. So it pauses execution, it finds the state, it runs the state, and then it resumes execution, and then starts the service or restarts the service if it's already installed. So that's how that works. That's how it knows to put this in front of this. Okay. Now, if we were to say run this again, nothing would need to change. The service would not need to be restarted. Okay, so no changes. And then, of course, if we change this, it will put the new version of that file in place and restart the service once again. There we go. Service.running, service restarted. In addition to require and watch, there's requisites called onChanges, onFail, and prereq. And we're going to talk about those three in the next video. Suffice it to say, they all conditionally perform executions. Now let's talk about extend and requisite ins. The extend statement allows us to modify the dictionary of one state from another state that lives inside of that same state tree. The reason this is important is because in this file, it's not a big deal that we've got this watch file here under service for this state because they all live within the same state tree. But let's swap this out for our real state tree, and let's see what happens. So as you recall, we've got a serve salt apache mods.sls, and this file has configuration files that affect Apache. And if any of them change, we probably want to restart Apache automatically. The problem is they live in a completely different state, right? Its job is to install Apache and start the service, right? This mods.sls file, its job is to put these configuration files in place. And so it makes a lot of sense for this file to say dep on the Apache state, right? But not the other way around. And so, as we saw in the previous video, the obvious way to do that is to put an include statement in here. Right, so now we're going to make this mods.sls file self-contained like we talked about. But we also want to put this watch statement in place. The problem is we don't want to modify this init.sls in order to do that. We want to keep this mods.sls self-contained and the init.sls self-contained. And so the way we're going to do this is with what's called an extend directive. And so from mods.sls, we're going to extend the start Apache service state, and then from there we're going to put a watch statement in place. All right, and the watch statement that we're going to put in place could be some config, right? If some config lived inside of here, and so that would allow us to get rid of the watch statement here. Right? So that gives us a self-contained init.sls. It's got one job to do these two things, and it's done. And our mods.sls also now has one job. Right? It just puts the configuration file in place, but it's able to cause Apache to be restarted if you include it in the state tree. The problem is this is a little bit verbose, as you can see, and so that's where requisite ins come into place. Requisite ins allow you to do this just a little bit more succinctly. So I'm going to get rid of this. We're going to keep our include, and in here, what we're going to do is we're going to put a watch in requisite. And so that's what a requisite in looks like. So what this says, what this watch in says, is it says find the start Apache ID, find the call to service, find the service state under that ID, and put me in as a watch, right? So append me to that watch list. And that allows us to modify that state at runtime. Okay, now let's run apache.mods. It's now self-contained. Let's see the order that it runs in. Okay, there we go. So you can see that the very first thing it did was install Apache. Then it put mod info in place. Then it put mod status in place because we had that requisite as a watch statement. Then it starts Apache, right? And then it does our command runs. So if we were to say change these, let's put just a little white space in there and run that again. You'll see it installed Apache, nothing needed to change. It did change our two configuration files, and then it restarted Apache. All of that from just this little requisite here. So that's why extend and requisite ins are important. Requisite ins are just syntactic sugar for extend. They take a little while to wrap your head around. A good mnemonic that I use is that in, right? Find this state and put me into that state as a require statement or as a watch statement. And all of the requisite types have the _in variant. So explicit ordering via requisites means that each SLS file is self-contained, and that's important for the reason we talked about in the previous video. That means that one SLS file can be run individually, regardless of how many other SLS files it includes in, or any kind of ordering semantics that you put in there with requisites or whatever else, right? So it can be run individually from state.sls, or you can include it in a top file and run it with state.hightstate, or you can put it in multiple top files with state.top, and you don't have to have the ordering between those two different top files agree. As we'll talk about, you can also run it from Orchestrator or the reactor. And again, you don't have to care about what it's doing. It is essentially a black box. It is self-contained, and you can just run it. It can also be moved to different places within the state tree without breaking things. So, as we've talked about, requisites are evaluated at runtime, which means the only way to view the final order of a state run is to run it. Now, that sounds like a bad thing, but there's a few ways to view it without kicking off a full run. One of them is to kick off a dry run. And so you can do a state.sls test equals true. And the output that you get back is the order that it will have run in. Actually, it's the order that it did run in, but everything just got mucked out, right? Nothing needed to change, but that tells us the order that it would run in. Now, there's another argument to state.sls, which is mock equals true. And what this is this is similar to a dry run, except it doesn't execute anything. It just mocks out all of the runs. So you can see not called mocked. The nice thing about this is it still goes through the state compiler, and so you can still see the order that it mocked those runs in. And so that's a nice lightweight way to check the ordering. In this video, we talked about the various strategies for ordering a state run, and we talked about requisites. In the next video, we'll talk more about requisites to make dynamic decisions during a state run. Video 5.3, Conditional and Branching Logic During a State Run. In the previous video, we talked about ordering in salt states, and we introduced requisites. In this video, we'll talk more about requisites that can change the course of a state run dynamically. We're going to talk about onChanges, onFail, and prereq. First is the onChanges requisite. This requisite optionally runs a state only when another state changes the system. And it does this by looking at the changes dictionary in the state return for the state that it is looking at in that require statement, in that requisite, I mean. So let's take a look at our state tree and see how we can apply it. Let's edit our serve salt apache mods.sls. As you'll recall, we've got this command.run, and this runs whenever only on Debian family systems, and it runs if this file, this configuration file, is not in place, which means the only way we can get it to rerun these two commands is to delete this file. Now, for this particular example, that's not a big deal. This is seldom going to need to be run, and so there's nothing particularly wrong with this, but we're going to use it to demo onChanges anyway. So what we're going to do is we're going to swap out this flag to command.run for a salt state level requirement, a requisite, the onChanges requisite. And we're going to have it watch the file state for these two configuration files. So now these are going to run whenever this file changes. And for this particular example, that's going to work just fine. This will run these two commands more than one time, but Debian treats them idempotently, and so if we run them more than one time, it's not a big deal. And so this allows us to run these when this file changes, and so that's just kind of an extra little bit of functionality. So let's run that. And as you'll see, nothing changes, right? We haven't changed our file, and so the command.run was not executed. So now, if we get rid of this white space that we added in the previous video and run that again, we'll see that not only does the file change, but now that command.run is executed. There we go. So let's go over the execution. It installs Apache, nothing needs to change there. The mod info configuration file did change, and so did the mod status. And so Apache was restarted, and now our two command runs execute. All right, that's great. So now we can execute these command runs just by changing this file. So that's a little value add than over what we had before. One of the problems you may have noticed is these command.runs should really execute before Apache is restarted, for the reason that they're going to put these configuration files in place, and so we want them in place before Apache is restarted. And so for that, we're just going to add our watch in there. And let's make another change to this file. Let's reintroduce that white space, run it again, And now we should see the full run execute all in the right order. Okay. So you can see nothing needed to happen with Apache being installed. There we go, the configuration file changed, and the command.run now executed. Right? Again, configuration file changed, command.run executed, and then finally service.running restarted Apache there at the very end. And you can see, even though we've got multiple watch-ins, the Salt was smart enough to only restart Apache one time. So that is the onChangers requisite. And as you can see, you put the onChangers requisite on the state that you want to optionally run, depending on the other state. And it's got the in variant as well, just like all of the other states. Now let's talk about onFail. OnFail is a requisite that optionally runs a state only when another state does not complete successfully. And it does this by looking at the result field in the state return of the other state. If the result is false, then onFail knows that it should trigger. So let's demo this by creating a new SLS file that deploys a web application. So for this, we're going to do serve-salt myapp.sls. We're going to name it myapp, and we're going to use a state called get.latest to deploy our web application from Git. Let's pull up the docs on get.latest. It's a state module, so start with S, jump down to Git, states.get, and in here is a function called latest. As we can see, latest takes name as a first parameter, like all states, which is the address of the remote repository. Next up, revision, the revision to deploy. And then next is target, which is the target directory where the repository should be cloned. Okay? So we need a repository to deploy. For this, I'm going to grab just a random repository off the SaltStack GitHub organization. Let's pretend it's a web application. It really doesn't matter which one we use. And for that, I'm going to do name, and then the repository, rev, master, and then finally target. And for this, it's going to be var www myapp. Okay, so this is going to deploy a web application from Git. Now, this state is obviously specific to Git, but this pattern that we're going to be talking about is applicable to really any other state, right? We could be deploying the web application by running file.managed or file.recurse, or we could be deploying a Tomcat application using that module, right? It doesn't matter. It's just a web application that we're putting down onto the remote minions somehow, and then depending on the result of the state, we're going to do other states. So say like we wanted to send a notification that would notify us if this state ever failed. To do this, we're going to do we're going to fire a custom event in Salt. Now, we haven't talked about this yet, but we'll be talking about it in the section after this section. So bear with me for now. Suffice it to say, you can have something listening to this Salt event that could say, send out a bark in a Slack channel or a HipChat channel, something like that. Or you could, page somebody. Sky's the limit. So what we're going to do is we're going to notify of fail. And for this, we're going to do event.send. And the event that we're going to send is my company, my app, fail, deploy. Okay? But we don't want it to send this event every time. We only want it to send the event if there's a failure. And for that, we're going to do my app. Okay? So now this event will trigger if there's ever a problem with this get.latest state. Okay, with that in place, let's give it a run, see how it goes. Great, so we've got one minion that failed and one succeeded. That's great. Okay, so as you can see on Jerry, this failed because get.latest was not available. Jerry does not have Git installed, so we'll take care of that. But as you can see, in response to that failure, our event.send did indeed trigger, and it sent our event. Stuart happily ran the get.latest state. He already had Git installed. You can see that there's the new revision that he deployed, and you can see that his notify on fail did not run because it didn't fail. Let's go ahead and fix Jerry as a one-off. Salt Jerry package.install git. Obviously, the way we'd want to do this permanently is to code this up in an SLS file, but this will suffice just for brevity. So now we should be able to run our state, my app, on both machines and have it succeed on both. There we go. Now Jerry has it as well. All right, so that's the onFail requisite. Now let's talk about prereq. Prereq is kind of an interesting beast. What it does is it optionally runs a state if another state will change the system in the future. So what this allows us to do is kind of look into the future. We like to joke in any case. Let's go through a real-world use case, and I think it'll be more clear. Say like my app is a complex web application. It's a big Java application or something like that. And so what we want to do is before we update this web application, we want to drain the web server of all active users. We want to wait until that finishes before we update the web application. Once the web application does update, then we want to restart the web server. But we don't want to shut the web server down if this web application does not have a new version to update to, right? So we don't want to unnecessarily drain the web server. And we're going to use prereq to do this. So let's start by creating a state called drain Apache. And for this, we're going to call out to module.run. This is similar to command.run, except it calls a salt execution module. And for this, we're going to call out to the service module, service.stop. And the m name argument to this is going to be apache.serve from our map file. So let's pull that in. Serve salt apache init.sls. That is the import statement that we want. And so now we can reference that variable. But as we said, we don't want to call module.run every time. We are going to put in prereq. And what that's going to let us do is it's going to let us reference another state. In this case, it's going to be the get my app, but it could just as well be any other state, like file.recurse or tomcat.war_deployed, right? So let's go through the execution, and we'll see how this goes. Here are the steps. Step 1 is it inserts itself as a require statement in the other state. We'll go over this again. The other state pauses execution to call the now required prereq state. Prereq runs that individual state again in dry run mode. If the dry run mode produces changes, the prereq will run. Execution resumes and the other state runs as normal, invoking any other requisites as normal. So let's go through it here. So with this prereq in place, this inserts itself as a require statement into this state. Okay, so the very first thing that's going to happen is Salt is going to try and run get.latest. It's going to see that there's a require statement, so it's going to pause execution and find this state. Now, this state is going to execute, or this prereq is going to execute, and what it's going to do is it's going to say, run get.latest, run this get.latest state in dry run mode, just this one state in dry run mode. If changes is true, right, this prereq is now satisfied, and so the rest of this state will run. And it will actually call out to service.stop and shut down Apache. At that point, this is all done, and this requisite, this hidden requisite, is satisfied, so it resumes execution here. Okay? Get.latest runs for real, producing changes, just like we talked about, and it updates the application. There's one last thing that we need to round this out, which is that was start Apache. So whenever our web application is updated, we want to restart Apache. Okay? So now with that in place, once the state executes for real, this requisite will also execute for real, and it will restart Apache if get.latest produces changes. With that in place, to test this, we're going to switch this revision over to a different revision. Let's jump over to the master branch and deploy that. In order for that to succeed, we're going to need to pass a new flag to the get.latest state, which is force reset. There we go. And that'll allow us to switch between branches willy-nilly. Okay, set that to true. All right, now we are deploying master, and we should be able to see the magic of prereq in action. There we go. Let's go through it. So here's the output for Stuart. Okay. Very first thing that happened is Apache was installed, nothing needed to be changed. Now, drain Apache was actually run. Service.stop was executed, okay? And then get.latest was executed, updating the revision from the old to the new. And then, of course, the watch requisite kicked into to gear, and it was restarted, or in this case, started. No fails, and so there we go, prereq. All of that in this one little requisite. In this video, we learned about onChanges, onFail, and prereq. In the next video, we're going to shift gears and we're going to talk about debugging strategies for large state trees. Video 5.4, Debug a State Run. In the previous video, we talked about the remaining requisites that perform actions if a state produces changes or fails. In this video, we're going to talk about debugging strategies for large state trees. We're going to start by talking about how to debug effectively by debugging each layer separately from the other layers. We're going to do a review of the whole execution pipeline of a full state run, and then we're going to talk about how to verify the result of a state run after the fact. So as you're building out a state tree, it's a good idea to take each step incrementally, right? Debug incrementally. Don't build out a full state tree with a bunch of files, glue them all together in a top.sls, kick off a state.highstate, and then see what happens, right? Debug as you go, little by little. Pay attention to what you happen to be debugging at the moment. If you're writing YAML or Jinja syntax, right, make sure that you check that as you go by running state.showSLS, right, which will process both of those things. Make sure that any errors that you get back from the minion are either coming from the Jinja or YAML parsers. We talked about strategies for that in video 3.7. Remember that the YAML that you produce has to be a valid salt high state syntax. And so again, you can run showSLS to produce that high state syntax, and you can look for errors that come from salt state compiler. Once that high state syntax is good, then you're going to want to make sure that the states that you've written are actually executing in the order that you expect them to. And we talked about ordering strategies in video 4.2. Then finally, you're going to want to look for execution failures in the state functions themselves. Now, these are often due to missing requirements, right? The state didn't run because it's missing a library, it's missing a CLI tool, or you're trying to run it on an operating system that just doesn't support that package name or that operation, that sort of thing. And then finally, you're going to want to verify the result of a state run after the fact. And usually running a second state run right after that to look for unwanted changes is a good way to go. But we'll talk about other strategies at the end of this video as well. So let's do a review of the full execution pipeline for salt states. As you recall, the very first thing that happens in a state run is you're here on the master and you type out a salt star state.sls, okay? Or a salt star state.highstate, how about? And that broadcast goes out to all minions simultaneously. And each one of those minions uses the match module that we've seen already. So each minion performs a match dot what? Let's go with glob. And it says, do I match star, right? And then depending on the output of that function, if it matches, great. If it doesn't match, then it's done. There's nothing else to do. But if it does match, then it executes the function that we're asking it to run. In this case, state.highstate. The very first thing that state.highstate does is says, do I have a local copy of state.sls or of top.sls? And to do that, it runs the function that we've already seen, cp.cachefile salt://top.sls. And so what that does is that performs that checksumming behavior that we've talked about. If the file exists locally on the minion, then it compares the checksum for that file with the checksum of the file on the master. It's a very lightweight check. If it doesn't exist on the minion, then it downloads it, right? If it does exist on the minion and the checksums do match, it's done, right? If they don't match, it downloads a new copy of that file. And in all cases, cp cachefile produces the directory path to the most up-to-date version of that cached file on the minion, right? So then the minion says, okay, for all of the entries that are in this top file, which ones match me? As you recall, a top file has a bunch of targets in it. And to do that, it parses that top file, and we can do that ourselves running state.showTop, right? And this will produce all of the SLS files that match the current host in that top file. And then from there, it goes through and it parses each one of those SLS files, producing a state tree. And you can see that state tree if you run state.show high state or show SLS. Right? And so that produces this high state data structure. This high state data structure is handed off to salt state compiler, which produces a low state data structure, which we can see running state.show low state. As you recall, the difference between high state and low state is high state is more human friendly. It's pretty much what you type into an SLS file. Low state is a little bit more machine friendly. It's a list of executions. It's an ordered list of executions. And then salt state compiler starts going through this ordered list and executing those states one by one. And then, as you recall, as it's going through those states one by one by one by one, every time it encounters a requisite, it pauses execution to look up if it's already got the result of that SLS file or that state for that requisite or not. And the way this happens is every time the state compiler runs a state function, it takes the result of that function and it puts it into what we call the running dictionary. And so that's how, when you encounter a requisite, when it looks up the result of whether or not it already has an entry for that requisite, it looks that up in the running dictionary. And so it's building up this running dictionary as it goes, step by step by step. But then at the very end of all of this, it takes the running dictionary that has been compiled from executing all of those state functions, and it returns that back to the master. So each minion produces its own running dictionary, and it ships that back to the master along with the JID, saying, here's the result for this job ID. Right? And the Salt master stores that in its job cache. Right? So that's a full state run. Now, the running dictionary is something that you've seen. So if we run state.highstate or state.sls, the thing that we get back from each one of the minions is the running dictionary. So this is the running dictionary. It's been formatted nicely, and we've got this little summary here at the end. But if you wanted to look at the actual data structure, you can just output it as JSON, and you can see what the running dictionary looks like. So you can see there's these very interesting dictionary keys that allow us to look up states in a very unambiguous way. And then everything else is just kind of a pretty printed version of what's in this dictionary, right? The result, right? The changes dictionary. Changes, there we go. The ID of the state, right? Which order this particular state ran in, right? Whether or not it was true or false, that sort of thing. And then the human-friendly comment. So this is the running dictionary. So once you've completed a state run, you've debugged all of the layers of the Salt state system. So if there were any errors in any one of those layers, you've seen those and you've diagnosed those, right? So once you've got a successful state run, it would be a nice thing to be able to say, go back in and verify that Salt did the thing that you were expecting it to do after the fact. Now, a common way to test that is with a third-party external tool, right? One popular one is called Kitchen Salt, which is a Salt interface to a tool called Test Kitchen. And this is essentially a way to, it's essentially a different program that does a subset of what Salt does, but, using different code. And so you can use it to say, perform all of those same actions just using a different tool to see if you get the same result. And that's a fine way to go, right? That way you've got that external validation, right? If there's any bugs in Salt, hopefully Test Kitchen will suss those out, and so you can get that kind of two perspectives on the same operation. The downside with something like Kitchen Salt is you essentially have to write your states twice. You write your states in Salt, and then you write this test script that is performing a lot of those same checks in a different syntax. You can also perform a verification using Salt itself. Now, of course, this won't suss out any bugs that exist in Salt, but if you trust that Salt will do the right thing, or those bugs will show up some other way, and then those bugs will be fixed in Salt, of course, then you can verify Salt using Salt itself. Now, one way to go is with a dry run, right? So you kick off a state run, and then you immediately kick off a dry run after that. So you kick off a state.highstate, and then as soon as that's done, you kick off a state.highstate again, but this time with test equals true, just to see if any unintended changes show up, right? You should get the same result both times. Another way to go is with an additional kind of state run using what we call verification states. Now, these are state functions that are scattered throughout Salt's codebase that perform checks only. They don't change the system, they just perform checks. So this can sometimes be useful locally to, say, follow up on the result of an operation, or they're most often useful via, say, orchestrate. So these verification states would be things like states that verify the result of, say, putting firewall rules in place by trying to connect to ports on that machine with that new firewall from, say, an external system. And so there are various states to perform those kinds of verifications, sometimes externally, right? So you put an Apache configuration file in place using a file.managed or something like that, you restart the Apache service, and then you might want to, say, follow up on that by calling out to the HTTP state, right? By trying to connect to that HTTP port and verify that the result that you get back from that is what you expected. So there's, again, just a handful of these verification states, and more are needed. So if you've got ideas for that, please file issues on the Salt repository, or feel free to contribute verification states yourselves. But yeah, those kinds of operations are quite useful to provide that additional validation, and again, often from an external system. So in this video, we talked about debugging strategies for states. In the next video, we talk about a way to share data between minions, which is often useful to do in state runs. Video 5.5, Share Data Between Systems with SaltMine. In the previous video, we talked about debugging state runs. In this video, we're going to change topics to talk about how to share data between minions. We're going to talk about how to configure mine via pillar, how to manually run and refresh mine, and we're going to talk about how to pull mine data into a state. So let's talk about what SaltMine is. There's a few ways to share data between minions in Salt, one of which is the peer system. It's not very often used because the way it works is you whitelist certain minions to be able to run certain functions on the Salt master, and then you initiate a call from a minion, say, hey, I need, some information from this guy. So that call goes out to the master and stays open synchronously. The execution goes down to the other minion, collects that the return from that function. That goes back to the master and then back to the original initiating minion. And so as you can see, there's a few hops involved. Whereas with SaltMine, what you do is you configure certain functions to be run on a certain interval. And then any minion that's running those mine functions then will push that up to the master on that regular interval. So now whenever any minion needs to know mine information from any other minion, it asks the master and the master replies, and you're done. Now, you can configure SaltMine using pillar or using the minion configuration file. In both cases, the configuration looks the same. You define what's called mine functions and optionally mine interval. So in our pillar, we could do serve pillar, let's go with mine.sls, okay? And then in here, you configure mine functions. And then you specify any functions that you want to run on a regular interval. So network.ipaddrs is a common one. Adders. And then any arguments to that function come after that. So this is something that often minions will want to know about each other. If we configure this mine functions to go out to all minions, say we switch to serve pillar top.sls, right? We can say all minions get the same mine data. Then all minions will run this network.ipaddrs and send that up. If you want different minions to have different mine data, you do the normal pillar thing of sending just that pillar data to just those minions. And we can do that with Jinja, as we've talked about before, or we can do that with the top file and specify different SLS files that go to different minions. Once that's done, if you do a salt star, salt util, refresh pillar, that will cause all minions to refresh their pillar, and as part of that, they'll see that they pick up new mine directives, and then they'll start running these functions, these mine functions, on the default interval. The default interval is every 60 minutes, but mine is pretty lightweight, so if you wanted a mine interval of even a minute, that's usually just fine. We can also force that by running mine.send network.ipaddrs, and that will trigger each minion to push that data up to the master. So here's the mine documentation. It's under topics mine, and it's well worth a read to see what knobs and dials are available, such as mine aliases and mine interval, that sort of thing. But for now, let's just jump to the mine execution module. And you can see which functions are available in there. So you can see mine.send, mine.update, flush, get, delete, that sort of thing. And so all of these are well worth reading about if you start to use mine. Once that's done, we can view the cache on the master using the cache runner. So we can run salt run cache.mine and then a target, and that'll show us what cache data is available. Another nice thing about mine is you can send information from minions, say like status.uptime, without having it configured necessarily. So this is a nice thing for one-offs. And you can run salt runner again, and you can see that we've got that status information as well. So there are execution modules, mine.get, mine.update, and mine.send, and those will push mine data up to the master. And then on the master, you can run mine.get or the cache runner. You can clear mine or you can view mine data to actually view or do things with that cache data. That's a nice thing to be able to rely on from, say, Orchestrate or things like that are on the master side. And then finally, it's a common use case to pull mine data into a state. And you do that with mine.get. Now, it's a good idea to run this at the CLI to see what kind of data structure comes back from a given minion so that you know how to loop over it in Jinja. So for example, it would be a good idea to run mine.get, and then after that it takes a target, network.ip adders. This is one of those examples that we talked about at the very beginning of this video series where it starts to get a little confusing what is a salt command and what's a salt target, that sort of thing. The structure is the same: salt, the target, the function, and then any arguments to that function. It just happens to be that one of the arguments to this function is a salt target, right? So again, don't get confused. So this is a little confusing, say run from the master, but if you run this from Jerry, then what you get back is just this little subset here. If you run this from Stuart, you get this little subset back here. And then each one of those minions can do something with that data. So let's see what this looks like from a minion. Let's jump over to Jerry, and let's run salt call mine.get, and let's restrict this to Stuart. Cut down on a little noise, and then network.ip adders. But now let's look at this as JSON. So this is what you'll have to loop over in Jinja if you wanted to consume this from Jinja. You can see that you get back a dictionary of values, and those values are minion IDs, and then for each minion ID there's going to be an array of IP addresses that apply to that minion. And so as you're looping over that in Jinja, just keep in mind you're going to have to loop over minion IDs, and then you're going to have to loop over IP addresses in that. So you're probably going to have 2 for loops inside of Jinja. So viewing that as JSON really makes that data structure clear, and it makes the path to what you need to write in Jinja more clear. In this video, we learned how to use SaltMine to quickly share data between minions. In the next video, we'll talk about how to execute state runs on a master, also known as orchestrate. Video 5.6. Use Salt Orchestrate to manage complex state runs. In the previous video, we learned how to share data between minions via SaltMine. In this data, we return to states to talk about how to execute a state run on a master using Salt Orchestrate. So we're going to talk about master-side state runs. We're going to learn how to call out to minions from those state runs. We're going to talk about any master-specific modules that are available. And then we're going to talk about how to use non-master-specific modules. So Salt Orchestrate is kind of billed as a big thing, but what it really is it's a master-side state run. There's nothing weird or different about it. It uses all of the same code paths. It just happens to execute on the master. So what that means is there's no additional things to learn, right? Everything you already know about states and requisites and ordering and all of that stuff still applies to Orchestrate. But it also means that you have access to be able to do more things. Because you're executing from the master, you can say call out to minions. You can reference the cache on the master. You can call out to Salt Cloud, that sort of thing. So there's a few ways to call out to minions, and also to the way you kick off Orchestrate is via a runner. So if we jump to the module index and down to R for runners, there is a state runner. And you can kick off Orchestrate by calling state.orchestrate. State.orchestrate just starts up the normal Salt state system, right? Everything else is the same. So it takes a mods keyword argument, which are the SLS files that should run, and Orchestrate files get pulled out of file roots, again, just like Salt states on a minion. Now, you can call any Salt module, any Salt state module that you can call from a minion in Orchestrate. But there's also a few state modules that are specifically written to be called from Orchestrate, and they live in the Salt state module. Let's take a look at those. All Salt modules, as for state modules, and there is a Salt mod, there we go, state module that gets loaded into memory as just Salt. Now you can see in here there is various functions like function and state, and what these allow us to do is call down to minions. You can see they take a target parameter. So if, for example, we were to call salt.function, again target parameter, from an Orchestrate file, that would allow us to call out to an execution module on a minion. So let's do it. So we're going to create a file, serve salt. And actually what we should do is we should make a subdirectory. I'll call this orchestrate, or orc for short. And the reason for that is the functions that we're going to put in the file, in the SLS file that lives in this directory, are specifically for orchestrate. And we don't want to confuse those with our other SLS files. Serve salt, orc. Now let's just do testfun.sls. Okay. So in here we can say call execution function salt.function. Okay. And then it takes a target parameter. We'll target everybody. And the name parameter is the name of the function to run. So let's do command.run. And then this part is interesting. So arg and kwarg are singular, and these are the positional arguments or the keyword arguments that get sent down to the minion. So if we specify arg, it is a list. So we're going to do command.run. So let's go with date. Okay. With that in place, now we can run salt run state.orchestrate orc test fun. This will send an execution down to the minions. It'll kick off that execution function and then return back. So you can see that we got a return from both minions, Jerry and Stuart, and they both returned the dates on both systems. So there we go. There's an orchestrate run. In addition to that, there's a function called state. Now this is exactly the same as what we could do with state.function and say run state.sls, except it is tailor-made to work with states. So let's take a look at it. So what this does is this allows us to specify the same things as before. Name in this particular function is ignored. And then we can kick off a high state run if we want to, or we can specify a list of SLS files to run. So this allows us to run state.highstate or state.sls. So let's switch this over. Actually, we'll keep that in place. Call state functions salt.state target star. And this time let's do SLS and apache.welcome. So now if we run this again, we get a little bit more output since we're running 2 functions instead of just 1. And there we go. States ran successfully, no changes made to Jerry or Stuart. So as you can see, orchestrate is this salt.state function is written to consume the output from states and then provide a higher level overview to those for the orchestrate run. There's one other thing we can do in here, which is we can orchestrate runs across different minions. So for example, say we wanted to run a state against one minion and wait for that to finish and succeed before moving on to the next minion. For example, we wanted to set up our database servers before we set up our web servers so that our web servers can connect to our database servers when they come up. We can do that with orchestrate. So we could do something like this. Call state functions 1 and call state functions 2, right? And instead of specifying target here, let's start with Jerry and then do Stuart. And really, the only thing we need to do to put this in place so that Jerry runs before Stuart is to add a requisite. And now with that in place, we can kick off a state run on Jerry, followed by Stuart. Salt run state.orchestrate org.testfun. It's a little error with pillar since we don't have a minion ID for our master. So there we go. Function ran successfully, command.run, here's the date from both of them. It executed state function 1, followed by state function 2. In addition, there's some execution modules that we can call from orchestrate, and these live in the saltutil execution module. And these are functions that let us call execution modules or runner or wheel modules from orchestrate, and the salt function, salt.state, salt.function, they actually wrap these. So there's a few master-specific modules that we can call from orchestrate. This allows us to, say, call out to the master-side cache or perform master-side specific actions like key management. We can accept keys or delete keys, that sort of thing. And we can call out to things like Salt Cloud. We can also listen to the master's event bus with wait for event. And this is kind of a handy thing. So say, for example, you wanted to kick off a system.reboot. And then you wanted to wait for all of the minions to finish rebooting before you continued on for any of the other steps. You could do wait for event, and you could listen for, say, the start event. Now, we haven't talked about salt events yet, and we will in the next section, but you could wait for that minion start event from the following minions with an optional timeout, and then once all of those minions had checked in, as in they had rebooted and reconnected to the Saltmaster, then you could carry on from there and then do things to those newly rebooted minions. So that's a nice thing for, say, Windows systems where you have to reboot frequently after installing packages. And then finally, you can call any non-master specific modules at all. You can install packages on the master. You can reference the local file system. You can shell out, that sort of thing. And so orchestrate is a nice way to, say, salt the master. You can configure the master programmatically. You can use salt orchestrate to, say, configure salt or put files in place and or configuration files in place, that sort of thing. In this video, we learned how to manage the Saltmaster and orchestrate operations across minions using Salt Orchestrate. In the next volume, we're going to talk about Salt's event system and the reactor and Salt API. We'll start with section 6, talking about events in the reactor. We're going to go over an overview of Salt's event bus. We're going to learn how to send custom events. We're going to learn how to listen for events and trigger actions using Salt's reactor. We're going to integrate Salt with external tools using events. We're going to send events using beacon modules, and we're going to learn how to debug the reactor and some best practices. Video 6.1, an overview of Salt's event bus. In this video, we'll learn the basics of Salt's events because we're going to spend the rest of this section creating and using them. We're going to take a look at master and minion side events. We're going to talk about the anatomy of a Salt event, talk about various event types, and we'll talk about how to view events. So there is a master side event bus and a minion side event bus. It's sort of an event loop. And the minion can also send events up to the master. Now you can tap into the event bus on either one of these machines and just listen in. You can have many, many subscribers to the event bus in Salt. And the minion can send events up to the Saltmaster by just sending up the same way it sends up job returns. So what a Salt event is it's two things. It's a tag and data. The tag is a string. It's a / delimited kind of namespace. And it can be matched on via a globbing syntax, as we'll see. The data is a dictionary, and sometimes that dictionary is going to have an ID field if that initiates from a minion. Other times it won't have an ID field, so like Salt Cloud events have a name field because we don't yet have a minion ID. And all Salt events have a timestamp associated with them. There's various kinds of event types. There's a non-authoritative list in the Salt docs at the URL below. So you can see that there's events for authentication. There's a minion start event when the minion first connects to the Salt master. There are events that are fired whenever a Salt key changes key statuses. There are Salt events that are fired when jobs are created or job returns come back from minions. And there's events for when runners return data. There's also events for something called presence, which we'll talk about, and then Salt Cloud fires events. So if we jump to the Salt docs, we can see each one of those Salt events is kind of described here, so you can see which data is available in a given event and any other detail about that event. So, well worth looking over. In order to view events, you can do so via a runner, salt run state.event. There's also a salt call variant if you want to watch the event bus on the minion. So let's run that now. Let's run salt run state.event. And what we're going to do is we're going to pass an argument to that which is pretty equals true. And this is going to pretty print the JSON as it comes in from the CLI. And now we're going to run something that's going to trigger an event. We're going to run a test.ping. Okay. So we get the return back as normal on the right, and we get a bunch of events on the left. If you see an event tag that does not have slashes in it, it is an old style tag that will be deprecated and removed, so feel free to just ignore it. So the very first thing that we can see here is there's a salt/job event. So all Salt event tags are namespaced with specificity. So all Salt events are going to be prefixed with Salt, all Salt job events will be prefixed with Salt/job, and so on. So we can see there's a job event for this job ID, and it's a new event, meaning we're sending the broadcast out to the minions. And so we can see that here's the function we're sending out, and here are the minions we expect to return for this target. And we've talked about that educated guess before. Here it is laid bare. And then as job returns come in, it fires an event. So Salt job, same job ID, but this time it's a return event for a given minion. And we can see that the the event has the actual return from minions. So we ran test.ping, meaning the return is true in this case. The state.event CLI is written to be consumed from other shell tools. It's a way to integrate shell tools with Salt's event system. So if we pull up the docs, all Salt modules are for runners. Scroll down to the state runner. And so if we jump to the docs on the state event runner module, we can see that there's some examples of how that might be used from other shell tools. So say you wanted to initiate a system reboot like this, and then you wanted to wait for the minion start event, and you were just waiting for one minion, and you didn't care about the output. So this would just block until Jerry would fire that event, and then kick off a high state on Jerry, right? So here we go, 3 shell commands all strung together on a CLI. In addition to that, you could do something like listen for a list of minions and kick off a system reboot on all of them and wait for all of them to chime in. Or you can just watch the event bus in, say, a bash while loop if you want to see what that looks like. In this video, we learned the basics of what Salt events are, how Salt uses them internally, and how to watch them. In the next video, we're going to create our own custom events. Video 6.2, Send Custom Events. In the previous video, we learned the basics of Salt events and event types. In this video, we're going to create our own custom events. These can be used for a variety of things. We're going to learn about how to define a namespace. We're going to send events from a minion. We're going to add arbitrary data to that event. We're going to add minion-specific data to that event. And then finally, we're going to send events from third-party tools. So it's a good idea to define a namespace when you are creating your own custom event. As we saw in the previous video, Salt events are namespaced with specificity. So all Salt events start with Salt. And so it's a good idea to say, start all of the events that you send with some common prefix, perhaps your company name. And then from there, go on and drill down in whatever makes sense for the data that you're sending. So go from most general to most specific in the event tags, and keep in mind that you can then match on the event tag in a variety of places, as we'll see in upcoming videos. You can send events from a minion using, you guessed it, an execution module. This one is called event.send. So let's take a look at it. M for execution module, event. There we go. Event.send. So event.send takes the tag as the first parameter, and then any additional parameters are optional. So let's jump over to our minion and run that. So first we're going to do a salt.run state.event so that we can watch the event bus. And then we're going to jump over to Jerry, and we're going to run salt call event.send and then a tag. So my company, my tag. That returns true, it's fire and forget. If we jump back to the master, we can see, there we go, my tag. And here's what came through. So you can see data, the inner data dictionary just had some publish information. We can see that the ID of the minion that sent the event was Jerry. And this is something we can rely on incidentally. And then we've got the programmatic access to the tag, and there's a timestamp for the event. So let's try that again. But let's send some additional data through, okay? So for that, we're going to do event.send once again. Now, as you recall, Salt will parse CLI arguments as YAML. So if we were to do something like foo bar true, Salt will parse everything in between those single quotes as YAML. So now if we jump back over, we can see here's the event, and here's the event data. And this time we've got bar is equal to true, and then you can see that got picked up as an actual Boolean value, and foo is foo. Right? Whenever you send a custom event, the event data that you send is under this data subdictionary so that you can't step on the top level keys that are in that event for security reasons. So again, use Salt's argument as YAML syntax to pass in arbitrary data structures. In addition to that, event.send is intended to be used by CLI tools, and so there's an easier key equals value syntax if you want to send string values. So if you don't need to send complex data structures, if you just want to do foo equals foo and bar equals bar, you can do that, and you can see that that comes through just fine. A little bit easier to type in at the CLI. But again, that'll be limited. So event.send also allows you to send up minion-specific information. Now, the reason this is useful is one for integrating with third-party tools, as we'll see in just a moment, and the other one is Salt events have the ID of the minion that sent the event, but they don't have any other information about the event. So, say you're reacting to an event in the reactor, you might want more information from that minion, like grains or pillar data, that sort of thing. And so event.send allows you to send additional data. You can specify with env, and that'll include environment variables, with grains, with pillar, and so to send that additional data up. Let's take a look at what that looks like. Let's jump over to Jerry. And this time around, we're going to do with grains. And this can either be a Boolean to send all grains, or it can be an array of grain values to send. So in this case, let's send the OS family grain. Okay. So now if we jump back, we can see that in our event data, we've got a subdictionary called grains, and it has our OS family grain. That's true for environment variables or pillar data as well. So the reason you might want to send environment variables is integration with third-party tooling. So for example, Jenkins. Jenkins can run a job, and that job makes various details about that job available as environment variables. So again, with the other one, you can specify true to include all environment variables, or a list of strings or variable names to include. So for example, if calling this from a Jenkins job, you could say use sudo to avoid having to need root access in order to call salt call, event.send, some string, saying the Jenkins server saying some build is finished, and then you can say with env, and then you can pass in the environment variables you want to send. So if it were, say, a build server, you'd probably want to send the build ID, the URL, and the Git branch that build came from, the Git commit that build came from. So this allows you to integrate with Jenkins in a very first-class kind of a way. And this example in the event.send documentation will show you how to set up Jenkins to use sudo. In this video, we learned how to create and send custom events. This can be done manually or from third-party tools, and as we'll explore in an upcoming video, it can even be done from completely external systems via Salt API. But before we do that, we're going to talk about how to react to events using Salt's reactor. Video 6.3. Listen to events and trigger actions with Salt's reactor. In the previous video, we learned how to make custom events. In this video, we're going to actually use our custom events as well as Salt events to perform actions automatically. We're going to learn how to configure the reactor, how to write reactor SLS files and best practices, and how to use the reactor to run our states. So we should start by talking about what the reactor is. The reactor is a long-running process that watches Salt's event bus and takes actions based on those event tags that come through. Now, it didn't begin life as an engine module. It predated engine modules, but it's since been retrofitted as an engine module because engine modules are long-running processes, oftentimes that watch the Salt event bus and then do things. So that's what the reactor is nowadays. So the way the reactor works is you configure it to listen for certain Salt event tags, and then you list SLS files for it to render when it sees those event tags. So let's start by editing the Salt master config. Scroll down to the bottom. We're going to add a new section, reactor. There is no default. So the very first item is a list of event tags to listen for. So say we wanted to listen for everything coming from my company, my event, star. Okay? So that means that we can glob on Salt event tags. And then after that is a list of SLS files to render whenever that tag comes through. So this might be salt : / and then something that lives under file roots, or it might be something like serve reactor highstate.sls. Okay? Now, it's a good idea to, say, separate your SLS files in file roots from your reactor SLS files for two reasons. One is oftentimes they contain sensitive data, and the other one is they take a slightly different syntax from the SLS files that you can run via Orchestrate or Salt's state system. And so it's a good idea to keep them separate just for that. So what we're going to do is we're going to make a directory, serve reactor, and we're going to put our file in there. Reactor SLS files have the same Jinja to YAML pipeline that SLS files do, but they have a different Jinja context, and they take a different syntax, as we mentioned. So that syntax is run high state. The top level ID serves the same purpose as it does in salt states. It should be unique, and it should serve as sort of a description of what the states that come under it do. After that, the syntax differs. So we can run anything we can run from a master, including sending executions down to minions. So let's do that. And to do that, we have to prefix the module with cmd. After that, it's as normal, high state, and then that takes a target parameter, similar to how we saw in orchestrate. Okay. So if we were to do that, that is the equivalent of running a salt star state.highstate on the CLI. They're functionally the same, it's just different syntax. Okay. So with that in place, I'm going to restart my salt master. systemctl restart salt master. Since we edited the master config, we have to restart. And I'm also going to listen to the event bus. Salt run state.event pretty equals true, as we saw in the previous video. So now with both of those two in place, I'm going to jump over to Jerry and I'm going to kick off an event that's going to match my event. Okay. To do this, we're going to do salt call event.send my event foo. Put any event data in there. Event.send, pardon me. Okay, fire and forget, we get a true back. Let's see what we get on the event bus. There we go. My event foo, and we can see that that came from Jerry, no data. And then, right after that, we can see that a new event was created. State.highstate targeted to star. So the reactor kicked this off. Now the jobs that the reactor kicks off are the exact same as jobs that you would kick off from the CLI. They have a job ID, the job returns show up in the job cache, same as normal. There's nothing different about them, it's just who initiates the command, you or the reactor. Then we can see that the return came back from Jerry, and our high state ran successfully. There's another one from Stuart. So there we go, the reactor kicked off the high state that we had already written. One thing that you should keep in mind with reactor SLS files is they should render as quickly as possible. So the SLS file that we're looking at here, that gets executed, that gets rendered, I should say, in a single process. And so any other reactions would also get rendered in that process. So if this takes a long time to render, then those other reactions can get backed up. But the thing that this thing executes, right, this rendering this file produces a data structure that we then use to call state.highstate. The state.highstate is executed by a pool of worker processes. And so that can be long running. You can kick off long running, say, orchestrate runs, that sort of thing from the reactor, no problem. And so that indicates that the reactor SLS files should really be simple, right? They should be one-offs. They should see a tag and kick off a thing, and that thing can be complex, but the reactor SLS file itself should not be complex. And this goes back to what we were talking about for making SLS files black boxes, right? If you put the functionality into an SLS file, right, that's the thing that's hard to write, and then you can run that, you can test that from the CLI, and once that's baked, you just call it from the reactor and you're done. You don't have to do any complex debugging within the reactor itself. So the reactor can trigger any action that we can trigger from the master, which means running an orchestrate for complex master side or minion side operations. We can kick off a state run, as we just saw, and we can run execution or runner modules. So say you wanted to, say, listen to the event bus for notifications, right, like we saw with the onFail requisite. And then whenever you see one, call out to an execution module or a runner module that notifies your Slack channel or your HipChat channel or something in IRC with that notification. You can also make ad hoc returner-like data brokers, and there's a great community project called Salt Events D that does exactly that. Salt Events D listens to the Salt event bus and it matches on Salt tags, same as the reactor, but then based on those tags it can then shuttle that event data to arbitrary data stores. So it can say, if you match this tag, put it in this data store, and if you match this other tag, put it in this other data store. that allows you to, say, store job returns for a long period of time in, say, Postgres or syslog, and then other events that are more ephemeral, like notifications, in something just like Slack. Cool community project. So we've already seen how we can call our states from the reactor. We can also forward event data as pillar. As you recall, we can send pillar data in at the CLI when we call our state system. As you recall, the place that we left our serve salt myapp.sls file was we had hard-coded the master branch right there in the file. Let's pull that from pillar instead. Salt.pillar.get version, and if nobody passes that in, we'll default. So with that in place, we can now do a salt star state.sls myapp, and we can override that version by saying pillar equals version develop. Okay, so now we can override that at runtime. We have parameterized this state. Okay, so with that in place, let's call that from orchestrate. From the reactor. So let's edit our salt master config. Scroll down. Now let's make a state to deploy our application. So in this case, it's going to be, instead of my event, let's do my app deploy. Okay. And then for this, we're going to make a state called deploy my.sls. Okay. We've edited the salt master config, so I'm going to restart the salt master. And while that's going, I'm going to create this file. Deploy my app. Again, command. This time we're going to do state.sls. Specify our target. Now let's pull our target from the event data. We can grab that using Jinja as data. Data.id, in fact. Data.id. So the event data has an ID parameter from the minion that actually fired the event. So now let's say kwarg, and then mods, and this will be my app. Okay, so what we have on the left is equivalent to salt some target state.sls my app. Okay, it's actually equivalent to mods.myapp, which is the same. Now we also want to pass pillar data through, so let's do that. And it's just a dictionary. So let's get that from the event. Okay, so with that in place, we can now fire that custom event. As you recall, we're listening for myapp deploy, and I'm going to listen to the event bus once again, salt run, state.event, pretty equals true, jump over to Jerry, and this time we're going to fire this event, and we're going to pass in some additional data to the event that we fire, namely version is equal to master. Okay, there we go, fire and forget. So let's scroll up and take a look at what this event data looks like. There we go. myapp deploy, and you can see that that came from Jerry. And so when we do data.id, that gets set to Jerry. And then we've got this data.data. So what's that all about? Well, when we call a custom event, any custom data that we send is available in this data dictionary here. But this is the dictionary that's available to Jinja as data, meaning there is a data.data, and so our version is inside of there. Okay, this prevents us from stepping on any of these top-level keys from custom events for security reasons. So you can see that version is right there. So let's scroll down. All right, here's the reactor. It is kicked off state.sls for us, and it is targeted only Jerry, so it pulled that value out of Jinja for us. And the keyword arguments to it has been my app and version equals master. Okay, so now if we scroll down for the return for that, we should see that it did indeed deploy a new version of that app. Okay, repository was hard set to a new revision. A little hard to eyeball in this raw format, but it did indeed run. In this video, we learned how to use Salt events and custom events to trigger actions. In the next video, we'll talk about how to integrate Salt with third-party tools using events. Video 6.4. Integrate Salt with external tools using events. In the previous video, we learned about Salt's reactor system that can react to custom events and Salt events. In this video, we're going to talk about how and whether you should use Salt events to integrate third-party tools with Salt. We're going to take a look at common workflows for working with other programs, external programs, when to integrate via events, when to integrate via another way. We're going to talk about some real-world examples of using Jenkins to send Salt events as well. So, there are a few common workflows for working with other programs in Salt. If your integration can do a fire and forget, event.send in the reactor is a good way to go. So for example, Jenkins, does an event.send, it doesn't care about the result, that sort of thing. When it's done, it just does an event.send saying, hey, I'm done. And then the reactor picks up on that. Another way is if you do need that return, right? So you start a command and you look up the return for that later. We'll see this when we talk about Salt API. For example, you start an async job, you get the job ID for reference, you wait a given time, and then when you care about the result of that job, you look it up to see if it's done yet. And then finally, there's to start a Salt command and then synchronously wait for the return. So you start a synchronous job and you just block until it's done. And as we've seen in previous videos, Salt goes to a lot of machinations to present a synchronous interface on top of what is just an asynchronous series of operations behind the scenes. And so if that's good enough, if you can rely on that synchronous facade, then it's a nice way to, say, simplify a shell script that needs to wait for a job to finish. So when it's a good time to integrate via Salt's event system is ask yourself first, can it run a minion daemon, right? The system that you're integrating with, can it run a minion daemon? Because if it can, you can just fire an event whenever you feel like it. There's nothing additional to install or set up or configure. You just fire an event, right? You set up a reactor to listen for that particular event and you just fire it, right? So if it can run a minion daemon, firing a custom event is a good way to go. If another question to ask yourself is, do you need to directly associate the Salt job that may or may not be kicked off in response to that event with the invocation? So if you need the results of that job when you kick off the event, then sending an event is not what you want. It's not fire and forget, right? So for that, Salt's peer system, which we haven't covered in this video series, but it's a way to, say, whitelist one minion to be able to run commands on another minion, proxied via the master, of course, or something like Salt API would be a better choice. So that allows you to, say, get a job ID back when you kick off a function. Or if you actually need the full job results, ask yourself if you need them, and if you do need them, when and where do you need them, right? We've talked about Salt's returner modules already. They can deliver a job result to a predictable location asynchronously. When the job is done, it just gets put into, say, your MySQL database, that sort of thing. So returners are very reliable and very simple. Simple to configure, simple to use, that sort of thing. But if you need to do, say, something like kick off a Jenkins job, wait for it to synchronously finish, and then write the result of that to Jenkins, that's where, you're going to have a little custom work ahead of you. So something like using Salt's peer system again or Salt API would be better to do that synchronously if you need that right there. So, for example, Jenkins is a common way to integrate Salt with a third-party tool, and so much so that the event.send documentation has some examples of how to do Jenkins integration. So if we jump to the module index, down to M for modules or execution modules, and scroll down to the event module. We've seen this before. Event.send has some parameters in here that are useful specifically for Jenkins. So for example, Jenkins will often make the results of a Jenkins job available as environment variables. And so you can specify with env, and you can pull those environment variables right into your Salt event. In addition, Jenkins is often not running as root, and you need to be able to run Salt's Salt call as root. And so here's an example sudoers configuration so that you can have Jenkins use the sudo system. So you would say allow Jenkins, the Jenkins user, to run this Salt call event.send without having to specify a password. And so that's what your sudoers would look like. And then once that's in place, you can then call Jenkins via sudo with the -e flag to preserve the environment. And so this is what you would put inside of your Jenkins job verbatim: sudo -e, salt call, event.send, and then whatever event you wanted to specify, and then any environment variables that you wanted to pluck out of Jenkins's environment there for that job, and then send those as part of the event. So for example, build system, let's say, builds a package. could fire an event saying, hey, the package has been built, from this Git branch, this Git commit, that sort of thing, and at this URL. So that could go up to the salt master, to the reactor. The reactor could pull this build URL out of the event data and then say, copy that up to the salt master, or have some other minion, fetch that from that build URL and then deploy it, that sort of thing. But again, useful for fire and forget. That's really the line in the sand for integrating with third-party tools, is if fire and forget is good, Salt events will work for that. In this video, we talked about strategies for integrating Salt with third-party tools using events. In the next video, we're going to explore another way to send events in Salt using beacon modules. Video 6.5, Send events using beacon modules. In the previous video, we learned how to integrate Salt with third-party tools using events. In this video, we're going to learn how to create even more events using what are called beacon modules. We're going to talk about what they are, how to configure, start, and stop them, and we're going to demo the iNotify beacon. So beacon modules are yet another module type in Salt. They are lightweight functions that are invoked on a regular and short interval. The default is every 1 second. The function is executed every 1 second. And what they do is they send Salt events based on certain criteria, and they're very open-ended. So for example, beacon modules can be used to tail a file, or to watch the file system for changes, or to watch for system logins, or failed logins, or to periodically send system data. We can see the list of modules that ship with Salt if we jump to the module index, to B for beacons, and these are the beacon modules that ship with Salt. So for example, the wtemp module can watch the system actively for logins. So say like you wanted to fire a custom Salt event whenever somebody logged into a system somewhere in your infrastructure as root, and then you've got a reactor set up to listen for that to bark something to the Slack channel. So whenever somebody logs on as root anywhere in your infrastructure, you get a notification in Slack saying, hey, someone logged on as root. Or if you want to do the same thing with failed logins, the btemp, right? Or you could use iNotify to actively watch a file or directory. Or you could say, use the status beacon to call out to the status module, which we've already seen, and periodically send a Salt event with status information about the system. So that could be used to, say, monitor a CPU graph or memory usage over time, that sort of thing. So again, very open-ended. You configure beacons either in the minion config or in pillar, just like you do with, say, Salt Mine. You can view the status of beacons using an execution module, right? M for execution module, and there is a beacon execution module, which gives you an interface into, say, viewing the status of beacon modules. You can add them or disable them or enable them or list them, that sort of thing, all from this execution module. You can also change intervals or various other configuration options, and that's all worth reading about if you jump to the beacon documentation. So, for example, if you wanted to change the interval that a particular beacon fired on, you could do that here. Or if you wanted to, say, disable a beacon during a state run, for example, say you've got a reactor set up to kick off a state run in response to a beacon, you don't want to, say, have that in a loop, so you'd want to turn off that beacon during a state run so that you don't get a nested loop, that sort of thing. So this whole document is well worth reading. Let's demo the iNotify beacon. As you'll recall in the section in states, say you've got a file.managed like we've got with our Apache file. So serve Apache, let's say serve salt Apache, and our welcome page, right? To put down that index.html file. Say you've got a file.managed as we do here, so when you kick off a state run, it will put this index.html file in the correct state. But then say somebody logs in after that and changes it, then it will be in the wrong state until you kick off another state run. It doesn't actively monitor things over time, right? It's just in the context of a state run. So say we wanted to do that active monitoring over time, well, let's use a beacon module to do exactly that. So let's configure the iNotify beacon. We're going to do this via pillar, serve pillar, monitor welcome.sls. And in here, we're going to make a top-level key called beacons. Make sure you spell it right, B-E-A. And we're going to configure the iNotify beacon. And then under here, we're going to specify that we want it to watch our index.html and that we are going to do a mask of, meaning we care about close write, meaning if anybody writes to this file, we want it to fire an event. We also don't want this to kick off during a state run because we're going to use this to kick off a state run. So true. Right. Make sure that mask is indented to after, since this is a dictionary. It reads well, but don't forget that this is a data structure. Okay. So there's our beacon configuration. Now, since this is in pillar, we've got to make it available to all of our minions. So we also need to edit serve pillar top.sls. Okay. And in here, our file is called monitor welcome. So let's add another line in here called monitor welcome. So with that in place, this is going to go out to all of our minions. Salt star, salt util, refresh pillar. Let's make sure our minions picked up that right pillar. Pillar.get beacons. There we go. They've got the beacon configuration. So now what we're going to do is we're going to call out to the beacon module, beacons dot enable, and this will enable all configured beacons. And then we can view which beacons are enabled by calling out to beacons.list. There we go. There's our iNotify beacon. Good deal. All right. So with that in place, let's go ahead and watch our event bus. Salt run, state.event, pretty equals true. Okay. And let's jump over to one of our minions. Let's jump over to Stuart. I'm going to touch var www HTML index. Okay, and there we go. Here is our beacon. Here's our event. So salt beacon Stuart fired the event, the iNotify beacon, and then the path to the file. So var www index.html, and we can see that it was indeed written to. So now let's set up a reactor to do something about that. So master config, jump down to our reactor config, and let's go ahead and grab our event here. Put that in place, and whenever that is triggered, let's go ahead and kick off a reactor file that is going to fix the welcome. So let's make a new reactor file called fixwelcome.sls. And then we're going to edit that file. While we're editing that file, I'm going to go ahead and restart my saltmaster. System ctl restart saltmaster. Okay. Now, the thing that we want to do is we want to fix the welcome file. And for that, we're going to do a command state.sls. Going to specify a target. Let's figure that out. In fact, let's pull that out of the event data, data.id. So the minion that triggers the event will be the one that gets targeted. And the SLS file that we wanted to run, let's see, is going to be our salt star cp.list states, just as a reminder, and it's going to be the apache.welcome. Oops, apache.welcome, that's the one we want. All right, so what we have here on the left is the equivalent to running salt some target state.sls apache.welcome. Okay. So let's save that. Oh, I just realized got a mistake here in my reactor config. The Stuart's name is in the thing here, so we need to glob on Stuart. So if any minion fires this event, then we want to fix the welcome. All right, with that in place, let's go ahead and give it a try. So I'm going to listen to the event bus once again. And now I'm going to jump over to Stuart, and I'm going to edit that file this time. Okay. Edit that, save it out, and let's see what happens. All right, so we can see we got our beacon event, so Stuart fired that, saying it was changed, followed by a new event. So we ran state.sls Apache welcome. So there's the new event. Now let's look for the return. There we go. So Stuart gives us a return. And here we've got the diff where it puts it back into place. So let's make sure that that's actually the case. Perfect. In this video, we learned about beacon modules to automatically create Salt events. In the next video, we're going to talk about how to debug the Salt reactor. Video 6.6, how to debug the reactor and best practices. In this video, we're going to talk about how to debug the reactor. We're going to talk about the processing workflow that it goes through. We're going to talk about reactor best practices. And finally, we'll talk about the future of Salt reactions. So the best way to debug the reactor is to stop the saltmaster daemon and to start it up in the foreground with debug logging. So to do that, we're going to do a systemctl stop saltmaster, and then we're going to start the saltmaster in the foreground like this. We could also edit the saltmaster config and change the debug logging from there, and then just look in the saltmaster log. But I tend to prefer to do it in the CLI here for the reason that usually it's a one-off operation. You debug one SLS file and then you're done until you have to add another SLS file into the mix. Since, as we talked about in the previous video, it's best to use the reactor to kick off other operations, the reactor itself tends to be pretty small. All right, so once that's done, then we're going to jump over to Jerry and let's send an event and see what we can see here on the console output. So the line that we're looking for is gathering reactions for, and then the event tag. Here we go. Gathering reactors for, my app deploy, compiling reactions for, my app deploy, compiling template, so you can see there was a match here, deploy my app, and then we can see that that it actually rendered the file. So we've got the same profiling and output information that we've seen with SLS files. So rendering it using Jinja, and the render data from file. So like with debugging SLS files in states, this is what we need to debug the reactor file. We need this output to see what Jinja produced. In this case, we can see that Jinja produced Jerry and it produced versions master, right? So that tells us that Jinja is doing the right thing, and then we can eyeball the YAML, or we can look at the result of the YAML rendering here if we want to look at a data structure version of that. But that is the very best way to debug the reactor. If there's an error in our YAML or our Jinja, it will show up here. And then finally, it's a nice thing to watch the event bus to actually see the thing that the reactor sends out. So what happens is the reactor is watching the Salt event bus. So a Salt event arrives, the reactor matches it against the list in the reactor config that we saw in the previous video, and then the SLS file for that matching event is rendered into a data structure. That data structure is then used to invoke a function in a worker pool. So this is the thing, this last step is the thing that can be long running. This can be, say, an orchestrate run or whatever else we want to invoke. But since it's invoked in a worker pool, we don't care what it does or how long it takes. It just does what it needs to do. The SLS file that matches the event and renders that data structure, that's the thing that needs to be quick. And so, since reactor SLS files must be rendered quickly, try not to do too much in them, right? They should not be complex. They should be fire and forget. See an event, generate a data structure that's used to call some other function. So really, orchestrate is a wonderful thing to pair with the reactor because orchestrate can do so much stuff, and it runs from the master just like the reactor. And so this allows you to, say, write an orchestrate file and debug an orchestrate file from the CLI. And once that's baked, once it does what you need it to do, you simply call it from the reactor and you're done. You don't have any additional debugging to do. You don't have to fire an event. You don't have to view this reactor output in order to troubleshoot things because all of the complexity is happening within orchestrate. So the reactor is simple, as we've been talking about. It sees an event, it triggers an action. It sees an event, it triggers an action. There's a new addition to Salt called Thorium. Thorium is a complex decision engine. And the nice thing about Thorium is it's a time aware and it tracks context. Thorium allows you to say, watch the Salt event bus for the following event tag. If the following event tag happens, and then within a 5-minute window, another event tag happens, then take some action, right? That kind of thing. So it allows you to kind of string together events and kick off more complex things. So it's brand new. So keep an eye on the SALT mailing list and the SALT release notes for additional improvements there. There's some documentation on thorium in the SALT docs already. But like I said, it's new, so if you dive in there, feel free to file issues and that sort of thing if you run into trouble. So in this video, we learned how to debug the SALT reactor. In the next section, we're going to learn all about SALT's REST API. Section 7, the SALT REST API. In the previous section, we learned about SALT's event system in the reactor. In this section, we're going to learn how to use SALT's REST API to access all the parts of SALT that we have covered throughout this series. We're going to talk about how to install and configure SALT API. We're going to talk about the difference between synchronous and asynchronous commands. We're going to use SALT API to integrate with external systems. And then we're going to wrap the series up and talk about some additional material. Install and configure SALT API. In this video, we're going to take a look at what NetAPI modules are. We're going to talk about SALT's Python API. We're going to talk about SALT's external auth system. And then finally, we're going to install and configure REST Cherry Pie. So NetAPI modules are yet another module type in SALT, and they have the contract that they bind to a port and start a service. If we jump to the module index and down to N, we can see the list of NetAPI modules that ship with SALT. There's 3, REST Cherry Pie, REST Tornado, and REST Whiskey. Now these 3 all provide a REST interface, but NetAPI modules are open-ended enough that they can provide any kind of interface that listens on a port. So keep that in mind. REST Whiskey is a very bare bones REST interface. It's no depths. It's sort of a proof of concept. It's not recommended for most use. REST Tornado is the new kid on the block. Since SALT depths on Tornado for its concurrency library, it makes sense for us to start providing the default REST interface using Tornado because that's one fewer dep to install. And also Tornado is nice and performant, but it is not feature complete. It's missing quite a few features and it's not recommended for most use. REST Cherry Pie is the currently recommended REST interface, the NetAPI module for SALT. It is the most featureful and in most cases it's performant enough for most people. So we'll talk about those in detail in the next video. In order to use NetAPI modules, you have to know a little something about SALT's Python API because SALT API is a thin wrapper around SALT. It just exposes SALT's Python API for external consumption. So that means we have to dive into the Python API just a little bit. Now, if you're not a Python programmer, the function calls that we're making still have good documentation, and you don't need to know Python to call into them. You just need to know where to look them up in the docs. So let's do that now. If you jump to the SALT docs and scroll down here, there's a page called APIs. If we bring that up, one of them is Python Client API. And that goes through all of the client interfaces. Now what client interfaces they are classes in SALT that abstract some kind of section or part of SALT for certain things. And this document also talks about how SALT will, say, load the master or minion ops into the ops dictionary and how it loads grains and other modules, that sort of thing. So it's well worth reading if you're interested in that. But we're just going to talk about the client interfaces. So if you use SALT at the CLI, then you are calling into local client, a class called local client that has various methods on it for sending commands down to minions. If you call out to SALT in the reactor or via orchestrate, again, you're calling into local client. You're calling something that wraps local client. That's true of SALT run and runner client as well. Every time you call SALT run at the CLI, you're calling into runner client. SALT call is caller client. Wheel client is sort of an outlier. It came a little bit later in SALT's life, say well before SALT key. Wheel client wraps wheel modules. Wheel modules are intended to programmatically manage the SALT master. We can see them in the module index. We jump down to W for wheel. And so wheel modules allow you to programmatically manage the SALT master, so managing the master config or files and file roots or files and pillar roots. You can also accept and do things with minion keys right there on the master. And so SALT key has been retrofitted to use the key wheel module. But that's why it doesn't have a direct CLI equivalent. Cloud client and SSH client then wrap SALT Cloud and SALT SSH. In each case, these client interfaces are different from one another because they do different things. Local client sends commands down to minions. Runner client calls functions directly on the master. So in all cases, you'll want to pull up the docs on each to see what arguments and keyword arguments they accept and don't accept, that sort of thing, because they are different from one another. Now let's talk about Salt's external auth subsystem. It uses what are called auth modules, yet another module type in Salt. So if we jump back to our module index and down to A, auth modules are modules that can authenticate a user with some external system. Now, Salt's external auth subsystem is intended to provide authentication into Salt from some external place, like a REST API or something like that. So if you want to provide authentication with Salt from an external place, external auth modules are usually the way to go. If you can log into the system that is running the Salt master, you probably want the client ACL subsystem instead. Now you can use Salt's auth system at the CLI, and we'll see that in just a moment, but in general it's less useful if you can log directly into the box. Client ACL is usually preferred. So you can see that these modules allow you to authenticate with various services, like some Django website or Keystone if you're running OpenStack, or LDAP. Or you can authenticate with the local PAM system, but again from an external place. Or you can authenticate with some arbitrary REST service or Stormpath, the web service, that sort of thing. And again, Salt API just wraps Salt. So the external auth subsystem is doing all of that work. It's it's authenticating users, and then it's also authorizing the Salt commands that you run. So let's go ahead and take a look at it. To do this, we're going to edit the Salt master config. And there is a section in here called external auth. So we're going to take this, and we're going to copy it. And the backend that we're going to use, the external auth module we're going to use, is auto. Auto is something that we use for testing, and what it does is it returns true for any username that you pass in. So let's change this to salt dev. All right, now after this is a list of modules that we want to whitelist this user to be able to run. Now these are regular expression matches, okay? So that's why we've got the dot star, because it's a regular expression match. So this says the salt dev user can run anything in the test module, right? We can do the same if we just want to allow a user to run anything, right? It looks like that. And then if we want the user to allow the user to run either runner modules or wheel modules, then we have to whitelist those specifically, and that looks like that. So now our salt dev user can run anything, anywhere. If we wanted to restrict this by a host, we could do that as well by providing one additional level of indentation here. So this would be the host. So in this case, it would be a compound command. So grains at OS family Red Hat, right? And then with that in place, we just increase everything by one additional level of indentation. And so that allows us to target a host, right? So now the salt dev user can run any of these commands only on this host. And then if we wanted to run different commands on different hosts, we could say, how about, let's see, there we go. Right. So now the test user, the salt dev user can run anything on Red Hat, but only things in the test module on Debian. So keep in mind, this is a compound match, and these are regular expression matches against the function. For this, we're just going to allow our user to run everything on anyone. Okay. All right, so with that change in place, we're going to restart our salt master. System CTL, there we go. Restart salt master. I'll take my minions just a moment to reconnect, and then we can test out the EL system here at the CLI. So I'm going to run our regular test.ping just to check to see if they're authenticated yet. And then in order to use the external auth subsystem, we're going to use the -a flag to salt. Okay. And then this flag takes the backend that we're authenticating with. In this case, it's the auto backend. Okay. So now it's asking me for username and password. So I'm going to do salt dev, and then any password will do because we're using the auto backend. And there we go. So it has allowed this user. If we do a fake user, then Salt will then deny that. Now this is a master-side check. This check only happens on the master, so if you're logged into a minion, then you're logged in as root already, presumably, and this isn't going to help you. This is just for sending commands down to the minion. So there's the external auth subsystem. Now when we've authenticated like that, Salt generates what's called an EAuth token. And we can take that EAuth token and we can reuse it in subsequent calls, and we'll see what that looks like when we talk about the REST CherryPy module here in a moment. But first, let's install and configure REST CherryPy. As I mentioned, this module is the default REST interface in Salt, and by far the most featureful. Now, one caveat to mention is there are some SSL problems with some CherryPy versions, and that is compounded by the fact that there's some SSL problems with between Python 2.7 and 3.4. It got a little fiddly, and then there's a couple of OpenSSL version problems as well. So the whole thing is a bit of a mess, I'm afraid. But in general, running CherryPy 3.2.3 is best on most distros and most Python versions. It's not going to be a silver bullet, but generally speaking, it's good enough, or it's the most robust. So in order to start a NetAPI module, what you do is you put the configuration for that module into the master config. And then if it's there, then it will start that module. In this case, we need to say REST CherryPy and what port we want it to start on. So let's go ahead and do that. So still in our master config here on the left, I'm going to jump down to the bottom, and I'm going to add a new configuration here, REST CherryPy, port 8000. And let's also go ahead and generate some self-signed certificates for this. Because we're going to be sending Salt authentication credentials over the wire, it's a good idea to always secure this, even in testing, because it's kind of an important thing, right? Those credentials are keys to the kingdom, essentially. So if we jump to the REST CherryPy docs, it will kind of walk you through this in this setup section. And we can generate self-signed certificates using Salt, right? All we have to do is have the PyOpenSSL package installed. We're going to call a module, the TLS module, in order to do this, and we're going to do that from the Salt master, but we're going to use Salt call to call this module, which means we need to have the minion package installed, even if we're not going to be running the minion daemon. So let's go ahead and yum install PyOpenSSL and Salt minion. Since this is on CentOS, our master's on CentOS, it will not start the minion daemon by default, and it'll just give us access to that Salt call CLI. All right, with that in place, I'm going to go ahead and copy this. And that will generate those certificates for us, and it will put them in this expected location, etc PKI TLS. Okay. So now we can specify the SSL cert and the SSL key in our REST CherryPy config, and it will use those certificates for us. There we go. All right, so with that in place, I'm going to, once again, restart my Salt master because we edited the master config once again. And I'm also going to start Salt API. Okay. Now, if this worked, then we are now listening on port 8000. And we can, of course, check that with a variety of ways. We can call it to netstat to see if it's actually listening on the port, or we can just try to access it. So let's do that now. I'm going to specify the K flag to curl to ignore, to not check SSL certificates since it's self-signed. That's not going to do anything for us. And I have to specify HTTPS here so that curl uses the right port, uses the right request, and then localhost 8000. There we go. We got a reply back from our REST CherryPy. All right, so in this video we learned about Salt's Python API and how that is exposed as a REST interface using these various NetAPI modules. In the next video we're going to dive into and explore the REST CherryPy interface. REST CherryPy. In the previous video we learned about Salt's Python API and the EAuth system. In this video we'll do a deep dive with the REST CherryPy NetAPI module. We're going to take a look at an overview of what the module provides. We're going to talk about how to authenticate with session tokens, or how to use Salt EAuth tokens instead. We're going to talk about how to access Salt's Python API via client interfaces, and we're going to run sync and asynchronous commands and talk about the differences of each. So to start with, the REST CherryPy module uses the CherryPy framework. that does two things. It provides a web framework, and it also provides a built-in production-ready HTTP server that is written in Python and supports SSL. It provides a standard WSGI application interface, which means the REST CherryPy module can be served with Apache and mod WSGI, or Nginx in the equivalent, or any other server that can serve up WSGI applications. And it exposes all of Salt's Python API. Anything you can do in Salt, you can do from REST CherryPy. It also provides a few things like an event stream and webhooks, which we'll talk about in the video after the next video. And it does content negotiation, which we'll see in just a moment, where you can ask it for a particular return type, YAML or JSON, that sort of thing. And it was written to drive a JavaScript single-page application. So, as we discussed in the previous video, Salt actually provides authentication and authorization, and Salt API just wraps what Salt already provides. Salt API provides two different ways to tap into that system. One is using cookies, and one is passing EOT tokens directly. So if you use the cookie approach, then it requires a login step, and that will return you a session cookie that you can then send with subsequent requests. And that correlates to an EOT token on the backend. So what that looks like is if we were to do a Salt, or a curl, and let's do HTTPS, localhost 8000. And in order to log in, we're going to send a post request to the login URL. Now we can send either URL encoded data like an HTML form or what curl provides by default, or we can send JSON or YAML, and we'll talk about that in detail in just a moment. So for this, I'm just going to send URL encoded data because it's easy at the CLI. Username, saltdev, password, saltdev, and EOT is auto. So as you may recall from the previous video, this is exactly the same credentials, the EOT credentials that we provided at the Salt CLI in the last video. So if we do that, then we get a response back and saying everything's okay, and here's the supported clients, that sort of thing. Or here's the EOT permissions that you have access to, I should say. Now this is a little hard to read at the CLI, so instead of getting JSON back, which is the default, let's ask it for YAML, because that'll just be a little bit easier to read at the CLI. To do that, we're going to specify a header called accept, and we're going to say that we want to accept application XYAML. There we go. So same data, just in YAML format. And so as you can see, these are the permissions that came in, and here is the session token. Now this session token correlates to a Salt EOT token, but if you go this route where you log in if you log in with a separate step, then it will hide the Salt EOT token from you as sort of a convenience. Okay. As you can see, the session token also comes in as a cookie, which means we can use any HTTP client that has cookie support to send and receive that automatically. Now we could send a follow-up request, and we could pass in this XAuth token manually as a custom header, or we could just send it as a cookie. So let's send it as a cookie because that's a lot easier, and that looks like this. So we're gonna log in again, and we're going to save the result of that to a cookie. So root cookies.txt with the -c flag, so that'll save it. And then we can reuse that cookie in subsequent requests with the B flag. So instead of C, switch that over to B, and I'll just do a quick test.ping. And so we're not going to post to the login URL, but rather just the root URL. We'll talk about this in detail in just a moment. But what we're going to do is we're going to send client is local, target is star, function is test.ping. Okay, there we go. So we didn't have to pass that manually. It was done via cookies for us, right? So that's one way to go. The other way to go is to use Salt EOT tokens directly, or EOT credentials directly. And if you go this route, then you don't have to do the login step. You've already got everything you need. Now there's two ways to go about this. One is we can send the EOT credentials directly to, say, a different URL. So say we wanted to get rid of cookies there. Instead of posting to the root URL, we can post to the run URL, and that bypasses the session handling. And so it doesn't use sessions at all, and it just has you pass in the EOT credentials directly. Everything else is the same, so local client, target, function, that sort of thing. But we also want to pass in username, saltdev, password, saltdev, and EOT auto. Right. So there we go. Exact same response back, but this time we're not dealing with session cookies at all. Instead of passing in the EOT credentials, we can also pass in just token. And then the EOT token goes here, right? There's a few different ways to get an EOT token. One is Salt added a runner to generate an EOT token in recent Salt versions. If we go to the module index, R to runners, there is a auth runner now, and that has a function that can make an EOT token and return that to you with the following credentials. And you can also specify when that token expires. So if you're setting up Salt API access in a script, for example, and you need a long-running token, this is generally the best way to go. And to do that, you just pass in the token flag instead of the EOT credentials flag. And again, hit the run URL and just don't use that session handling. But most of Salt API, or most of the REST Cherry Pie module is set up to use cookies because that's kind of the most common interface, as you're interacting with it, say via a web application or something like that. So keep that distinction in mind. So the root endpoint, as we just saw, is very RPC-like. It's not very RESTful, if that makes sense. The good news is that means that we can do anything we can do in Salt via these client interfaces. And we run Salt commands by sending what is called load data in the post request. Load data is just a bunch of dictionaries, commands, right? Saying, here's the function, here's the target, here's the arguments to that function, that sort of thing. Let's take a look at what it looks like to send JSON instead. So if we were to bring back our test.ping, for example, we're sending URL encoded data here. So let's send JSON data instead. To do this, instead of sending individual form fields, we're just going to send a string of JSON. Okay? So this is going to look like this. We're going to start by sending it a list of dictionaries. I'll get back to why in just a moment. Everything else is the same, though. It's just in JSON format. So client, local, target, function, and then test.ping. Okay? Close our dictionary, close our list, and then finally close our string. We got a 400 back saying that our request was bad. And the reason is I forgot to tell it that we were sending JSON instead of URL encoded data. So we specified what format we wanted back with the accept header. In order to specify which format we're sending, we're going to use the content type header. And we're going to say we're sending application JSON. Okay, it's getting a little crowded up there on the CLI, but we're sending JSON and getting YAML back. So there we go. The reason that is a list of dictionaries is because you can run multiple commands in the same command. So for example, if we wanted to do another dictionary here, we could just specify client, local, target, star. And this time, instead of test.ping, let's do command.run. And to pass an argument to command.run, we can do one of two things. We can send positional arguments or we can send keyword arguments. Let's do positional arguments. In both cases, arg and kwarg will be singular. Arg is going to be a list, kwarg is going to be a dictionary. And so this is going to be a list of strings to send to command.run. And in this case, let's run uptime. Okay. I made a invalid JSON. So I made a mistake somewhere. Where did I make that mistake? Let's see. Forgot to close my load data there. Oh, that is not JSON. When you are sending JSON, when in doubt, don't be shy about running your command through, say, a JSON linter. So, copy and paste this into, any web-based JSON linter, that sort of thing. In this case, I made the mistake of using single quotes instead of double quotes, and of course that's not valid JSON. There we go. So as you can see, we get back the result of our test.ping, as well as our command.run. So that allows us to save and send multiple commands in one HTTP request. This is useful for, say, web applications and that sort of thing that we're going to commonly need to run multiple things in order to, say, view something on the screen. In addition, we can run jobs across the other client interfaces. So, for example, we could do let's bring this back. We could do a runner command. So let's go to our client, and we're going to change this to runner. Okay, and runners do not take a target argument. A runner client does not take a target argument, just a function. So we could do something like, oh, how about jobs.list jobs? And that'll call out to that runner and return all of the jobs that are in the job cache, that sort of thing. So runner and wheel and local also have async variants, which we'll talk about in just a moment. But just keep in mind, you can call out to each of those different function types with different clients here. Now, as we talked about in the previous video, the client interfaces are different. So, for example, local client will take an arg and kwarg parameter, but runner client does not, because it's not sending args and kwargs down to a minion to be executed. So say we wanted to do jobs.lookup JID. Instead of an arg parameter, it just takes JID. Right? And then the name of a job ID. And you can find this by looking up the documentation. So, for example, if we go to all salt modules are for runners, jump down to the job runner, and then look up JID. You can see that this function does indeed take a JID argument. Okay, and so in order to call that here, we just do JID and then the value of that argument. I don't have a JID, but yeah, there you go. Next are synchronous and asynchronous commands. We'll talk about this in detail in the next video, but same as with Salt CLI, you can run synchronous commands or asynchronous commands, right? We saw in the previous video that you can pass the --async flag to Salt, salt star test.sleep 10 --async, and this avoids all of the machinations that we've talked about previously, where Salt presents the appearance of synchronous behavior, even though, as we've discussed, everything in Salt is asynchronous. So this gives us the job ID back, and then we can, say, use that job ID to look something up after the fact. So we could look up the result of our job now that we have a job ID. There we go. We've got the return right there. And so since HTTP is not well suited to long-running connections, this is generally the preferred workflow. We'll show this in the next video, but if you want to run synchronous commands via HTTP, there's a few things to keep in mind. One is there's a timeout keyword argument to local client, which fine-tunes the timeout behavior that Salt uses in order to determine if a job is still running. And there's also a flag to the CherryPy server called expire responses. What this does is the CherryPy server has a default timeout of 5 minutes. So if you've got a job that takes longer than 5 minutes to run, like a high state that takes 15 minutes, for example, you're going to want to set this to false to prevent the CherryPy server from killing the HTTP connection if it exceeds 5 minutes. And another thing to keep in mind is, this is very common for HTTP servers. The server is going to have a default timeout, and the client, right? If you're using a browser, if you're using curl, that sort of thing, it's going to have its own timeout. And so you're going to want to fine-tune both of those things if you're kicking off long-running HTTP connections. By default, CherryPy is a threaded server, so it can maintain about 100 concurrent connections at any one time. That's enough for most usage, but if you're, say, making automated requests, or if you're making a lot of Salt requests, it might not be enough. And so it's just a good idea to avoid the long-running HTTP connections, because HTTP doesn't do it well, and you've got to tweak all of these things. And so there's a few alternatives to running synchronous commands, which is to watch the event stream and to pull for job returns. And this is a common workflow, so we're going to talk about it in the next video. So in this video, we learned how to authenticate with REST CherryPy and run Salt commands. In the next video, we're going to continue to explore REST CherryPy by talking about some convenience endpoints and the event stream and webhooks. More REST CherryPy features. In the previous video, we learned the basics of how to authenticate with the REST CherryPy NetAPI module and run Salt commands. In this video, we're going to learn about other endpoints as well as the event stream and webhooks. We're going to talk about the convenience URLs that are presented, the event stream webhooks, and how to drive a JavaScript single-page application. So to start with, we've seen the root URL, we've seen the login URL, and also the run URL. There's a few other ones that are worth noting. Now, these are just convenience URLs, meaning they just wrap other functionality that you can get just by calling out to one of the client interfaces, same as we've already seen. They just abstract out a certain kind of workflow. If you come to the REST CherryPy docs and you scroll down a bit, you can see the various URLs that are available in the REST CherryPy module. So log in, log out, right? Minions, we haven't seen yet, but we've seen this workflow. What this is this is a convenience URL for running asynchronous jobs on minions. So we've talked about that before. Let's take a look at the endpoint real quick. Let's do a curl b root keys. And this time around, we're going to hit localhost :8000, and we're going to do a GET request to the minions endpoint. And what this is going to do is this is going to give us all of the minion grains back by default. So if you hit it with a GET request, it'll give you the minion grains. Let's look at that in YAML. There we go. So all of the minion grains, okay? But the workflow that this enables is running something asynchronously and getting the job ID back, okay? We've seen this before where if we do a client of local async, right? And then target of, say, star, function, test.sleep or test.ping, whatever, right? We've seen this. Let's see. Do I have all of my JSON in a row? Not quite. Oh, I forgot to tell it that we were sending JSON once again. Content type is application JSON. There we go. So we've seen before if we send something local async, then we get a job ID back and we can look up the result of that job ID back. What the minions endpoint allows us to do is we don't have to specify the client here. It defaults to local async, so we can just specify the command to run. And then we get the job ID back, same as we did before. And we also get the URL to another endpoint that we can use to look up the result of that. So that's one of the other endpoints that we have here, which is we've seen the jobs endpoint, or we haven't seen the jobs endpoint. We've seen the jobs runner, so that we can do a jobs.listJobs or jobs.lookupJID as we did in the last video. So the jobs endpoint just does that for us. So in this case, if we do a GET request to jobs, it'll do the same thing as jobs.listJobs. If we do a jobs and then the job ID, that'll do the same thing as jobs.lookupJID. Okay, so that would look like this. Oops, don't need the extra slash there. And we can send a GET request. We don't need to send a POST request for this one. And so if we do a GET request to jobs and then that job ID that we got back from the previous command, we can look up the result of that job. And there we go. Jerry and Stuart both returned true. And so that is a nice way to, say, avoid that synchronous behavior that we talked about in the previous video where you have to keep a long-running HTTP connection open. So if you've got a high state that takes 15 minutes to run, kick it off using this endpoint, get a job ID back, and then just pull this job ID. We're not sending anything, so we don't need this header. And so now we can just pull this job endpoint, and if it returns empty results, or if it doesn't return enough results, then it's not finished yet, and we can just keep pulling until it's finished, that sort of thing. So that's one way to do that asynchronous running a job, looking up the result later. Another convenience URL is generating keys. So if we were to say look at the keys endpoint, this will allow us to do a couple of things. Let's pull it up. One is if we send a GET request to it, it'll just list the keys that have been accepted. And if we send a POST request, it allows us to generate some keys. So let's take a look at that real quick. Let's see, jobs. So let's switch that over to keys, GET request to keys. That'll show us the keys that have been accepted. Okay, so you can see, as you recall, we rejected one for Frank, and then we've got Jerry and Stuart right there. But generating keys is kind of interesting. So what this allows us to do is this calls out to a wheel function that generates and accepts a key. So we can call that wheel function directly if we want to. But what this convenience endpoint does is it calls the genAccept function, same as you can, but then it bundles that up into a tarball so that you can then just decompress that into a directory somewhere. So this is, say, an endpoint that allows easily bootstrapping a new minion by by putting in a script. So like this example here is for a Kickstarter script, a Kickstart script, I should say. So you send a post request to the keys endpoint with the authentication credentials, and then that gives you back a tarball, so that you can just pipe that to tar and then output the result of that into the PKI minion directory, and poof, you've got a minion that has been bootstrapped using Salt API. You can also view Salt's event stream as an HTTP stream of events. This uses a specification called Server Sent Events, SSE. It's supported by all modern browsers, so that means not Internet Explorer, of course, but it's very easy to polyfill in Internet Explorer. It has the base functionality, it just doesn't have the right API, so it's easy to polyfill. And this is the only endpoint that is optimized for long-running HTTP connections. It's also very fast, which is important. We'll talk about that in just a moment, so let's take a look at it real quick. To use it, we're going to send a request to the events endpoint, and we're going to tell curl not to buffer the results of that. So we just want to output as they come in. Okay, so there we go. It is now listening, and it returns JSON and only JSON. You can't view this as YAML because that's part of the SSE stream. Okay, so you can see here that it is hanging at the CLI, meaning it is waiting for Salt events, and the connection is not going to time out. So if you've got a long-running connection and you want to see, if you've got a long-running command and you want to see the moment that it returns, this is a nice way to go about that. But it's fast, meaning if we were to do, say, a salt star test.ping, or if we were to do that via curl, for example, we can definitely get the results of that job on the event stream before we get the return from the HTTP request that actually triggered the event. And so because this is an asynchronous operation, it's very important that you start listening to the stream first, and then you kick off the job that can put things on the stream. But as you can see, this is exactly the same as we've already seen in Salt via the runner that shows the event stream, but this time it's in HTTP format and JSON. So this tag and data is part of the SSE specification. Tag is optional, you can actually just ignore it, and by default browsers will. And so really we just care about everything that lives inside of this data key. And so this is the payload that we're interested in, and this contains, again, the tag and then the event data, right? So there we can pluck out, say, the response. So here's the event tag, so the return from Jerry, and then the actual return itself is return true for our test.ping. Okay. So this is a nice way to get real-time updates as to what's going on in your Salt infrastructure via HTTP. It can also drive a browser-based application, as we've discussed. So that means it can serve static files, and as well as some HTML5 history API features. So if we jump to the configuration section, and we jump down to the end here, there's a few things that are relevant here. One is static, which is a path to a file system path to where your static assets live, and it doesn't matter what they are, it'll happily serve them up. And then if we want, by default, the /static URL is the one that serves those. So if you want to change that, feel free. And then if you specify app, then this is a file system path to an HTML file that will be served. So this is like an index.html kind of a thing. And that is useful for bootstrapping that single page application. And by default, that lives at /app. And so what this allows you to do is to serve that index.html file from that URL, and then that will, say, kick off the application that can then make REST API calls via AJAX from then on to drive the rest of the app. There is an example of this. If we jump to the Salt GitHub repository, there's an example single-page application. If we jump down to Salt, and then net API, and then REST cherry pie, there's an index.html file there that you can look through, and this will give you an idea of, say, how to use the event stream to get real-time events, and how you might use, say, Salt API to drive this. So well worth looking through if you're interested. So for example, we could grab this file, pull it down, and then if we edit our Etsy salt master file once again, jump down to the REST cherry pie section, we can say the app will be set to, I believe this is in root index, yep, okay. So we need to restart both the Salt Master and Salt API. Systemctl restart Salt Master. And we need to do both because they share the same the configuration file in memory. So if you don't restart them both, every so often one of them can hang on to a copy of the old version of that, and so it's just a good idea to restart both. Once that's done, with our app configured, we can then pull that up in a browser. And there we go. So here's our web application. Let's go ahead and log in. Salt dev, and auto. And so this is just kind of a simple proof of concept. So it's well worth looking over if you're interested, but it's not useful for anything real. So it's looking for salt events. So it's actually watching the event stream, and it's showing any job returns that come in. So say we could kick something off at the CLI. Salt star test.ping, and we could see that it has seen 6 salt events, and here's some job returns. Right, and there's the full return. Okay, so there's the return from Stuart and the return from Jerry. Okay, so as you can see, we didn't kick off anything here from the app, but it still saw that because it's watching the event stream. But we can also kick things off from here. So we could do, say, star command.run, and then who am I? Okay, and once again, so we get the 2 returns, one from each minion. And once again, we need to do this asynchronously. So by the time we hit the submit and the AJAX request goes out to trigger the job returns may show up on this event stream faster than the response to come back. And so we've actually kicked this off in asynchronous mode, so we're not listening for the return. But if we were, we can't rely on it. We have to do this asynchronously. And so that's a common gotcha, but something to keep in mind. You have to listen to the job event stream, or you have to listen to the event stream before you kick off the job. But there you go. So that's an example of a single page application. In this video, we explored other REST cherry pie endpoints as well as the event stream. In the next video, we're going to demonstrate how to integrate external services and systems using Salt with webhooks. Use Salt API to integrate with external systems. In the previous video, we learned about REST cherry pie's event stream and other endpoints. In this video, we'll learn how to create events using Salt's the webhook interface, which is useful for integrating Salt with external services and systems. So we're going to use webhooks to create Salt events. We're going to learn how to disable webhook authentication and why you might want to do that. And then finally, we're going to manually authenticate some incoming requests via the reactor. So you can use a endpoint in Salt API to create Salt events. It's a webhook interface. And it is by default the /hook endpoint. And you send post requests to that endpoint. And that's how you generate Salt events. So let's take a look at it. So let's listen to our event stream in HTTP. So same as we saw already. Let's see, unauthorized. So let me log in real quick. Okay. All right. So now we are listening to the event stream on the left-hand pane there. And so let's go ahead and create a custom event. Right. Now we could do this by calling the say event.send module. Same as we've already seen, but what we're going to do is we're going to use the webhook interface for doing that exact same thing. So I'm going to send a curl request. Let's see, cookies, and then The URL that I'm going to send it to is https localhost 8000 and then hook, okay? And from here on out, any post data that we send will automatically be part of the event. So if we say send URL encoded data, we could do foo is equal to foo, right? And so here we go. Here is our event. You can see that here's the data, here's the tag. The tag is salt net API hook by default, right? And then we've got some other information in here. We've got the body of the request, we've got the headers of the request, and then we've got the post data of the request. And you can see that came through as a data structure. So it took that URL encoded data and put it into a data structure for us. If we want to send a real data structure, we can do that as well by just specifying first the header to say content type is application JSON, and then the data itself is going to be JSON. So in this case, it'll be foo. And there we go. So same result, but this time we're sending JSON instead of URL encoded. So that lets us send complex data structures in the request that we send. Now, the webhook interface, like event.send itself, is fire and forget. So we get a success true back, but we don't know if anything responded to that event. We don't know if there were any listeners. It's just fire and forget, right? Same as event.send. If we wanted to customize the event tag, we could do that by customizing the URL that we're sending this to. So instead of sending it to just /hook, let's send it to /hook/ my company / my event. So if we do that, you can see that the tag that comes through is still salt net API hook, but it also has my event. So this allows a kind of namespacing for these webhook events, so that they're always going to have this prefix that prevents them from stepping on any other events that might be going on in the system, and it also kind of gives an indication to you as you're writing a reactor to respond to this event that you need to authenticate this event yourself, probably. So right now we're actually using our authenticated connection. So we're specifying our salt token via the cookie file that we've talked about in previous videos, and so this is an authenticated request. But not all services can authenticate beforehand. So for example, say you set up a GitHub webhook, and GitHub is going to send a post request to Salt API every time somebody merges a pull request or something like that, or makes a new pull request. You can't tell GitHub to authenticate beforehand. And so oftentimes it's very useful to disable the webhook authentication. When you do that, it is on you to authenticate that request. That's important, right? You must make sure that that is a valid request. Okay. So there's two ways to do that, or there's one way to do it and one additional way, additional bit of configuration. So in order to disable the authentication, you put in webhook disable auth and set that to true. So let's go ahead and do that. Let's salt master. Scroll down to our REST cherry pie config, and then webhook disable auth is true. Okay. We can also change the URL that the webhook interface is listening on. This is not a security feature, right? So instead of listening on /hook, we could say listen on /random string. Again, this is not for security purposes. This is just to cut down on automated scans of your network to see if you're, say, maybe running Salt API, that sort of thing. So you can set that to a random string, but don't rely on it for security. Okay. So I'm going to save that out. And now we're going to do systemctl restart Salt API, and to pick up that change. With that in place, we should be able to log in, start listening to our event stream, and now we should be able to send a request to that that endpoint without authenticating first. There we go. Good deal. So that will allow GitHub to, or any other third-party service, to send a call into Salt API. So how do you authenticate that request? Well, there's a variety of ways. If you come to the REST cherry pie documentation and you jump down to the documentation on the hook interface, there's a lot of suggestions in here about how you do that, right? And warnings about having to do that, okay? So one of the ways that you could do this is you could send, say, a secret key, either in a header or in the post data, that sort of thing. So like if you're calling out from Travis CI or something, you could put that secret, that shared secret, right in the post data. And then in the reactor that you're writing to respond to this, then it's on you to do something with that. So let's take a look at what that looks like. So we're sending this event tag here, right? And as we've already seen in our reactor config, we can then listen to that event tag, right? Wrap that in quotes just to be safe. And then we could specify serve reactor. How about well, let's go ahead and just deploy my app, right? Let's keep that in there. So say we wanted to deploy our application whenever a GitHub pull request was merged, right? So that would say deploy that out to the staging service, perhaps. That would be one workflow. So in this, we would then want to authenticate that request. So let's see what that looks like. So here's our reactor file that deploys the version of our application. If we were to do this from a webhook interface, we would want to do something like if data.post. Now, as you recall, that post data is available in the post attribute on that data, is equal to my shared secret. That's the simplest way to go about this. And if, right? So that way, if somebody sends a post request and they do not know your shared secret, this will not match, and so this if statement will produce nothing, and so the reactor will do nothing, right? That's a simple way to go about it, right? But oftentimes, third-party services have more in-depth ways of doing it. So for example, GitHub will actually sign their requests. So will Amazon. Now, this is going to vary from provider to provider, so there's not an out-of-the-box way to do this with all providers. So you're going to have to read the instructions, the documentation on whatever provider you happen to be integrating with. Because it's kind of a common thing to do this, there is a module in Salt called hashutil. It's an execution module, so jump down to M for execution modules, and jump down to H for hashutil. There we go. This module contains a bunch of functions for decoding or encoding hashed strings in various ways. And so these are often going to be useful in this kind of work. So you would want to, say, decode the shared secret or whatever in the hash before you do the if statement, that sort of thing. In recent versions of Salt, at the time of this recording, it's just in the develop branch. There's one specifically for GitHub, and so you might want to take a look at that to see how it's been implemented. But this will verify the signature that you get from GitHub using these other functions. So take a look at this if you want to see how that's done. And so that would allow you to do something like param1, param2, and you'd pull those parameters out of the event data. So that's one way you would go about securing that, to verify that signature from GitHub. Amazon has its own thing, and most providers are going to have their own thing, so keep that in mind. So again, set up a shared secret at the very least, and then do a no-op in the reactor if authorization fails somehow. In this video, we learned how external services can create Salt events that we can react to. In the next video, we're going to wrap this video series up with some other Salt resources. Wrapping up and additional material. So in this video, we're going to finally wrap up the video series. We're going to take a look at some other packed resources. We're going to talk about the SaltStack training courses, and we're going to talk about the Salt community and ecosystem. So there are some other books by Pact Publishing, and they are quite good resources. Now, I should say, full disclosure, I've worked with Colton Myers and Joseph Hall at SaltStack for several years, so I'm not unbiased, but they know their stuff, and so they're definitely good resources. The Learning SaltStack follows the same basic format as this video series, starting at the beginning and covering each topic in depth. It's able to cover a great deal more material, though, because it's in print. The Mastering SaltStack book dives into Salt internals and the philosophy of managing systems with Salt. The extending Salt, SaltStack talks about how to write a variety of custom Salt modules. And then finally, the cookbook contains recipes for performing many common system management tasks using Salt. So all good resources and well worth continuing your journey. SaltStack, the company, provides a training course. It's a 3-day training course. They do it on site, so they can come to you, or they can do teleconference training. They also do regional training in various times in the year, so they'll go to the East Coast or the West Coast, or various big cities. And so keep an eye on the schedule that they post at saltstack.com/training. And that training course is extremely thorough. It is a mind-bending 3 days, and it'll leave you exhausted at the end of each day. It's this video series, but with a lot more detail and covering a lot of things that we just didn't have time to get to in this video series. The Salt community and ecosystem are also a great avenue for support. So the Salt users mailing list is well populated, and it's a great place to ask questions if you get stuck or you're wondering about this or that. There's a SaltStack subreddit, which is maintained by some community members as well as a few people at SaltStack. And of course IRC. So Pound Salt on the Freenode network is a great resource. A lot of friendly folk in there that are always happy to field questions. And that brings us to the end of the video series. Thanks a lot for joining me. I really enjoyed putting it together. I hope it provided a good jumping off point for you to continue your journey into the depths of SaltStack's capabilities. There's so much there. And really the goal of this video series was to kind of show you the high-level basics of how Salt does its thing, so that you can then dive into the details of this particular module to manage this kind of service on a system and that sort of thing. So I hope you enjoyed it, and thanks a lot.